Do not try anything you are about to see at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode,
Time to go diving.
stand well back as the MythBusters probe the power of pressure.
This has never been done before.
And later, they crush it
There you go.
with some voracious vacuum myths.
This is killing me.
It's all about the PSI
It's alive!
as the team dials it up. First up, Adam and Jamie test a myth that ping pong can go fatally wrong. According to this myth, in the right conditions, a delicate ping pong ball can be as lethal as a full metal jacket. But how is that possible when ping pong balls have so little mass? Time to get this myth up to speed.
So if you're thinking an itty-bitty ping pong ball can kill you, what's your plan?
Well, force equals mass times acceleration.
Ah, I see. So what this lacks in mass, you're hoping to make up for in speed. How fast are you thinking of going?
A lot. I'm thinking supersonic.
I love it.
So, could Adam and Jamie impart enough velocity to a ping pong ball to compensate for its lack of mass and turn it lethal? To go supersonic, they need to get one flying at 760 miles per hour. Clearly, muscle power won't do it. Cue brain power.
Perfect.
Adam thinks air pressure might be the way to go.
This is what I call a breech-loading pop gun. Here's the breech. There's the ammo. Seal it up. Pressurize from here. Open it up. Point it in the direction you want to hit with a ping pong ball. Release with this high-pressure valve. And Bob's your uncle.
With the pressure pumped to the max the pop gun can handle,
95 PSI in 3.
let's see how this flies.
140 miles per hour at 100 PSI.
That's about twice the speed of hitting it with a bat. But there's a long way to go. The obvious next step is to turn up the air pressure. But they also have another trick up their sleeve.
Coming along nicely.
A long barrel, like 80 feet long. To explain the physics, a Hyneman walks into a bar and says,
So why the long barrel? Well, as long as the pressure behind the ball is greater than the pressure in front of the ball's going to continue to accelerate.
It's perfect.
so the longer the barrel, the more time to accelerate, the faster the ping pong ball.
There's a target.
Or that's the theory.
Okay, that's 140 PSI. Firing. 3, 2, 1.
I just see a hole at the other end.
Wow.
That is far out.
140 PSI plus long barrel gives an encouraging
453 miles per hour.
That's a good place to start.
Absolutely.
So we got this ball going 453 miles per hour. Wow. That's really fast, but I have to say, I don't think it's lethal. Might break a rib, but it's not going to kill you.
They need more speed, and a spot of research triggers a slight change in direction.
It turns out that physics teachers have been getting incredible acceleration out of ping pong balls. What they've been doing is they've been taking 36-inch long tube of PVC. Then they put packing tape over each end of the tube, and they draw a full vacuum in that tube.
Okay.
Here we go, pulling the vacuum.
The theory is that when the tape is pierced, air rushes in to fill the vacuum,
Just everyone back off a little bit.
propelling the ping pong ball forward at up to 300 miles per hour, even with a short barrel.
Here we go. Whoa!
Popping the sealed vacuum causes a sudden influx of air,
Holy
and the pressure differential sends the ball rocketing.
I didn't expect it to work that well. Well, the vacuum trick's working gangbusters. I actually got 375 miles an hour. That is awesome, and this is where I'm going to concentrate my energy to get the fastest ping pong ball possible. We're ready.
In theory, all they need to do now is apply the vacuum trick to the 80-foot barrel, and the result should be frightening speeds.
This has never been done before. It's scary.
Ping pong bazooka in 3, 2, 1.
But it's an unexpected and disappointing dud.
That's no good.
The high-speed camera shows the problem.
See, air rushes in this tube behind the ping pong ball. There's a vacuum in front of it, but that air sneaks past the ping pong ball, and it looks like it's providing a cushion that's actually causing it to spring back once it reaches the end. So it's not attaining enough speed or momentum to bust out.
But on the bright side, the ball is reaching incredible speeds at 30 feet.
8:29. We're well past Mach 1 here.
So shorten the tube to 30 feet, and this myth is going supersonic, right?
2, 1.
Wrong.
275 miles per hour. We're getting less out of a 30-foot barrel than I was out of a 6-foot barrel.
Even with a shorter barrel, the air cushion is still an issue.
Failure is apparently the only option.
Just as it seems they're about to choke, Adam has a bright idea. Add one to the pop gun.
We found out about this technology of adding a choke, like rocket science.
The choke is a sealed pressure chamber behind the barrel.
Oh, kidding. Vacuumizing.
Pull a vacuum in the barrel,
I really hope this works.
pressurize the
3,
choke to 100
2,
psi,
1.
and stand back.
Oh, oh. Wow, wow.
The blast of pressurized air popped the vacuum and added extra energy to the equation. But just how much?
779 miles per hour. Mama. That's what I'm talking about.
What Adam's talking about is that after all their hard work, they have a ping pong ball faster than the speed of sound. Armed with their supersonic ping pong ball bazooka, they head to Fort Mason, where they set up a 20-foot-long barrel and a supersized choke chamber running at 300 psi.
Here we go. 20-foot barrel, 300 psi. 3, 2, 1, go. That was an ever-loving smack of a bang.
But how fast did the vanishing ping pong ball actually go?
Was going at a speed of 1,100 miles per hour.
That's pretty fast.
That is pretty fast. Now it's time to find out if the 1,100 miles per hour we got out of the end of that barrel is in fact lethal. Lethal balls. That's what we're looking for. For our lethality test, today's human analog will be played by a pork butt. I think we're ready. 300 PSI lethality test with a pork butt in 3, 2, 1, go.
How did our porcine pal fare?
Dude, there's like flesh trauma going down 1.5 inches into here. I'm shocked by how much damage it did.
Now that thing actually penetrated. That's ping pong ball shaped.
That is a shocker.
That would hurt.
But I think we still need to call that this is a non-lethal hit. This is a substantial flesh wound, but it ain't lethal.
It's a close call. At supersonic speed, the ping pong ball struck like a bullet. But lack of mass meant it wasn't quite mortal. Next, it's time to take a deeper dive into pressure with a meaty underwater myth.
Before the days of scuba diving, divers would go down in those old suits with those brass helmets, just like this, right?
Sure.
They would pressurize their suit using a compressor on a boat at the surface.
To counteract the external water pressure.
Exactly.
Well, that sounds like an accident waiting to happen.
And that's what this myth is about.
According to the myth, early deep-sea diving suits had a fatal flaw. A failure in the air supply would cause a drastic decompression inside the suit, and the water pressure at depth would squash the diver into the helmet. They dive into this myth at Six Flags Discovery Kingdom in Vallejo, where there's a handy 15-foot deep pool
That is so cool.
that the occupants have kindly agreed to lend them. Tori's made a ballistics gel mini diver for a scale test.
Oh, cool, you painted him red.
Yeah, that way, if something does happen, we'll be able to see if his body does get sucked up into the helmet. All right, time to go diving.
Okay, pressurizing the suit.
A compressor feeds air into mini diver's suit, so the pressure inside it matches the water pressure at the bottom of the pool.
Ready?
What happens when the air supply is cut off?
Compressor failure in 3, 2, 1.
Okay, so the pressure on my side has gone to 0 immediately.
Air pressure is quickly squeezing the suit against the gelatin.
Well, that's good, we know.
Now it's actually squishing body into the helmet.
You're kidding me, this is working?
It's squishing up all around his neck.
Even at a depth of only 15 feet, the pressure differential squeezes mini diver like a tube of toothpaste.
Totally worked. It smashed the body into the helmet.
Oh my God.
Awesome.
I think we have a perfect proof of concept here. We could totally move on to the large scale.
But to really test this myth, ballistics gel won't cut it. They need something almost human.
So I give you Meat Man.
Using slabs of pork sewn onto a model human skeleton,
It's alive!
Meat Man slowly takes shape in the hands of the diabolical Dr. Frankenswine.
I present to you my creation, Meat Man. Oh, almost threw up. That's gross.
Armed with their man-sized meat puppet, the team heads for Santa Cruz Harbor. But before Meat Man can truly call himself a human analog, he needs a final, awful ingredient.
What we need to do is fill him up with some kind of organs, guts, blood, so that way if we do get that squeeze, we'll be able to see it come shooting into the helmet. I have no idea what that is.
With Meat Man organed up, it's time to wrestle him into his old-time diving suit. Jessie Coons is standing in for Carrie, who's cleverly timed her pregnancy to avoid the carnage. And finally suited and booted, it's off to sea for a date with the deep.
If you see any sharks, play dead.
5 miles out to sea, they reach the dive site. Grant has built an air compressor to keep the suit pressurized all the way to its target depth of 300 feet.
As he makes his descent, the pressure pushing in on the suit goes up by 0.445 psi every foot. So in order to compensate for that, I'm gonna have to add air in through this hose and push back out. Now I've calibrated this gauge to the approximate psi that I need versus the depth.
We have a live video feed from an ROV, so we should be able to see everything very easily from sitting right here.
With the bases covered, it's time to dive.
And Meat Man is in the water.
Say hello to Davy Jones.
As the cameras roll, the fleshy frogman drops slowly into the drink to meet his deep-sea fate.
What's your depth, Jesse?
31 feet.
Copy that.
But as they monitor his slow descent, the team is skeptical of a full-body squeeze.
There's a lot of meat down there. I don't think the whole body's gonna come in the helmet.
235 feet, and it's getting really dark. Thank God we got all those lights all over the place.
Okay, that's 300 feet.
Okay, stop the cage.
At 300 feet, there's 135 pounds of water pressure squeezing on every square inch of the diving suit. The only thing protecting Meat Man is the compressed air inside it.
We have Meat Man safely at 300 feet. The suit is holding. Now, we are about to cut his line to see whether or not he gets the squeeze. You guys ready to cut the line and see what happens?
Yeah.
In 3, 2, 1.
Grant cuts the line.
Whoa! Look at what's happening to his head! Oh my God! His head! Oh, Meat Man is in the helmet!
That's crazy!
Oh my God! It's filled with blood and flesh! It worked!
Yep, Meat Man is mincemeat. When the air pressure was cut, the water pressure slammed him up into his helmet, just like the myth predicted.
Oh, wow! We totally caved the helmet in!
Look at all the guts in there.
His stomach is inside his helmet.
Now, the name of this game is differential pressure. They can withstand a huge amount of pressure when they're equalized. But the second you take away all the pressure on the inside, crush. You can see, this is what's left. That is absolutely confirmed.
What do you got?
Well, it looks like we've got a bunch of fire hoses pointed down, and they're lifting a car off the ground.
That is friggin' perfect for us.
You know, if this is real, and we can actually pull this off, it's gonna be awesome.
Jamie's picked out a fire training facility about 30 miles east of the city in Pleasanton.
This is kind of a dangerous situation that we don't really want to just dive into without preparation. And so we're going to build a scale model before we start dealing with the big boys.
A system comprising pipes and valves will feed water from a fire hydrant to multiple hoses on either side of a model car 1/6 the scale of the real thing. Right on cue, fire engine and crew hit the scene to open the tap on this scale test.
All right. Dude, look at that! Yeah!
And in scale, that's about right. That's like 20 feet off the ground.
These things are pointed every which way, but because they're mostly down, it's really stable. It could not have gone better. We got liftoff, we got stability. This seems really, really possible.
What?
Fired up by the results, the MythBusters splash out on an old wreck to see if they can shoot it skywards. But Jamie crunches some numbers, and he's not so sure.
This car weighs, according to the sticker, 3,175 pounds. Now, that means that each of those hoses has to put out about 320 pounds of thrust. Personally, I don't think so.
Not one to leave things to chance, Jamie knocks up a rig to rate the pressure from a standard fire hose and heads back to the fire department to test it out before anyone in wardrobe could have a word in his ear.
We're good to go. We got 400 pounds on there. Let's fire it up.
Okay, here we go.
If one hose lifts this weight, then 10 hoses should lift the car. There's movement, but no liftoff.
There we go!
So Jamie decides to narrow the valve and raise the pressure.
Hopefully, putting this reducer on this will make for an increased nozzle reaction. That's what they call it in the industry.
Water is pumped through the truck as Jamie wills the weights to greater heights. But as the saying goes, be careful what you wish for.
Everybody over here. I think we got a little bit more nozzle reaction that time. it was like a rocket. That was exciting. In fact, that was like dangerous.
And terminal as far as any more testing goes. But on the bright side, there's no doubt that one hose can lift over 400 pounds. So they're still in business. Back at base, Adams upscaled his water delivery rig. A quick coat of paint, and it's time to hose this myth down. Or up. All available fire trucks roll up to the test site. But there's only 6 instead of the planned for 10.
I'm a little nervous about it. The math says we should be able to do it but will we?
Now let's see if a full-size, full-weight car really can take flight.
The tension is mounting.
Are you ready?
I'm ready. Let's do it.
I'm gonna get in position.
Test number 1 starts with the standard hydrant pressure of 80 psi, which Jamie steadily raises 10 psi at a time.
All right, all pumps up 10 psi. All pumps up 10 more psi.
But sadly, this car looks more likely to float than fly.
All pumps down, completely down.
Okay, we're exceeding the amount of water flow for the system.
Oh, no.
Yeah.
Well, what if we remove a couple of the hoses, or just, don't power up with 2 of the hoses?
With a fixed water supply, cutting 2 hoses will raise the pressure in the remaining 8. It's a question of finding the perfect balance. They'll start this test at 100 psi, then lift the pressure bit by bit.
10 more psi.
In test after test,
All pumps 1, 2, 0.
Jamie raises the starting pressure,
All engines 170.
repositions the nozzles, and changes the number of hoses. But try as they might, the jalopy stays firmly on terra firma. So how did they achieve this? Adam's starting to think that there's less to this car than meets the eye.
The problem is we've got an engine. That's why we're not getting any movement.
Well, let's get the engine out.
All right. There's nothing in the video we saw that said that car had an engine. And we got to get liftoff before the end of the day. So we're lightening our load by a few hundred pounds.
Daylight's fading, and this next test is make or break.
This one's going to work. I hope.
Up on 6.
With 6 engines, 6 hoses,
Come on, baby!
Up, up, up.
and no motor, the car finally takes flight.
Up on 3. Up on 3.
The hatchback hovers handsomely at 15 feet high for a full 45 seconds.
Okay, down, down, down. Cut it. Oh, yeah! Nice landing.
It worked. I didn't actually think it was going to happen, but it did. Well, just like the video.
I'd say we've confirmed this one.
Confirmed it is.
Now for 3 myths that test out the science of vacuums.
Man, that makes me nervous. That thing's so friggin' big.
Don't imagine for a minute
Come on, baby.
that the pressure's letting up.
Oh. This is killing me.
First up, Casey Jones has nothing on this myth.
All right, there's a guy. He's tasked with cleaning out one of those tanker cars on a train that holds liquid, and he's using a steam cleaner. So he's steam cleaning the whole thing, and of course, as he's doing that, he's warming it up. And it starts to rain. So he caps off the tanker car and walks away. The cooling rain causes the steam to contract, and as the myth goes, the train car crushes itself.
From a vacuum.
Exactly. Whoops.
To show that this myth isn't completely off the rails, here's Adam with a quick demo. He heats up a metal can, pours in some boiling water, caps it, and removes it from the heat.
This vessel was full of steam and air that was heated to its boiling point. Now that air is rapidly cooling. As it's cooling, they're creating a negative pressure inside the can. Oh, there we go. There we go. Oh, it's actively moving. Look at that. I'm doing this with my mind. In case you were wondering, this is all telekinesis.
Actually, it's differential pressure, but this can is fairly flimsy, so they're going to step it up to a 55-gallon steel drum.
Structurally, it's much stronger because it's round and it's got these ribs, so it'll present much more of a challenge.
The drill's the same. Pour in water, bring to the boil, seal the drum.
There we go.
And wait while it cools.
How long did it take the little cans to crush?
Those crushed very, very quickly.
You know how a watch pot never boils? Seems like that goes for cooling, too. So let's cut to the chase.
Next time we hold the camera up with magnet.
There you go.
Wow!
You can feel that.
Woo! That was so cool.
They crushed it. Literally. But before they go full scale and wreck a perfectly good, very expensive railroad tank car, there's one more test to do.
Shape and geometry are critical when it comes to pressure vessels. And so we're going to build a scale version of our tank car cylinder and see what difference that makes.
They weld together a row of 55-gallon drums. Then steam clean the model rail tanker as per the myth, heating it to 200 degrees Fahrenheit.
All right, capping it up.
A pressure gauge will tell them how strong the vacuum is at crush point.
Oh, hey!
A total vacuum measures around 30 inches of mercury.
Okay. 7 minutes in, we're at 11 inches of mercury.
But way before they reach that point,
Whoa! Awesome!
another spectacular implosion.
Oh, that was fantastic!
For these veterans of explosions, this is kind of like seeing snow for the first time.
That is awesome!
The model tank car is mangled metal. Now, can they do the same thing to this? If you're wondering how on earth the MythBusters managed to score a perfectly good tanker car to have their way with, you're not alone.
Isn't it beautiful? 67 feet long, 10 feet diameter. It holds almost 30,000 gallons of liquid. Unless you think that the shell is thin, it's actually almost half an inch thick.
It's almost 70,000 pounds of cold rolled steel. But could a simple steam cleaning accident cause it to crush like a tin can? Adam rigs it for data monitoring with a vacuum pressure gauge and heat sensor.
We just turned this tank car into an experimental vessel.
It's ready for them to recreate the implosive events of this railroad myth.
This is gonna be cool.
First, they turn on the steam, just like the cleaning crew on that fateful day.
Piping hot at over 300 degrees, its goal is to remove every last trace of residue from the previous cargo.
Then they wait, while the metal casing heats up.
It's happening.
Yeah, it's already rising.
When the temperature hits 200 degrees Fahrenheit, Adam springs into action to batten down the hatches.
Here we go. This is it.
Unfortunately, once the service guys had done their job, they closed every hatch and valve on the tank car, something they should never have done.
I am de-assing the area.
Mission accomplished.
That went smoothly.
Now for the final ingredient of the developing disaster.
All right, fire department, let's make it rain.
Copy, making it rain.
With a hot, sealed tank car, the heavens open.
Oh, perfect.
Rapidly cooling the steel vessel.
5 inches of mercury.
The trapped steam inside condenses.
6.
Negative pressure rises.
It's climbing steadily, that's what we wanted to see.
And a vacuum builds.
13.
Ah.
The pressure differential means that already more than 1.5 million pounds is squeezing on the tank car's steel shell.
Man, that makes me nervous. That thing's so friggin' big.
I know.
The small-scale tank car crushed at 11 inches of mercury.
This is killing me.
Then, 1 hour in, and pulling almost a full vacuum,
Why, they make these things tough, don't they?
Absolutely nothing happens.
Damn!
It's a crushing anticlimax.
Here we go.
But the guys aren't about to let it suck the air out of them.
Technically, what we did to this car to try and make it collapse with a vacuum was flawless. Got the tank really hot. We sealed it up really well. We pulled darn near a perfect vacuum on it, and yet nothing we did to it made it collapse. But you know what? We're not done yet.
Time to switch tracks on this myth. Perhaps the tank car in question imploded because of structural wear and tear. With this theory in mind, the guys decide to stage
A bit of a, shall we say, accident. Dropping 3,200 pounds on a tank car. Something we didn't expect to be doing in this episode. 3, 2, 1.
Yeah, that's ideal.
They've already proved steam cleaning could have pulled a vacuum. So this time they're taking a shortcut with a giant truck that sucks.
All right, Dean, go ahead and start the vacuum.
It'll pull exactly the same negative pressure as in the first test.
10 minutes, 21 inches of mercury.
23 inches. Come on. Come on, you melon farmer. Oh! Yeah! Yeah! Woo! Yeah!
Finally.
Oh! 23 inches of mercury. Holy cow!
That, my friends, is an ex-tank car, flattened by nothing but a vacuum.
Man, look at that. That is beautiful.
I've never seen anything quite like that.
35 tons of steel, flattened like a tin can.
Well, this one was a bear. How do you want to call it?
Well, I think the myth as stated, we have to conclude based on the evidence that it's busted. Your average tank car, even under an impressive amount of vacuum pressure, isn't going to implode.
Agreed, but if it's dented or corroded or otherwise compromised, it could happen.
Spectacularly so. Okay, let's get the hell out of here.
Okay.
That first myth went off with a bang, but this next one says you'll never get one of those in space.
Apparently, it is impossible to fire a gun in space.
You mean like in a vacuum?
Exactly. Think we got to test it.
I've always wanted to go to space.
Me too. Guns in space. What could possibly go wrong?
So, will a gun fire in a vacuum? And if not, why not? The theory is, first, the lack of air at atmospheric pressure in space may cause the slug to deform. Second, without oxygen, the primer can't ignite the propellant. With all space flights currently booked out, Jamie and Adam will have to test this myth in a slightly more down-to-earth way.
Yeah, baby!
By building a bulletproof vacuum chamber in the shop.
Nice.
Creating a slice of outer space in San Francisco is a challenge, but with precision and patience,
You go down first, okay?
plus lots of glue, they managed to stick it.
It's going to be beautiful.
I hope so. This was nerve-wracking.
We're gonna put a lady in here, and she's gonna turn into a tiger. Wabba!
With a vacuum gauge added, and a remote-controlled handgun in place, they're ready to fire up a control test.
Before we pull the trigger on this gun in the vacuum, we're going to fire the gun in the vacuum chamber without a vacuum to be able to compare the two. In 3, 2, 1.
There it goes. That was a bang.
Well, seemed to work pretty well.
Indeed.
Yep, they've tested the remote firing mechanism, captured it on high speed, and have a slug impact on the backboard for comparison. Time to shoot for the stars.
Gun is hot. Range is hot.
Air is pumped out of the chamber to create a space-like environment.
We're waiting for our vacuum chamber to come up to a full vacuum, and then we're gonna pull the trigger on our revolver. And I am here to tell you that I think it's gonna go bang. I don't think the vacuum's gonna have any effect on the gunpowder's ability to propel a bullet out the barrel of our revolver.
This is it, with the chamber evacuated to a full vacuum.
Are you ready?
I'm ready.
And Adam's remote finger on the trigger.
All right, here we go.
Will the gun misfire or indeed not fire, as the myth suggests?
Firing a gun in a vacuum. 3, 2, 1.
There it is.
There it is, successfully shot. That gun fired in a vacuum.
Like what he said, but the high-speed vision is less predictable.
Wow!
Almost unearthly.
I swear, if I just saw this footage, I would totally believe that it was a special effect. It doesn't look real.
Yeah.
Amazing.
We chose a revolver for this test, and you'll notice in the high-speed footage that a fireball is created around the gun when it fires. Now, that's because of the gases coming out of the cartridge to escape. If you look at the vacuum, that fireball is much, much larger. And that is because a gas, when it's exposed to a vacuum, is going to expand more.
But the astronomical observations don't end there.
Now that we know a gun can fire in a vacuum, the question arises, does the bullet behave any differently in the vacuum than in the air? We might posit that the bullet would move slower in the air because the air provides resistance where the vacuum provides none. And in fact, we did find a very minor difference. The bullet in the air traveled 5% slower than its partner in the vacuum. That's not a big result, but it is also borne out in a tiny way by the bullets that we found embedded in the glass. The bullet in the vacuum made a slightly larger pressure ring in the glass than the one in the air. It's a tiny difference, but an interesting one nonetheless.
Having put a slug through this myth, Adam and Jamie have one more space itch they want to scratch.
There is a theory floating out there that a solid fuel rocket won't work in space. But now that we have this big vacuum chamber, we can totally test that out. These bottle rockets are, in fact, solid fuel rockets with a little bit of powder inside. So here is my rocket. Ready? Watch this. This should push the car forward, right? Action, reaction. Ta-da! If that works in the vacuum, then we might have busted another myth in this episode. Rocket firing in a vacuum in
3, 2, 1, 0. Ignition. Liftoff.
Hey! It happened so fast I wasn't looking.
It worked.
Solid rockets work in a vacuum.
Let's look at the high speed.
Why not? This is a rocket in a vacuum. Watch it go.
Liftoff. 30 minutes after the hour.
So, the myth that guns cannot be fired within the vacuum of space?
It's totally busted.
Yeah, it's busted.
MythBusters and vacuums have history. A levitation machine made from a vacuum cleaner. And an intimate connection between Adam's butt and an aircraft vacuum toilet.
Oh my God!
But this next myth is dialing up the suck factor to even greater heights.
Go, go, go!
There is a story that's been on our list for a long time. I've always wanted to test it. The myth is that a standard household vacuum cleaner has enough suction to lift a car.
Well, I'm dubious, but sounds like fun.
Let's dive straight in. Can a household vacuum cleaner lift more than household dirt? How about a 5-pound weight?
Okay, so that's just barely enough to hold on to that 5 pounds.
It is.
Not much, but it's enough to get Jamie thinking.
Now, the surface area on the end of the hose is 1.75 inches. So doing the math, that means that it's pulling about 2.8 pounds per square inch. So how are we going to lift a car that weighs 2,600 pounds? Well, all you need is more square inches. In fact, if we have up to about 1,000 square inches of suction area on the car, we should be able to lift it, in theory.
When Jamie says, in theory, he often means, good luck with that. But to give themselves more square inches of suction area,
This is one of the stranger things we've built.
Adam enlarges the vacuum attachment.
I hope that works.
Jamie modifies a manifold for the vacuum cleaner.
There we go. That ought to do it.
And I've got a 50-pound weight to try and lift.
Hey!
Turns out,
Nice!
Jamie's math and their prototype work.
In theory, I think this should be able to hold more than twice that.
That is awesome!
So awesome, in fact, they're going with that model full scale.
Our plan is to build 40 more suction cups just like the one we just made. We'll position them on the roof, the trunk, and the hood. From each one will come a tube that will join to a kind of mega manifold that will be attached directly to our single vacuum cleaner. Also from each cup will be a piece of threaded steel rod that will link to a support structure we'll hang above it. We'll turn the vacuum on, then we'll lift up the steel structure with the crane, and either the car will lift up or the car will not get off the ground.
So with the rig wrangled, it's off to a test pad. The cups are placed, and the vacuum cleaner is ready to suck.
All right, you ready to turn it on and do this thing for real?
There we go.
All right, let's get them all socked down.
Roof's all good. Trunk's good.
All good. Let's go.
Come on, baby. Come on. Come on. Ah! Rats! Rats! Rats!
The problem is the hood. It's buckling slightly
The hood is boning us.
and breaking the seal.
Our solution? Cut that hood out and replace it with a piece of sheet steel.
A flat and strong sheet of metal should give a much better seal.
That ought to do it.
Look, I don't want to get overly confident here, but right away, the replacement of the hood with a flat piece of sheet steel is working magnificently.
So with confidence brimming,
A single vacuum lifting an entire car. Come on, baby. Hey, it's off the ground.
There it comes.
It's gonna work. Come on, yes! Ah! What?
It was an inch.
It was an inch
On the front wheel.
on the front wheel before failure. Yes!
if just one suction cup lets go of its grip, there's a total suction failure. So Adam calls time on this rig.
We have proven that this cannot work. We need to implement some other solution to distribute the vacuum's power and lift this car.
It's back to the drawing board.
Now we are going with a method we call the box method. Instead of 40 points of failure, we now have three. Three big, sturdy wooden boxes made out of plywood, sealed with a gasket between them and the car.
It's a straightforward, simple plan, which usually means the best chance of success. So with just plywood and plenty of gasket goo, they're ready for round two.
Looks good.
Lovely.
Back at the launch pad, the new rig is maneuvered into place.
A little more, a little top. Yeah, that's tight.
The crane is engaged,
That's good.
and the vacuum cleaner's dusted off for one more try.
So is this going to work? Well, our three boxes have a total surface area of 4,000 square inches, and we've shown that the vacuum cleaner can lift 2.8 pounds with 1 square inch. Now, that gives us a total theoretical lifting capability of 11,000 pounds. That's over 4 times the weight of our car. But as we showed earlier, it may not all be just about the math.
There speaks centuries of experience. So with high hopes and low expectations, here goes.
Starting the vacuum in 3, 2, 1. It's climbing.
It's climbing?
Yeah.
Yes! Oh, yeah, baby!
The gauges show healthy negative pressure, which spells suction.
Let's do this.
All right, let's take it up 18 inches.
Okay.
Oh,
That was the hood popping. That's good. That's cool. We got pressure.
Commencing countdown.
come on, baby. Hold on to this car.
We have liftoff.
Yes, it's off the ground. This freaking car is off the ground! Oh, man. That is freaking awesome! Oh, dude! We are lifting a car with nothing but a single vacuum. I know, this is freaking me out.
Remember, the crane is lifting the steel cradle.
Holy balls. There you go. That's about how we're feeling here.
But it's the vacuum cleaner on its own
This is every bit as satisfying as I was hoping it would be.
that is sucking the cradle to the car.
That is freaking awesome!
And to prove just that, once the car's as high as it can go, they'll pull the plug on the cleaner.
3, 2, 1.
And with no suction, gravity does its thing.
That was very satisfying.
Oh, that was awesome. Woo! So, and if anyone needs to lift a car with a vacuum, don't call us. We've done it once. We don't want to do it again. We actually lifted this thing with nothing but the power of a single vacuum cleaner. Next time someone tells you that MythBusters sucks, tell them damn straight.
Do not try what you are about to see at home.
Well, there's your problem.
In this special series of MythBusters,
it's almost too exciting.
The Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry.
Oh my goodness.
Far out physics.
Fun for the whole family.
And insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode,
Somebody order an explosion?
the MythBusters countdown
In 3.
to some explosive myths
2.
about shockwaves.
1. Bye-bye.
And later, prepare for impact. With 3 more
It's a Tory Pinata.
based on Newton's laws.
I've been waiting for this, you know.
It's MythBusters in motion.
Bring on the explosions!
As the team tests out some freaky physics.
Never get used to that.
The first myth is straight out of the movies. Our heroes trapped on a boat. A bomb set to blow. Facing certain death, they dive into the drink for protection and surface miraculously unscathed. But would that happen in reality? We know how shockwaves behave in air and water. But what happens when one moves from air into water? Will it speed up, slow down, or even be reflected by the surface? There's only one way to find out.
Good day to blow some crap up, huh?
You bet.
Step 1 is to measure how destructive a set amount of explosive is over distance in air, for which the key piece of kit is this.
An Osico rupture disc, basically a calibrated piece of aluminum foil, and over 13 pounds per square inch of pressure, it will burst, telling you that if you were standing where this disc was, you'd encounter physical injury.
Burst discs are positioned 1 foot apart up to 14 feet to see how far a calibrated block of C4 would cause injury.
All right, JD, go ahead and light it. So this is calculating injurious distance of C4. was a rush.
That'll wake you up in the morning.
It definitely has more get up and go than a cup of coffee. The shock front ruptures the burst discs up to 10 feet.
That's our danger zone.
All right, 10 feet. Now it's time for phase 2.
To find out what effect the same airborne explosion has underwater, the guys rejigged their rig to simultaneously monitor a second blast in air and in H2O.
If there's any truth to this myth, what we should see when we set off that explosive is that this burst disc will blow and this one will not.
Okay, take it up.
Well, it's time to put that theory to the test with the same amount of C4 10 feet away from the 2 pressure discs.
Go for it, JB. Light it up.
There it goes. This is invigorating.
Good morning.
Now to find out how the burst discs compare.
Two blown burst discs, 2 intact burst discs. Nice. That's what I call a result.
There might be something to this after all.
It's looking good for the myth. The water does appear to dampen the shock wave and reduce the risk of injury. But they won't know for sure until they go full scale. So it's off to Pit 232 at Arroyo Seco.
That's perfect.
A man-made water hole devoid of wildlife and perfect for what?
Yes, blowing stuff up.
But first, they've got to get their upscale rig in position.
We'll be deploying our ruptured disc masts at 5, 10, 20, and 50 feet away from the explosions.
Each has 1 burst disc above the water's surface and 2 beneath at 5 feet and 10 feet depth.
And if the myth is true, if jumping in the water really can protect you from an explosion, we should find that one of our masts has its in-air disc burst, but the ones underwater intact.
And for an in-depth result, they'll do tests with 50 pounds of 3 different explosives, starting with gasoline.
Fire in the hole! Fire in the hole!
3, 2, 1. Wow!
The platform is gone.
The shock wave from the gasoline destroyed the floating platform. But how did the burst discs fare? At distances of 50 feet, 20 feet, and 10 feet, they're all intact, above and below the water. But at the 5-foot mark, it's a different story.
5 feet away, clean through.
And beneath the surface?
The burst discs are totally intact.
Interesting.
I thought so.
This myth is in good shape, so let's step it up a notch to a powerful explosive called ANFO, which should be a sterner test than the gasoline. And remember, don't try this kind of boom in your own lagoon.
3, 2, 1. Bye-bye.
Whoops. 50 pounds of ANFO almost obliterated the rig entirely.
It's suddenly become a recovery mission.
So they head straight to the farthest marker.
Oh!
It's burst?
It's clean through.
Really?
Yeah.
Oh, God, I wonder what it's going to look like underneath.
Yeah, that's the big question.
Both burst discs are burst.
Wow!
Even at 50 feet, water wouldn't save you from 50 pounds of ANFO. Let's face it, not much would. But this myth has one more boom before it's busted. 50 pounds of dynamite.
Look at it go, our little tetrahedron of death.
50 pounds of dynamite. And 3, 2, 1.
Oh, yeah.
Wow. That was a thud.
That was more than the ANFO.
The rig has been decimated by the dynamite.
I only see one of our things left.
Yeah.
Salvage operation.
But will the underwater burst discs have suffered the same fate?
It's a hilarious horror show down here. The 5, the 10,
And the 20-foot marker
are all huddled together.
And their burst discs are all broken, a pattern mirrored above. So how about the 50-footer?
Well, that's clean through.
Underwater, however,
You're gonna love this, Jamie. The 50-foot mast, 10 foot down, the burst disc is intact.
What about the 5-footer?
The 5-footer is also intact. Repeat, the 5-footer is also intact.
Well, that says something really strong about the myth. That's great.
with 2 unburst burst discs underwater, it's a bombshell result. For some common types of explosive, diving underwater really could save your skin, just like the myth. Next, it's back to the set with another shocking movie myth.
What are you looking so excited about?
All right, we are testing a Hollywood movie myth dealing with explosions.
Great. What is it?
It's a bomb-tastic scene straight from the blockbusters. Escaping an imminent explosion, the hero leaps into the air, and the force of the blast gives them a superhuman boost. But are these film physics bang on? Or is this mission implausible? To jumpstart the myth,
Pykrete, get those legs up!
Carrie and Tori need to establish the average distance and hang time of a regular jump
All right, I'm in the zone.
by an average person.
Well, that was about 16 feet.
Do it remind you of Michael Jordan, all that air?
All right, your average is 16 feet, mine is 9.5.
All right, well, why don't we look at the high speed and see how much hang time we're actually getting?
Hang time is critical. If a blast can propel someone in midair, they need to be there long enough for it to take effect.
You know, between the two of us, we're talking about an average of 12 feet and only half a second in the air.
Yeah, you know what? That is not going to give us much time to get Buster in the air and then halfway through the jump set off an explosion.
So they decide to take a leap and use elite long jumper stats, which average around 27 feet and a second of hang time.
God, I think I'm gonna be sore tomorrow.
Tomorrow?
Luckily, our jaded jocks won't be doing any more jumping in this myth. That'll be down to Buster. All they have to do is give him a boost.
Since Buster can't jump on his own, we need to help him by giving him both upward and forward momentum. And to do that, we're gonna use this nitrogen cannon.
It's going into a blast zone, so it gets its own protective armor.
There it is.
It's beautiful. Cannon in a box.
Then Tori turns his attention to Buster, fitting him with a strategically placed rod that will launch him at the perfect angle.
Oh! Landed it.
Grant dials the cannon up to 1,500 PSI, and Buster is ready to kick butt.
3, 2, 1.
He flies through the air without a care in the world. All right, let's see how far he went.
At 32 feet, Buster doesn't just smash the Olympic records.
He actually smashed into the top of the shelving.
So they dial the cannon back for launch number 2.
1,000 PSI. 3, 2, 1.
I think that's it.
Cool.
At 1,000 PSI, Buster consistently flies around 27 feet. And the high speed confirms a 1-second hang time. Spot on.
That's good enough for an elite jumper. That's good enough for an action hero.
Time for Buster to surf some shockwaves.
So curious to see if this actually works.
Leaping dummies and explosions. I mean, I can't think of anything better.
The nitro cannon is buried to boost Buster 27 feet from ground level.
Couple more digs and we're there.
But to time the jump and blast just right requires a very tricky trigger.
Now this right here is the trigger for the cannon. It's gonna come down a line of shock tube and split in 2 directions. The first one's gonna come over here that hits this switch that fires the cannon. The other side of that goes over to the explosive through a delay cap that's going to delay it half a second to let Buster get to the top of his arc before it fires off the explosion.
Special delivery. 10 pounds of C4 is wired and ready to blow.
Here comes the firing line.
Will the shockwave extend our stand-in stumpman's jump?
Think action hero.
All right, arming in 3, 2, 1, fire.
Wow, that happened so fast. Yeah. We're gonna have to look at the high speed to see exactly what happened.
On review, the trigger worked perfectly. Buster's jump peaked just as the shockwave hit. But did he fly further than 27 feet?
All right, what do you got?
27 feet.
So that's a negative on C4.
C4, negative. But it's a high-velocity explosive, which delivers a rapid shock impulse.
So now we're moving on to a low-velocity explosive, ANFO. This should be really interesting.
Will 10 pounds of low-velocity ANFO give Buster more of a heave-ho?
Here we go.
Let's see if he rides that shockwave.
In 3, 2, 1, fire. That's a lot louder.
You can definitely feel that thud. Let's see what happened.
Yeah.
The ANFO packed a punch, and the shockwave is clear to see. But did Buster hitch a ride?
All right, what do we get?
27 feet.
That's it? So he didn't go any farther.
It's the same result again. Despite changing explosive, Buster didn't surf the shockwave.
So far, everything we've tried has failed. That's 10 pounds of ANFO, 10 pounds of C4. Neither one has moved him any further than no explosive at all. So next up,
a whacking 100 pounds of ANFO. 10 times the explosive might sound like overkill, but this is MythBusters. So it's boom or bust.
Somebody order an explosion?
All right, 100 pounds of ANFO.
And in 3, 2, 1, fire.
Dang, that was a big blast. Well,
nice disc cloud.
Yeah.
100 pounds of ANFO had the MythBusters jumping out of their skin. But did that impressive shockwave send Buster surfing?
We're looking at the same 27 feet. 100 pounds of ANFO and he didn't move at all.
27 feet again. I so wanted this to work.
Well, I guess we got no choice but to call this one busted. You can't surf a shockwave.
You can't surf a shockwave, but can you hide from one if you find the right angle?
Aren't you going to ask me about my costume?
Nope.
The myth is that in World War I, Germans were very precise about the digging of their trenches.
Towards what end?
They thought that when a mortar landed in the trench, the 90-degree corners would prevent the blast pressure wave from traveling too far in the trench. Sharp, sharp corners. That's the story.
All right. Earth-moving equipment and explosives.
Sounds like a perfect day.
It's another myth that shakes down to shockwaves. A clumsy corner will supposedly let one sail right past, while a right angle will stop it dead. But will this myth hit the wall? Before they launch full-scale warfare, time for some reconnaissance using 3 small-scale models. A straight control trench.
It's not pretty, but it'll do.
One with crisp corners.
Freaking sexy, man.
And another with careless curves.
That's how you're meant to be. Yes.
Add water, food dye,
doink,
oil, and a paddle. And you get consistent, measurable waves.
So this is our impulse wave. It is our stand-in for a shock wave. Lights! Isn't that cool? Here we go.
The machine ripples into action, while Adam marks the wave's high and low points.
Yeah, I think that's it.
At the far end of the control trench.
Our control was successful. Our wave impulse machine gave us a wave height from top to bottom at the end of the tank of 3/4 of an inch.
Next up, right-angle trench.
3, 2, 1. Huh.
a lot larger on this end than it is on this one.
Yeah, that is cool.
The right-angle tank reduces the wave height to 1/8 of an inch from 3/4 in the control, a 75% reduction. So how will the curved corner trench compare?
It looks a little bigger down here.
It does look a little bigger down there. We might have something.
The curved corners reduce the waves compared to the control, but the right angles reduce them more, which suggests those German sappers may have been onto something.
What do you think?
Well, this story's about blast pressure. We need explosives.
Absolutely. That is definitely the next step.
So the guys launch an invasion at Ione, California, to do battle with this historic myth at full scale.
We're gonna go back in time and dig a bunch of World War I trenches and subject them to some enemy fire. It's gonna bring back a lot of memories for Jamie.
In line with their shop tests, the guys dig 3 trenches. The plan is to detonate 25 pounds of TNT, the equivalent of a First World War mortar, in each one.
Coming along nicely.
To see if rigid right-angle trenches dampen blast waves better than sloppy serpentine ones.
What did you do today? I spray painted some dirt. All right, lads, bring on the explosions!
First up, they'll do a control test above ground with sensors to chart the blast at 10 feet increments.
Above ground blast. And 3, 2, 1.
I can feel that.
That was like a refreshing breeze that lasted a very short period of time.
Well, more like a red-hot fireball. But what are the numbers? 20 feet from the blast, and pressure was 39 pounds per square inch. 30 feet, it was 12. And by 50 feet, it had dropped to just 5. So, with a baseline data set, it's into the trenches. First up, the control trench, with 25 pounds of TNT.
In 3, 2, 1.
Wow, that was spectacular.
Spectacular and spine-chilling.
Oh, man.
The control trench has been well and truly trashed. And the sensors tell a smashing story. Compared to the above-ground explosion, the straight trench amplifies the blast pressure. The question now is whether those crisp right-angle corners will dampen it as per the myth.
This is the trench that the story's all about, the one with the sharp corners and right angles. And based on everything we've seen so far, by the time the blast wave gets to the end of this trench, past all these corners, it ought to be fairly small.
You ready for this?
Right angle, sharp cornered trench.
Yep.
In 3, 2, 1.
Wow!
I don't know, I think there's gonna be a crater there.
I think there might be. Let's go look at it.
It's safe to say that at first sight, that entire trench is toast. German-engineered corners to boot. But a closer inspection tells an absorbing tale.
Wow. Dude, check that out.
I think this tells pretty much the whole story, because that's intact. Everything up to that point is not. As you can see, this is the safe end of the trench. The further you go that way, the worse it gets. By the time you got here, there's not so much energy left.
The high speed confirms that the first corners seem to absorb much of the blast, and the data backs that up. At 20 feet, the PSI was 60. At 30 feet, it was 19. And at 50 feet, it was just 7. A big reduction from the control trench. But the myth says that the curved corners of the final trench will absorb a blast less efficiently. It's the moment of truth.
Here we go. This is 25 pounds of explosives in a serpentine soft-cornered trench. This is for real. This is for the money. 3, 2, 1. Bye-bye.
Never get used to that.
Gosh.
In real time, the final result is anyone's guess. The high speed suggests that the blast did pass the first corner and travel well down the trench. But as ever, it all comes down to data.
What do the numbers say?
Check out the difference between the right-angle trench and the serpentine trench.
It's clear that the numbers in the serpentine trench are higher than the ones in the right-angle trench.
I think these numbers tell us that this myth is plausible.
So it is.
Now it's time for a bit of the old equal and opposite, as the team tests out some Newtonian conundrums. Data! First up, Adam and Jamie are having a ball.
Go, baby! What are you doing?
An equation.
Go on.
Does one of these plus one of these equal this?
A wrecking ball-sized Newton cradle. That is fantastic.
Ain't it sweet? It's my favorite.
How do you want to proceed?
Well, since this is all about scaling the Newton's cradle effect, there's no need to go stampeding towards the full-on wrecking balls. Why don't we do it gradually?
You mean incrementally bumping up the size of our Newton cradles? Let's do it.
Okay.
First priority is the obvious cheap gag.
You need to stop playing with your balls and get back to work.
Now, Adam can focus on exactly how this desk toy works.
Now, the Newton cradle is effectively an instant lesson in energy transfer. When we bring this up to full-scale wrecking balls, the biggest problem we could encounter is that the energy transfer doesn't work, that when we lift ball 1 of the wrecking balls, it does not send ball 5 like you'd expect a Newton cradle to work. So how are we going to know how we're doing as we scale this up incrementally? This is how. I will pull ball 1 up to this block, which is the exact same distance from ball 1 as this block is from ball 5. I release ball 1. It sends ball 5 a certain distance that I can measure and compare against our subsequent Newton cradles.
Adam releases ball 1, and in a clear demonstration of this cradle's efficiency, ball 5 almost kisses the blue block.
What'd you get?
The energy transfer was surprisingly clean. Ball 5 traveled 98% the distance that ball 1 did.
Wow, only 2% loss after one hit.
Yeah.
Why don't we take it up a notch? Next size up.
Absolutely, let's do it.
Using the magic of montage, Adam whips up a 2.5-inch version in record time.
Shall we try it out?
And it's not just the balls that are swinging.
Oh, that's cool.
Adam releases ball 1 before measuring where ball 5 maxes out. And the results are definitely in the ballpark.
Come on, come on, come on,
It
come on,
looks
come on,
like
come
it's
on.
gonna touch.
It's 3/8 away, which is 3%, which means it's pretty freaking efficient. The desktop model, the ball went 98% of the original distance. This is 97% of the original distance. It's scaling beautifully.
Holy cojones, this myth might just work. Let's scale up to 6-inch balls, weighing an eye-watering 33 pounds each.
Wow, that's heavy.
They'll require a heavy-duty stand.
Nice rack.
Time for a trial run.
3, 2, 1.
Nice. That was a good clean one.
The reason this is called a Newton's cradle is because it's an elegant illustration of all 3 of Newton's laws of motion. As each ball collides, it transfers its kinetic energy almost exactly.
All right, Jamie, ball 5 went to 94.1% of the distance of ball 1.
Yeah, that's an additional 3% loss.
I'm still feeling pretty good about this thing.
Yeah, still working. So is increasing the mass causing us a problem? Well, we are seeing an increase in losses the more we scale these balls up. But here's the thing, it's not proportionate. These balls are over 200 times the mass of the original small balls on the toy, and yet we're only seeing a total of about a 6% loss. It's not very much.
Dude, this thing is great. What do we do next?
I think it's time for us to go check out a full-size wrecking ball.
Awesome! I was hoping you'd say that.
They're going to take a 28-inch naval buoy and cut it in half. Across the center, they'll weld a 3-inch thick hardened steel plate that should be able to transfer the energy of the swing. Inside the buoy, they'll add rebar and concrete. That leaves just 2 questions. 1, will it work? And 2, are all these ball jokes eroding the scientific integrity of the show? Let's keep rolling and see.
These things are going to get cut in half, and then we're going to weld the plates right down the middle. We're also going to weld structural stuff that we need onto it, like a bunch of reinforcing bars, and the rest of this space will be filled with concrete.
Adam and Jamie's fearsome spheres are taking shape fast.
And off we go.
And while the concrete pour isn't easy,
slow down.
It's not long before Adam and Jamie
Don, I need you to get the vibrator ready.
have this part of the build in the can.
Oh, messier than I thought.
After a 2-week build, these balls are rocking. But will they be knocking?
Let's move them out.
All right.
Rigging the world's biggest Newton's cradle will require balls of steel in more ways than one. Given their combined weight of over 5 tons, keeping these balls in the air is a serious engineering feat. Once they're safely secured and the test is underway, they'll use a giant pink ruler to measure the energy transfer.
All right, you ready?
I've been waiting for this, you
I
know.
know, me too. The world's largest Newton cradle. Test number 1 and 3, 2, 1. Go, baby! Yes! 1, 2.
3.
Ish.
4.
The pink gauge records the energy transfer from ball 1 to ball 5 at just 45%, compared to 98% for the desktop version. So what's the problem?
So check this out. Even though this is hardened steel, the areas where the balls are impacting have become flattened from the impacts. And it's not just here, it's throughout all of the balls, which means that they're all kind of squashing like hamburger patties. The amount of force here is something on the order of 500,000 times as much as what's happening with those little balls on the desktop toy.
But instead of creating bounce, that energy is being transferred into compressing the balls. They'll try one last time, pulling ball 1 back to its maximum.
2 strings, max pullback. In 3, 2, 1.
It really is now or never. And it's never.
That went quite a ways.
And now it's all done. There goes one of our cameras.
As far as we're aware, this is the largest Newton's cradle that's ever been built. And it is a Newton's cradle because it's demonstrating exactly the same physical properties that the small one does. But as we get larger and larger, it becomes harder and harder to rein in the physical losses of energy in the system, from the balls to the cables to the overhead structure. While it is a Newton's cradle, it's just never going to be as perfect as the little ones are.
This myth's busted. Though if you could build the balls out of something hard enough to withstand all that force, there's a chance it could work. Like many scientific breakthroughs, this next myth was triggered by accident.
Wow!
A specific accident in the compact myth. In the aftermath of that smash, we heard what may have been a mistaken interpretation of Newton's laws of motion.
Both trucks were traveling at about 50 miles an hour when the impact occurred. Now, that's equivalent to a single impact going into a solid wall at 100 miles an hour.
And the fans went nuts. They are revolting. They rose up and they said, no, two cars hitting each other at 50 miles an hour is not equivalent to one hitting a wall at 100 miles an hour. It's equivalent to one hitting a wall at 50 miles an hour. They say that you were wrong.
Let's test it.
The theory is because of Newton's third law. Every action has an equal and opposite reaction. So, two cars crashing at 50 miles per hour is the same as one car crashing into a wall at just 50 miles an hour, and not 100. It sounds nuts, but can this counterintuitive argument actually be right?
I want to smash some cars.
All right, then.
Today, your much-needed dose of car crash TV will be coming direct from a collision test facility in Arizona.
Here we are. This is a 1,280-foot long crash rail. It has a track embedded in it and a cable that pulls a car along that track towards the impact spot.
Inside each unlucky vehicle, Jamie has added some high-tech sensors to measure the force they'll be subjected to.
It's kind of like a black box.
And because the crash is liable to induce, shall we say, shrinkage, they need to measure the car.
Shall we log the pre-crash length?
Sure.
15 feet.
All right, then.
First, they'll test one car into a steel wall at 50 miles an hour.
All right, the cable's ready. Come on in.
The track is ready. The MythBusters are ready. And if the car is having second thoughts, well, it really shouldn't have signed up to be on MythBusters in the first place.
All right, this is one car into one wall at 50 miles an hour. Take it away.
Okay, Bob, we're ready for roll-off.
As the engines pulling the cable roar, the car gains speed till it's holding at precisely 50 miles per hour. Then, with the cable detached, it's a one-way trip to Rexville, USA.
Oops.
Time to reach for the insurance policy, if you can find the glove compartment.
Yep, it's a car crash, I think.
Yeah, I'd say what happened here is this car here hit this wall. There.
The evidence of that is undeniable. Like a hot dog hit with a hammer, the front of the car crunched up so much, it was a whole 3.5 feet shorter.
11 feet 7 inches.
This car hit that wall at 50.7 miles per hour and took an average of 58 Gs in the longitudinal direction. I'm gonna go out on a limb and say that when we smash a car into this wall at 100 miles an hour, the G load is going to be significantly higher.
With Adam perched on that shaky limb, another car is strapped into the track of doom.
Commence with the 100-mile-per-hour crash.
Like some lemon-hued, ghost-driven chariot of the apocalypse, it reaches 100 miles an hour.
It's going flat out.
And hurtles towards its own date with destiny. That impact crushed the lemon car with such force, it should be in a glass with ice and a cocktail umbrella.
I can't wait to see what the data set says about the G load.
If the data's still intact.
If anything's still intact.
Got good data.
Really?
Yeah, we got a peak on the left side of 140 and a peak on the right side of 230. And we'd normally just average those to get a resultant there.
So the midpoint's somewhere around 185?
185.
That's nice. That's significantly more than, what was the last one, 58?
58.
Data!
Before it was 15 feet. Now it's 8 feet.
So, not only did the G-load triple, the crash compacted almost half of the car. And remember, these two cars were identical. There's only one more test left. Crash two cars together at 50 miles an hour. Will they resemble the 50 miles per hour squashed hot dog? Or the 100 miles per hour crushed lemon?
Bring on the head-on collision.
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Like tragic star-crossed lovers, they're pulled relentlessly towards each other. They reach 50 miles per hour.
It's about to happen.
The cables uncouple, and... well, that was quite a kiss.
That was spectacular.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle.
There's a windshield between them.
It's pretty evident, isn't it?
It really is.
It looks just like the 50-mile-an-hour against a wall crash.
And nothing like the 100.
Nope.
Amazing.
But just to be sure, Jamie's checking the all-important data.
Well, the figures are in. The orange card got 52 Gs, the yellow card got 58 Gs, which, give or take a few Gs, is the same as what we got against a wall at 50 miles an hour.
And the damage data backs up those numbers. Both of the cars are virtually the same length as the 50-mile-per-hour wall test at 11.5 feet. Newton's third law, every action has an equal and opposite reaction, holds true. Although the two-car crash at 50 miles per hour doubles the speed, the energy of the crash is transferred to twice the mass, thereby halving it, resulting in a crash that looks like just one car into a wall at 50 miles per hour. So if the laws of motion can crush a car like a tin can a speeding bullet sweep you off your feet? Tori, Carrie, and the rest of the team are taking aim at our final myth.
This one is another Hollywood-created myth, and it's the one around a person getting shot and, like, flying backwards.
So the question is, does a bullet have enough kinetic energy to transfer to a person that would, like, knock them back, whether or not they're wearing, like, a bulletproof vest or something, just like we see in the movies?
We've all seen it happen like this in movies. To capture the action without actually shooting someone, Hollywood experts use special stunt techniques, a crane, and a whole tug-of-war team.
It's a Tory pinata.
But to test if blowback like that actually happens in real life, we're going to use real guns and a real, though recently deceased, pig.
This is our harness, basically, that's gonna hold the pig up. We're gonna put its hooves, dig the hooks into the hooves, and then this will hang from our rig.
I just saw you punch yourself in the head.
Let's hope out on the range with high-powered weapons and live ammunition, things go a little bit smoother.
That's what you want.
It's the carabiner.
That's beautiful.
Okay.
Look busy. Here's San Francisco PD former sniper Alan Normandy with quite the arsenal.
A Remington 700 308 sniper rifle, 12-gauge shotgun, a Colt M4 in .223, Thompson submachine gun in .45 caliber, and an MP5 in 9mm.
The question is, will any of these have the firepower to make pigs fly backwards? The M4 is loaded with a 9mm hollow point bullet.
Lean forward just a little bit, squeeze slowly.
There you go. A direct hit, but the pig barely twitched.
Hardly at all.
It moved a little bit, but that could have been a fly that landed on it.
Yeah.
Let's try Tori with a .45 caliber Thompson. Nope.
Damn you.
And Jamie using a .44 Magnum, shooting the same caliber used by Dirty Harry, also has virtually no effect. The bullet moved at 1,300 feet per second, but none of that forward momentum is transferred to the pig. Let's take it up a notch, or 5.
This is the same sort of bullet they use in the M60 machine gun. You remember Rambo in the first movie where he's got that belt-fed machine gun? Yeah. This is the same cartridge.
Rambo? Surely a bullet fired by that dude will send a pig packing. But no, this little pig just won't go.
Nope, back on stage. There you go.
With many of the rounds passing right through the pig, some of the energy is being expended in the hillside behind.
I think we're hitting this pig in the perfect spot. I mean, this is where the highest concentration of his mass is. You couldn't ask for better, and it's not moving at all.
Last chance, a massive, solid deer slug fired from a shotgun.
Got some movement. Ah, finally.
But the swine didn't fall back, just down.
Yeah, it actually looked like it hit the hip bone and the legs spread, and then that caused the jostling that pulled it off the hook.
With the pig off to the smokehouse, the MythBusters bring in long-suffering Buster in a bulletproof vest. The logic being, maybe if the vest can stop the bullet, we'll finally get some blowback.
Nothing.
What about the same shotgun that dusted the pig?
Hey!
Buster drops, but doesn't go back. Why? Because as we know by now, every action has an equal and opposite reaction. So to make the shootee fly across the room, the shooter would have to be thrown an equal distance backwards. It don't happen.
The simple truth about this test is it's about the impact or effect on the target can't be greater than what the shooter's going to feel, because, you know, Newton's laws still apply.
So if he was going to go 10 feet, the shooter would go 10 feet in the opposite direction.
Absolutely.
And the physics also relies on mass. No matter how fast it's going, a bullet just doesn't have enough mass to push a 180-pound pig or a human backwards.
Do not try any of the experiments you are about to see at home.
Well, there's your problem.
In this special series of MythBusters,
it's almost too exciting.
The Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry.
Oh my goodness.
Far-out physics.
Fun for the whole family.
And insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode, the team takes a dive into some watery myths.
Wow, I can feel the pressure.
Both above and below the surface.
Come, silent walrus!
First up, can water shield you from a lethal shot?
Another myth where we get to fire some guns. What's this one all about?
The myth is that you're being shot at, you dive underwater, the water protects you from the bullets.
You know, I've seen this in countless Hollywood movies. The heroes being chased by the bad guys. They all start shooting, and he escapes totally unscathed.
Well, you know, I have no doubt that the water's going to slow down and eventually stop a bullet. But what we have to test is how deep would you have to be protected by it?
In other words, how much water do you need between you and the barrel of a gun before you're safe? To find out, first build an acrylic tank 10 feet tall. Then add H2O. Next, find a human target. If no volunteers, mix up a block of ballistics gel as the next best thing. The test will be disarmingly simple. If a bullet goes through it, you're dead. If not, you'll live to swim another day. The plan is to try out an arsenal of artillery.
This is a workout just picking it up.
But this being MythBusters, they'll start small and work their way up. First in the firing line, a 9mm pistol with a ballistics gel at a depth of 6 feet.
3, 2, 1.
Interesting. That looks like we went right through the ballistics gel, Jamie.
It's a fatal hit. Traveling at 960 feet per second, the bullet went clean through the gel. How about a couple of feet lower?
Okay, this is 9mm pistol at 8 feet. 3, 2, 1.
And the result?
Whoa, no, that didn't go all the way through. Jamie?
Yeah?
It's about ½ an inch under the surface of the ballistics gel.
It's a non-lethal hit, but that's 8 feet of water and a small caliber handgun. So how much water will you need when they really ramp things up?
Can I try?
There's that sound.
I know. James Hyneman is ready?
So this is the 3-inch deer slug out of a shotgun.
At 8 feet, think you'd be safe enough?
3, 2, 1.
Maybe not.
That's all.
Now, a couple of things here. Water and electric lights don't mix well.
Yep, yank all those cords out. Just yank them out.
And Jamie hates mess.
There's a huge crack in the front piece here.
All of which means this myth badly needs a new location. Like a public swimming pool, minus the public.
I never cease to be amazed at what people will allow MythBusters to come and do. We're firing bullets into their pool, and somehow everyone's agreed to cover it.
Adams redesigned the rig for firing at an angle from the pool edge. But the rules remain the same. How much water do you need between you and the barrel of a gun to dodge a bullet?
Worst case scenario today is that somebody dies from a bullet wound.
So, with this myth back in their sights, niftily designed to adjust for the light-bending properties of water, they pick up where they left off. Ballistics gel at 8 feet and the pump-action shotgun that wrecked their first rig.
Okay, deer slug in the shotgun.
Still firing at 1,400 feet per second.
And 3, 2, 1. It's smoking.
The bullet's deep in the ballistics gel, a lethal hit. It's looking like water offers less protection than the myth might have you believe. But what the heck? Jamie's not about to call time when he's having fun.
Okay, that's clear.
So he's stepping up to a .223 rifle, firing at 2,500 feet per second. If the shotgun pierced the gel, this could obliterate it.
So this is the .223 at 10 feet.
And that's the myth buried, right?
That was right there.
Wrong.
Well, there's a problem.
What do you know? The bullet shattered before it even reached the gel.
Adam, let's just bring this sucker right up to the shortest distance we can do. What's that, like 3 feet?
Absolutely, it's 3 feet.
3, 2, 1.
Surely 3 feet can't stop that mother.
The tip of the bullet was just resting at the ballistics gel.
Wow, this thing's breaking up the minute it hits the water.
As surprised as I am to say it, 223, myth actually confirmed.
Entering the water at supersonic speed, the .223 bullet decelerates so fast that it disintegrates into tiny fragments, which sink to the bottom of the pool. On the trail of a shock result, Adam and Jamie skipped the M1 and jumped the gun all the way up to the 50 cal. An armor-piercing giant that fires at 3,000 feet per second.
I don't know whether you understand what is about to happen here, but this is the M1 Grant.
Yeah.
This is the 50 caliber.
This kills you. This kills you and everyone else in the room.
In there, right? Okay, eyes and ears. This is the 50 caliber at 10 feet. 3, 2, 1.
Well, everyone seems to be alive.
Yeah, look at the water coming off of the roof.
But would our submerged human target have survived too?
There is no bullet in the ballistics gel.
The 50 cal has a range of up to 5 miles. Through water, it didn't make it 5 feet.
What do you got?
I got a bunch of stuff. It expended all its energy within 3 feet and became totally non-lethal. Wow.
Hard to believe, but just 3 feet of water would protect you from one of the most powerful guns on the planet. It's almost like it's turned water into a solid. So why does water behave that way? Carrie, Tori, and Grant take a look at the science from another angle.
Okay, so we've got a good one. We're testing that water is as hard as pavement.
Yeah, I've heard this one. The idea is that if you fall from a height tall enough and you get up enough speed, when you hit that water, it behaves just like pavement.
So, is there any hard science to this myth? According to Grant, the answer is a solid yes.
Let me demonstrate. In this syringe, I have air. In this syringe, I have water with some food coloring in it. Air is compressible. Compresses, springs back. Water is incompressible. I try and push it in, and it doesn't compress. And that's what's gonna happen when your body falls out of the sky and hits the surface of the water. It doesn't give, just like pavement.
But as always, the proof will be in the pudding, which could be all that's left of Buster once this show hits the road or the water.
It's always exciting when the crane shows up.
The team has fitted him with an accelerometer to measure how quickly he decelerates when he lands.
So we know how much impact he experiences, and then drop him on pavement and drop him on water and compare the results.
Bullseye.
First drop, 25 feet onto pavement.
In 3, 2, 1. Ow!
With a long day ahead, the dummy took that one in his stride. But what does the accelerometer say?
Got a peak G load of 60 Gs.
Well, that seems about right. I mean, he has his legs to break his fall.
Great! That should cheer Buster up. So what does a fall from the same height
All right, that looks good.
into water look like?
Oh, that didn't look so bad. That's definitely not the same as pavement.
And the numbers bear that out.
Okay, so I got no trigger, which means that that fall was less than 25 Gs. It won't trigger anything below that. And remember, in this same situation over pavement, it was 60 Gs.
But the myth states that water equals pavement from a great height. And at greater heights, Buster would be falling at greater speeds. Time to raise the stakes to the crane's maximum height of 75 feet.
That's a long way to fall. Anybody feel sorry for Buster? No.
No.
Just checking.
We got 29.
No way.
Yeah, so that's half of what we got on pavement at 3 times the height.
Wow. All right, 75 feet into the pavement, what kind of G's did we pull?
Absolutely maxed out our accelerometer.
That means over 500 Gs. A skin-shedding impact at least 17 times harder than the H2O. But if water's incompressible, how come this myth looks as busted as Buster? The answer is to do with how water behaves at lower impact speeds. Time for Grant mini experiment number 2.
Now, water's incompressible. That's a fact of physics. And if I put my hand in the water slow enough, the water can displace. It can move out of the way. But if Buster were to hit the water fast enough, and if he had enough surface area, the water wouldn't have a chance to get out of the way. And because it's incompressible, there'll be some point at which the G-force is equivalent between water and pavement.
So, they need to go much higher than a 75-foot crane. Cue Chopper.
Come on, let's go! Get to the chopper!
And Buster's on strike. So the next best thing to a crash test dummy? Crash test pig carcasses, of course. All nicely trussed up in body bags. One for pavement, one for water.
Pig doesn't want to fly.
First up, pavement.
The idea is as simple as it is gruesome. Drop the pigs, then x-ray them to compare the damage. From a height of 600 feet, the bacon bags will hit terminal velocity before they hit the planet.
Okay, so we're at our target altitude of 600 feet.
First up, the pavement pig.
We're hovering directly above the landing zone.
Okay, we're ready.
Okay, here we go. Operation Pork Drop onto pavement in 3, 2, 1. The pig is flying.
A drag chute ensures the pig falls belly first for maximum surface area.
Oh!
Bullseye.
Once I got him out of the helicopter, the drag chute opened up, he got into the belly flop position, and most importantly, he was traveling at terminal velocity. And the best part is, we hit the pavement.
Oh, dude, that was crazy.
Did you hear that splat?
We need to get this pig into X-ray stat.
The X-ray will reveal exactly how a 600-foot fall onto pavement affects the carcass. But before we check out the results, it's time for the water pig from the same height.
Pork drop number 2 onto water at terminal velocity.
Adios, muchacho.
Okay, there it goes.
Okay, stabilizing chute, deploy. Looking good, looking good.
Belly flop, and go! Oh!
Now it's time to bring home the bacon and put this myth to bed.
How did our pig do on pavement?
Well, the pig on the pavement did really disastrously. 17 fractures. Wow. Here's a femur fracture dislocation of the spine, and to top it all off, a decapitation.
Oh! You got a dislocated head.
The pavement pig is bacon bits. The key to this myth lies in the comparison.
How did it compare to the water drop?
The water drop pig did much better, although still 7 fractures compared to 17. 6 rib fractures, and also a neck fracture, but not as bad as the decapitation.
Take 2 pigs of the same weight, falling at the same speed, in the same orientation, and the one that whacks water will get a softer landing than the one that pounds pavement.
Oh!
Slam dunk. So far, the MythBusters have been testing myths about water density and how H2O behaves under impact. Now, for one that rests upon another property of water. Surface tension. The myth is that Japanese ninjas used shoes called mizugumo to walk on water. The theory is that the wide surface area distributed their weight, allowing the stronger bonds between water molecules at the surface to stop them sinking. Adam's going to try and make his own pair.
I've got some pine-based light-density fiberboard here. It's pretty much perfect for our uses, so I'm going to use this as our stand-in for the mizugumo wood.
That's good.
With the quarters assembled, he places a shoe-sized platform in the middle and secures it all with twine.
I can't wait to see how these work.
These are my special device for storming the castle, walking across the water.
All right, then. I think Adam's going to sink like a stone. They are made of wood. They do float. But unless he's going about 80 miles an hour when he touches the surface of the water, he's going straight down.
Jamie's nothing if not unimpressed. Adam, on the other hand...
Come, silent walrus, let us storm the castle. I will don my safety gear.
If enthusiasm could float, these feudal shoes should be a roaring success. Here we go. It's one small step for man.
The first step seemed kind of promising.
One giant failure for Mythkind. So, for his next attempt, Adam decides to channel another ninja power.
To me, it seems like it's all going to be a function of my ability to move my feet crazy fast, like a cartoon. Which might be possible.
Or not.
I don't know about you, but these seem a little cumbersome to me.
Yeah, I don't think you're going anywhere on water with those things.
The important thing is that I look damn good.
Undeterred, and with the cunning of a silent assassin, Adam turns to science. Using materials that probably aren't in the ninja handbook. Aluminum, packing foam, and snowboarding boots.
To make my water boots work, I am exploiting the principle of water displacement. I weigh about 200 pounds. I'm going to try and displace in excess of 200 pounds of water. I've calculated that 4 layers of this gives me about 2.2 cubic feet per foot of water displacement. That equals about a total of 265 pounds of buoyancy.
He traces outlines of the boots onto the foam, cuts out a hole, and wedges them inside.
Awesome! I could not have gone better.
To keep the foam from breaking apart, he tapes aluminum sheeting to the base and rivets on a lightweight rail.
I've added enough strength that it can support my 200 pounds out at either end, and it only has to support half that. So there's a little bit of flex, but no breakage.
They don't exactly scream stealthy, but it's back to the test pool for round 2.
These look like fun.
Well, this is Ninja Suit 2.0. This is my attempt. What do you think?
I think it's going to be real hard to stay upright on those puppies.
There's only one way to find out. Yeah.
It's do or die. Go time. The moment of truth.
Woo! Oh, if I had any dignity, that would have been humiliating.
For his next attempt, Adam tries a gentler launch.
There you go.
And what do you know?
Oh, I'm stealthy as the night. Oh. Don't I look like silent death? Bringing justice in the night?
Adam's floating, which means his calculations about how much foam he needed for water displacement were right on the money. But forward motion, aka walking on water, is terminally broke.
I don't know about these ninja shoes, man. What do you think?
I think they suck.
While Jamie's been enjoying Adam's epic fails, he's also been thinking of a solution.
There is something that I've come up with that you can walk on it. It does have a lot of water in it. I'd like to see how that works.
His plan involves 200 gallons of water and 1,000 pounds of powdery cornstarch.
It's a Hyneman version of water.
Yeah, and you're gonna walk on it.
No way.
Think like those movies where they're walking up bamboo and stuff, you know?
All right, here we go. That is so cool!
Hey, it worked.
The reason is the cornstarch and water combo is a non-Newtonian fluid, and these kinds of fluids can change their viscosity. Cornstarch is made up of long chains of molecules. If you add water, it slides between the chains and separates them, so it flows like a liquid. But if you add pressure, the water is squeezed out, and it behaves as a solid.
It looks like a liquid, it pours like a liquid, but when you want to run across it, you're fine, because the impact of your feet is enough to change that balance. All of a sudden, you've got a solid that you're dealing with only for a second, but it's long enough for you to move across the top of it without sinking into it.
And here's the thing about surface tension. It works okay if you're moving quickly. Stop for too long, and the bonds between the molecules move aside, and you get that sinking feeling.
Funky. Oh, dude, that feels so wrong.
So far, the team has only scratched the surface of H2O. Time to take a deeper dive.
Whoosh!
First up, unfasten your seatbelts as quick as you can.
That is intense!
This is one I've been wanting to do almost since we started doing this show. The myth is that you're in a car, it goes over the side of a bridge or something into the water and starts to sink. The myth is you will not be able to open that door until the cabin of the car fills up with water, and then you can open the door and escape.
Sounds like you might be cutting it kind of close, though.
That's exactly what we're gonna find out.
This myth is all to do with pressure differential. Water exerts greater pressure than air, so it presses on the doors, holding them shut. Only when the cabin is completely full of water does the inside pressure match the outside, allowing the door to be opened. But can you really hold your breath and keep your cool long enough to carry off such a narrow escape? To get this myth revved up, they need a test car, minus one engine. They don't work where it's going.
Well, there's your problem.
The motor is replaced with weights to make sure the car sinks.
This is Jamie's new hydrogen fuel cell engine.
Now for the wet bit.
This is a high school diving pool, and this is where we're going to sink our car.
And risk their necks. Here's how it'll work. The car will be lowered into the pool from a crane.
Lovely.
Adam will be in the driver's seat. Bosom buddy riding shotgun.
I'm just going to be sitting there relaxing, waiting for Adam to freak out, and then I'll be right there with the regulator.
You ready? I'm all set.
I think it's entirely likely I may need oxygen before this test is complete.
No kidding. Talk about being thrown into the deep end. This calls for nerves of steel.
I'm going to try to start opening this door the moment I see the water get above my glass. Now, if the myth is true, I won't be able to open that door until the water level inside the car gets to the same point.
Here comes that sinking feeling.
I couldn't stop now if I wanted to. Oh, man. Oh. The water's up to my butt now. All right. Okay, it's coming past my waist. Now I can start to see under the water. Oh my God, it's coming up under the windshield. Wow, I can feel the pressure. All right, I only have a couple more breaths here.
Adam's completely submerged. And scientifically speaking, in deep shit. If this was for real, he's dead in the water. Only after he starts taking breaths on the regulator does the cabin fill up completely, allowing him to escape.
Woo!
Dead man floating.
No matter how you slice it, I died. Let's just put it that way.
That myth is confirmed. I could not open that door until the cab seemed to be full of water for a while.
Undeterred by his near-drowning experience, Adam's taken the plunge again to try a new tactic.
I'm just gonna wait until the water gets up to my ankles, and then I'm gonna try and open the door. There we go.
The water rushes in.
Okay, I'm coming up to my ankles. Now I'm gonna try and open the door.
And Adam rushes out. But let's face it, that car was not sunk.
By the time you can see water halfway up your window, it's pretty much too late.
Window. Good point. Surely you can just wind the window down when you're underwater. Back to the shop to find out.
I have one electrically powered window and I have one manual powered window. I'm going to put them under the same kind of strain that they'd experience underwater and try and open them.
Adam weighs down the door windows with 350 pounds, matching the pressure they'd be under at a depth of only 2 feet.
I do not know of a more visual way to make clear how much pressure you're dealing with when you put things underwater.
Suddenly, this looks less simple. Manual winder.
Just failed.
Busted.
The gear just slipped.
You ready?
Uh-huh.
Electric winder.
No, it's not budging.
And neither would you be if you were trapped in the car. And if you're thinking, why not just bust out? Think again. Car keys.
Keys are busted.
Cell phone.
You're screwed.
Steel-toed boots.
No.
But if you're properly prepared and have the right tool in your glove compartment,
Oh!
One hit.
bust the glass, wait for the car to fill up, and you're home free.
It doesn't take much, but it has to be the right thing.
Yeah, exactly.
But this myth's still up in the air. So it's back to the pool where Jamie thinks he can land it. So what's the answer?
Simply patience. The idea being that if you sit there, you relax, you conserve your energy and therefore your air.
Easy for him to say, because Adam's the unlucky lab rat who gets to test his theory. With blue-hued deja vu, our aquanaut says a mental goodbye to the world above. Takes one final breath and does his best to kick back and relax as if he's on a lazy Sunday afternoon drive. And what do you know? When the cabin pressure finally equalizes, Adam makes a serene exit.
I survived! Woo! The MythBusters technique worked! Woo!
Well, how are we going to wrap this one up?
Well, the original myth we started with, that you can't open the car door until the cab is full of water, is absolutely confirmed. And we've actually looked at really viable survival techniques.
Of course, the best one is just don't drive into the water in the first place.
Next up, could a sinking boat, really suck?
Well, there's a myth that says that if you're on a ship when it's sinking, it'll suck you down with it.
You're telling me this thing, when it goes down, I'm gonna go down with it because it's gonna suck me down?
Yeah.
What are the prevailing theories behind a boat sucking you down?
Well, apparently there are three. And the first one is that air that mixes in with the water as it rushes up from the boat makes the water less dense. And so it's like you're gonna fall through the water quicker that way. The second theory is that the cavities in the ship will create an area for the water to rush in, and that'll pull you into the ship. And then the third one is that the ship moving through the water rapidly towards the bottom will create a vortex above it, kind of like drafting behind a truck when it's on the highway.
Rest assured they will push out the boat and sink a ship for real. But first, they want to test out the three theories small scale. A metal rig with winch and wires will hold a box designed to simulate the action of a sinking ship. Adam makes a bubbler to test out the water density theory.
Hopefully, it'll provide us with a really attractive stream of bubbles.
And the boat box will also let them test the cavity suckage and vortex theories.
We're going to fill this with 25-pound barbell weights.
So it's off to yet another school pool.
You'll have to walk it.
This time for a lesson in ship sinking science.
Oh, it's beautiful.
Adam's positively effervescent, so he fires up the bubbler for test 1, water density.
This is lead shot.
A homemade hydrometer completes the rig.
We will see how much the density of the water changes by how far this goes up and down when the water is aerated.
Remember, the theory is that bubbles from a sinking ship lower water density, making sailors sink too.
Okay, I'm going.
All right, I'm gonna watch it. Oh, that looks cool from here.
It looks like it's going down. Yes,
oh,
definitely.
Way down.
Encouraged by the first result, Adam decides to go all in for the next tests.
Can we blur out the love handles? Be nice to me, all right?
Test number 2 is the suckage theory, that water rushes into a sinking ship and sucks you down with it. The empty boat box is suspended on the surface and loaded with 200 pounds.
Good, go.
Water enters through specially designed holes, and down it goes.
Wow.
I pulled it down.
That was intense.
Where's the hydrometer?
There it is.
That pretty much says it.
Wow. I mean, it went all the way to the bottom and hung out there for a while. Based on what I see here, you would definitely get sucked down, and I think the bigger the object, the bigger the suck.
That's 2 for 2. Now for the third theory.
Okay, hold on.
Does a sinking ship create a vortex that drags you down from above? And it's a titanic yes.
Okay, ow, first of all. Second of all, you can feel yourself in the vortex as you're going down. I mean, I did not separate from the box at all. That was intense.
All 3 theories are confirmed. At small scale, it hardly seems worth testing this myth for real. Only kidding. The MythBusters would never turn down the chance to sink a boat, even if it means being tugged down with it.
It's a nice solid little hunk of steel, and I think it ought to go down like a rock.
The 9-ton tug is promptly renamed the Mythtanic. And they set about rigging this sucker to sink.
What we have are some large threaded fittings which we're going to weld into the holes that we cut in the boat, and we'll simply unscrew them to let water in.
As unsinkable as its ill-fated namesake, Mythtanic is towed out to the sink site, where a huge crane can haul it up from the bottom should retests be required. This myth needs a sailor to go down with a sinking ship.
Swing it out some more.
And Adam's drawn the short straw. Jamie will be one of the support divers.
Just letting you know we got 50 feet underneath your boat right now, 50 feet of water. Very cold water.
The water's murky, it's cold, it's deep. This is a dangerous stunt that we're doing. I guess Adam's life is in my hands.
Adams is relaxed as a band member on the deck of the Titanic, but it's too late to pull out now. So he bravely pulls the plug.
About 2 feet of water in here now.
At this point, things go downhill fast.
All right, it's going down, bro, it's going down.
And plucky Adam chickens out. But when sink or swim are the options, gotta sympathize.
My job, I know, was to stay with the boat and feel the suction. But I swear to God, sitting on there, my body just goes, move that way, not that way.
There's nothing for it but to raise the Mythtanic and hope Adam can raise his game for a second scuttle. Rescue plan in place. It's now or never.
Okay, be careful, it might roll and you get caught. It's gonna roll, guys.
I hardly dare say it, but I can't help hoping the Mythtanic really does suck.
Stay with it, stay with it. There you go.
Sadly, no. Though Adam probably doesn't feel that way.
No suction. No suction at all. I mean, I could not have been more central to the boat where it went down. I sat on it, the entire boat just dropped underneath me, and I hit the water, my neck hit the water, and I never went any lower.
It's a titanic dud. So how to explain the promising boat box tests? Perhaps the difference was the rate of descent.
It went right down really quickly. The boat's not built like that. It's a lot larger surface area. It didn't go down that fast.
Well, you know, Jamie, I'm gonna go out on a limb here and say there is no effect. That myth is busted.
Yeah, I'd agree.
So with one ship successfully sunk, next we ponder the myth that you can refloat a boat from the bottom using only these.
Well, Jamie, your years as a captain of a ship down in the Caribbean is going to serve you well for this myth. Ping pong ball salvage.
It's true. Jamie once raised a sunken sailboat using bags filled with air. Ping pong balls contain air too. So could they achieve the same result?
These, to raise a ship.
Yeah.
Off the bottom of the ocean.
That's the myth.
It comes from the 1940s, when Donald Duck and his nephews had the comical idea of using ping pong balls for underwater salvage. That's good enough for us.
You know, one of the first questions that comes to my mind, Jamie, is how much buoyancy does a ping pong ball have?
Huh.
Or in plain English, precisely how many ping pong balls will lift how much weight in water.
Are we gonna get like a 30-foot long tong for the real thing?
A small-scale test using 1 pound of buckshot gives them their first ping pong data point.
That actually confirms my math. I think that was exactly 15 balls to eliminate a pound of weight. That's a lot of balls for a lot of pounds.
3,500 pounds, to be exact. The weight of the sailboat they're planning to sink and salvage.
It'll take just over 50,000 balls to make it neutrally buoyant, probably 60,000 to raise it from the bottom of the ocean.
That's a small sailboat.
That's a small sailboat, like a 25-footer.
60,000 ping pong balls sounds pricey. So before they burn the cash, they need to know if the balls will bear up at the ocean bottom.
Would they hold up under the pressure?
Maybe we should test it first.
Jamie knocks up a mini pressure chamber to test to depths up to 100 feet underwater.
Never let it be said that Jamie and I don't take high pressure seriously.
You ready?
I'm ready.
If the balls crack under pressure too soon,
we're at 30 PSI.
This myth is busted before Adam and Jamie have even got their feet wet.
So let's go to 45.
Okay.
I'm just gonna keep on going.
Okay.
If you hear a big boom, just dive. Whoa! That was about
60.
Well, so they didn't burst until 60 PSI. That's equivalent to 90 feet under the water. The distance we're thinking of, about 30 feet, doesn't seem like these ping pong balls will crush it all down there.
Looks like they've got the balls to deal with the depth.
Yeah, would you like to hold these?
But how on earth do you get 50,000 of them down to a sunken vessel? Jamie funnels the thorny problem through his gray matter and flushes out a bright idea.
I think we should try seeing whether a flow of water downward will carry these with them, because we might just get away with having a tube going down into the boat.
Okay, good.
Gravity takes the water down, and maybe it'll pull some of these ping pong balls with it.
If this simple system works, it's going to save them a boatload of time. So, water on, balls in.
Come on!
And Bob's your uncle.
Yeah! That's what I like to see!
I'd say that's a working thing, right?
Yeah! That works!
Okay.
With a working rig, now all they need is a boat to sink. So it's down to Monterey Harbor, where they find the perfect fit.
What a piece of crap. We'll take it.
Okay.
Thank you.
All right. Congratulations.
Thanks.
Before they can send it to the seabed,
Here goes.
the proud owners must first polish this turd for environmental reasons. Rechristened the Mythtanic II, the doomed vessel makes its final voyage to a safe location, where it's dispatched to a watery grave.
How hard does this thing go?
But is this goodbye? Or merely au revoir? Before they get down to business, They seal off the salvage area to protect the marine life.
Hey, Jamie, they're calling you.
They saw the mustache.
Yeah.
Right on cue, 60,000 ping pong balls roll up. And it's finally time to put this Donald Duck-inspired myth to the test. While Adam feeds the rig, Jamie and Dive Master Robert will be down below marshalling balls into Mythstanic 2. At first, things seem to be going swimmingly, but that could be their last hurrah, for a while at least. The system is clogging up, and Adam's reduced to feeding balls in a handful at a time.
At this point, I've only emptied 4 or 5 boxes. That's like 6,000 or 7,000 ping pong balls.
At this rate, it'll be dark before they get halfway. Then Robert pops up with a suggestion.
I think the hose is still too long. I got all this slack. If you can take about another 10 or 12 feet off of this thing.
I can take 10 feet off in 5 seconds.
The long hose is looping in the water, slowing down the flow into the boat. Will a shorter hose and a more direct delivery get faster results? The answer is a resounding yes. And with thousands of ping pong balls per hour flowing into the boat, she soon becomes neutrally buoyant. Whisper it, but this seems to be working.
Oh, that's cool.
But with victory in sight, here come those jaws of defeat.
Oh, no. They're coming up.
Is that a whole boatload of bobbing balls coming to the surface?
What's going on down there?
There's a window on top. We didn't even see it. A piece of wood glued in. That blew out.
On the front of the boat, there was this hatch on the bow that we screwed down. That hole blew out, it seems, from pressure of the ping pong balls.
A new hatch cover is quickly fitted. And before long, there are 26,000 balls in the hull. Halfway there.
The boat is upright, it's teetering. These boats have a lead keel, so it's anybody's guess whether it's actually going to work.
With the boat and this entire myth in the balance, and an estimated 23,000 balls still to go, the math unexpectedly tilts Mythstanic 2's way. Holy duck, here she comes. The 9-hour marathon salvage is over.
We succeeded. Of all things, she's on the surface. We did it.
And the key to success? Jamie's brilliant ball-dropping system.
It got the balls down there. It worked like a charm.
And who would have ever thought that you could pour ping pong balls down into the bottom of the ocean?
Actually, Donald Duck did. The guys swear they didn't know, but 80-odd years ago, Donald and his nephews came up with a rig uncannily similar to Jamie's. And like the MythBusters, they also triumphed.
Amazingly, I'd say this one is entirely plausible.
Yeah, plausible, not practical, though.
Never try anything you see on the show at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode, it's burn, baby, burn, as the team tests out myths about fire.
This is gonna be scary.
While later, they do a 180.
It's time to go to war.
And get to grips with ice.
Come on, baby.
It's a feverish ride.
That's beautiful.
As temperatures hit new highs and lows. First up, viral myths and MythBusters. They go together like C4 and explosions.
Whoa! That looks seriously dangerous. I like it.
You know, they're claiming to do this with only sawdust. Fans, they're a little skeptical. They think it's either something way more flammable or it's CGI.
Well, in theory, it could work.
Yeah, even though they say they're not using any accelerant, if the powder's fine enough, you could get that result from just sawdust, compressed air, and an open flame.
Oh, we are gonna have to be so careful.
Viral videos can sometimes be a little loose with the truth, and viewers have suggested this may have involved added accelerant, but the maker says not.
What we have here is the energy source. It's a propane tank.
All you need is compressed air, sawdust, and an ignition source. Time to test if this is for real. To make the sawdust cannon barrel, Carrie recycles an old pipe.
Well, you didn't want it to come all off in one piece, did you?
Grant works on an empty propane canister, just like in the video. Modified to hold compressed air, a high-flow valve should release it all into the cannon in one short blast.
When we push this button, it deploys in less than a quarter of a second.
Heavy-duty pipes connect the canister to Carrie's cannon. And it's ready for a proof-of-concept blow test without flame to see how high they can blast the sawdust.
I think this will work out pretty well. It's light and fluffy.
The canister is pressurized to 100 psi, and...
In 3, 2, 1!
That's good.
The problem is, it didn't go that high.
No.
10 feet in the air.
At the moment, it's not looking exactly like the height that we would expect to see.
No, not quite.
But I think it's achievable.
So what to do? Grant thinks he'll get more punch with less hardware. He fits a shorter connecting pipe. Then Carrie trims an inch or two off the legs. Scarface Balachi's already booked the bomb range.
Say hello to my little friend!
Where they get ready to blow.
So this orange line right here is connected to the air compressor, and that is the source of air for the whole cannon. And hopefully, that'll be enough to create a huge sawdust plume.
The plan is I'm gonna light the flare. Grant's gonna pull the string, and hopefully we'll get a giant tower of fire.
The pressure inside the canister rises to 120 psi.
Perfect. Good to go.
In goes the ignition source.
All right, 3, 2, 1.
Grant releases the compressed air.
Oh my God, that was the coolest thing I've ever seen. It didn't look like it was gonna ignite, and then all of a sudden, whoa, it went up. It was beautiful.
It's not just the size of the flame, but the sound. It was amazing.
It's a towering inferno of nothing but sawdust, tiny particles which burn instantly. When one particle catches fire, it ignites the next almost immediately, causing a rapid chain reaction. Better than the original?
It was way cooler.
With a potential hoax definitively unhoaxed, what next but to up the ante?
So we made our cannon to the specs of the video, and it worked. Now it's time we ramp it up, and we make a giant cannon and see how big we can make the fire!
They've clearly caught the firebug, Carrie included. She wants something more combustible than sawdust, so she tests other fine-grained substances, like flour.
That was good.
Next, non-dairy creamer, which is made from highly combustible corn syrup.
Non-dairy creamer, flame burns to my hand and into the cup. It's so flammable that there is a backdraft.
They've found their most flammable fuel. Meanwhile, Tori's increasing their firepower. He's turning this blue hopper into a launch cannon and welding on a 55-gallon yellow barrel. Huge pipes will dump compressed air into the cannon. And let's not forget to pack the fuel.
How big a cup of coffee do you think you need for 3,000 pounds of non-dairy creamer?
Back at the bomb range, the coffee creamer is loaded into their super-sized cannon.
All right, it's full.
Everything is set. So, what's the prediction?
First of all, we know that the non-dairy creamer is much more reactive in air than the sawdust. Second, the orifice size is much larger, 36 times the force, 20 times the air capacity.
If everything goes right, we could set this whole hillside on fire.
As the saying goes, careful what you wish for.
We're good to go.
Tori sets the spark. And they beat a rapid retreat.
Okay. All right, fire this puppy up.
Here we go. Non-dairy creamer cannon in 3, 2, 1.
That was frightening!
Terrifying!
This was frightening. I mean, seriously, there was a moment where I'm like, oh, crap. This was a bad idea.
When you set off an explosion, you go click, boom. When you fire one of these cannons, you go click, and like, whoosh. It's not working. Oh my God!
All I heard in my head was, run.
We should destroy this. This technology should not be shared with anyone.
And just in case you missed the message,
I hope I don't need to tell you this, but don't try this at home.
now a fiery face-off to warm the cockles of any myth-busting heart.
Fire versus ice. It's a viral video that's been going around where two hillbillies pull up into the middle of nowhere and face off, one armed with a flamethrower, the other armed with a fire extinguisher. They both fire their devices, and fire and ice meet in the middle, and apparently, according to the clip, cancel each other out.
Dibs on the flamethrower.
And don't want to hear any more about the story?
No.
All right, then. Roll the clip.
No wonder this went viral. But the team wants to know if it's a case of film fakery or fiery fact. Time to get forensic.
Well, let's scale it up.
First, they study a film frame to get a take on the distances involved.
There's 60 feet between these guys, which means each of these things has to shoot 30 feet.
Adam sets up a firing range to test a standard 15-pound CO2 fire extinguisher as featured in the clip.
The question we're concerned with is, will it actually fire out 30 feet? Honestly, I don't think so, but that's why we're doing this test. 3, 2, 1. I think that was pretty far.
Encouragingly, that was a good 25 feet.
Dude!
Very close to the required target.
I think it's time to put it up against Jamie's impromptu flamethrower.
Impromptu and top secret.
Even though we tell people not to do what we do at home, when it comes to homemade flamethrowers, I'm just not going to show you how to do it.
And that's that. Now it's time for a proof of concept test and a swift change of set.
Obviously, we can't be squirting lit gasoline around inside M5, so we've come to the San Francisco Fire Department Treasure Island Training Facility.
I'm ready.
All right, fire extinguisher versus flamethrower, small scale. Let's light her up.
Adam claims victory. But what does the replay tell them about this first test?
Here at
just under 10 feet. I think I'm about to put it, there it is, I put it out. They're 60 feet apart, so I absolutely need to beef that thing up.
Based on this result, a standard fire extinguisher has no hope from 60 feet. So Adam's making a second, modified extinguisher to give him a cat-in-hell's chance.
I clearly need more power. I'm gonna start this experiment process by measuring the 15-pound fire extinguisher using my pressure swingometer. And I'm going to be comparing that against all my subsequent measurements from all the modifications I'm gonna make. I don't need a white, billowy cloud going to 25 feet. I need to push the fire back from 25 feet. So I'm gonna start by increasing the size of my extinguisher. I'm gonna go from 15 pounds to 50 pounds. Then, with a few modifications, we'll see if I can get that pressure wave extending out almost 25 feet.
My task now is to make an honest-to-goodness flamethrower. It's 100% illegal. We were able to do it only under the direct supervision of a number of different governmental agencies.
So, once again, no details allowed, but Johnny Storm is promising Armageddon. Meanwhile, Dr. Freeze is ramping up his backup fire extinguisher.
Try it out. On the side of this nozzle, looks very much like this. Water comes in here, CO2 comes out here. Hopefully, what ends up coming out of the business end of this cone has a lot more force behind it.
Dude! Wow!
The CO2 turns the water to ice, giving the blast way more punch.
Whoa! Wow! Woohoo!
Adam's in with a fighting chance, so it's time to hit the battlefield, where Jamie unveils his beast.
It's my own personal kick-ass version of a military flamethrower.
What could possibly not go wrong?
I've got 2 tanks full of fuel. I've got a 3rd tank full of inert gas at high pressure that I'll use to pressurize the fuel tanks, such that when I pull on this lever, all of that fuel will empty out the end of this gun and burn in about 4 seconds.
So first they want to test the glass safety hutch from which Adam will launch his counterattack come nightfall.
I need to be able to stand in the path of this flamethrower and not get burnt.
Glass house, flame test in 3, 2, 1.
That looked like it might keep me safe.
It looked good.
It did? From here, it looked terrifying. And after viewing the high speed, sanity prevails. So before the showdown begins, they add more protection in the shape of large side shields.
Now all we got to do is wait for it to get dark.
Eventually, the sun does its thing. Battle stations.
It's hot versus cold at 60 feet.
This is gonna be scary.
First test.
Okay, everyone set. We're going hot.
With Adam wielding the standard 15-pound fire extinguisher.
3, 2, 1, go!
I lived! Holy that was awesome! I don't think my fire extinguisher did very much, but that was awesome!
It was, but take away his safety hutch, and Adam was barbecued chicken.
It seemed to me like I was pretty much bathing Adam in his little house in fire.
That is insane! I'm gonna have to warn my mom before she watches this episode. She's gonna think I died in there.
The myth is toast. So time to step it up to Adam's supersized water-injected extinguisher.
I am ready!
Jamie, are you ready?
I'm ready.
3, 2, 1, go!
Not exactly, but he did stop the fire stream. Just.
It almost reached you.
Wow!
It wasn't exactly like it was in the clip.
No, oh man, look at that. I am totally beating back the fire. It's definitely not meeting in the middle, but I am successfully pushing back your flamethrower.
How do you want to call it?
Unfortunately, we gotta say it's busted. I mean, the 15-pound fire extinguisher was absolutely no match at all for your flamethrower.
Even the heavy-duty one that you put together just barely held me off, but it didn't look anything like the clip.
Nah, this one's totally busted.
Now for a grapple with the grape.
So our next myth combines two things that don't normally go together: projectiles and wine.
Oh, you're talking about the exploding wine truck myth.
Correct. Supposedly, a semi filled with wine crashed on the freeway and caught fire.
Oh, yeah, and the fire gets so hot that it causes the wine bottles to violently fire out their corks.
How violently? Like, were they lethal?
Well, we don't know because no one was ever hit. But here's the mythical part. Supposedly, the corks flew 100 feet, and when the bottles went off, they sounded just like machine gun fire.
There's no doubt this blazing bottle inferno actually happened, but were reports greatly exaggerated? Did the fiery wine truck really launch corks over 100 feet with a machine gun-like rattle? They'll start with small-scale shop tests to see how far a heated wine bottle will launch a cork. And in the interests of scientific rigor, they've assembled a variety of vintage vino.
It's possible that the size of the bottle, the type of wine, or even the shape of the bottle might make a more explosive cork.
This myth is all about pressure caused by fire. As heat is applied to bottled wine, it starts to boil. That increases the pressure in the cork bottle until...
We're gonna put each different type of wine in this holder right here, turn up the flame, and compare the results.
With a scale to clock speed and a long jump sand trap to measure distance. First up, a plucky little Bordeaux.
Here we go.
You know, this could be my favorite way to open up a bottle of wine.
After 2 minutes and at 160 degrees Fahrenheit,
Oh, that was it?
the cork exits at a dismal 3 miles an hour, barely making it to the sand.
After hearing this story, we got prepared with blast shields and eye protection and ear protection. And we got 2 feet of distance.
But being glass half full optimists, the guys reset with a twist.
So this bottle looks the same as the other one, and it is, but there's one big difference. It's been chilling for a while, since we don't know whether the wine was being refrigerated when it was being transported. I'm gonna throw this in and try it again.
But will the chill mean a bigger thrill?
I think I see it swelling.
Oh, yeah. Yeah, it's starting to push out.
Okay. Woo! Nice.
Although still way short of the myth,
3 feet 4 inches.
the cold Bordeaux did fly 50% further than its warm counterpart.
A cold bottle and a warm bottle both have the same pressure, but the more drastic change in temperature that a cold bottle experiences might mean a more drastic change in pressure.
So from here on in, they're sticking with cold bottles on high heat.
Next up, Burgundy. Chilled.
But neither the Burgundies
5 feet 10 inches.
or the Sauvignon Blancs come anywhere near the mythical 100 feet.
Looks like size doesn't matter.
And that just leaves the final wine.
Long, slender bottle, high heat.
The Riesling.
30 seconds on the clock.
All is quiet until the temperature hits 200 degrees, and suddenly...
Here we go.
Whoa!
Wow. Oh my gosh.
It went off the end of the scale.
That is incredible.
Result. Maybe because of its pointed shape, the Riesling shoots its cork over 30 feet at 32 miles an hour. Still not far enough for the myth, but all is not lost.
It's time to bring out the bubbly.
Champagne is already at a pressure of 80 psi at room temperature. Let's see what happens when things heat up.
The cork looks like it's pushing out. Here it goes.
Oh my God, it's happening.
It's about to pop.
It's happening.
I could not even see where it went.
It's a champagne moment. A cork bullet that flew 60 miles an hour and lodged in the rafters over 50 feet away.
Finally, we're getting some results, and this is looking very good for the myth.
Time to pop the cork on this one for real.
To the bomb range.
Yep, there's only one destination for this bottle barbecue, and it's BYO's semi-trailer with its chilled load of champagne and Riesling, the two winners from the small-scale tests.
Whoa! Actually, in pretty good condition.
Let's burn it.
And with the truck in position, prepped, and the firewood stacked.
All right, here we go. We're lighting up.
Okay, 3, 2, 1. Let's go.
That's beautiful. This fire is burning hot.
So, what about the myth? Will the flaming truck turn into a flying cork machine gun?
I have a hard time believing that.
Tori's not convinced, and after 5 minutes, the simmering semi is still relatively quiet.
Oh!
Here we go.
Yeah. I mean, it's not like a machine gun you would imagine. It's more.
Not yet. Hold your horses. Experiment's not over yet.
Carrie's right. Good things come to those who wait.
There's your machine gun.
Hey! Oh my goodness!
Whoa!
This is better than the 4th of July.
In fact, once the gunfire sounds start, there's no stopping them.
Wow, you see shrapnel flying out here?
Yeah.
As hundreds and hundreds of bottles either pop their corks or explode in the fire.
I can't believe how well this is working. After we set the trailer on fire, those bottles started popping just like a machine gun.
It doesn't just look like a war zone, it sounds like one too. The audio element of this alcoholic calamity is confirmed. But the myth is in 2 parts, so it all comes down to this. How far did the corks fly?
Look, there's one right there.
Wow!
What distance is that?
That's easily 50 feet.
You know what? It sounded like a machine gun.
Yeah, but the myth's at 100 feet. That's not even near it. So I'm thinking this is busted overall.
Yeah, I say busted.
Now for a change in temperature with 3 icy myths. A deep freeze is coming, so have an ice day.
This is the ice cannon. 3, 2, 1.
For our first myth, Carrie, Grant, and Tori are going into the heat of battle armed with unusual artillery.
Well, I hope you guys packed your thermals, because this myth comes from the depths of winter in medieval Russia. Now, there was a town, it was under siege, and they didn't have anything to defend themselves with. So they improvised a cannon and cannonballs out of the one thing they had plenty of: ice.
We've accurately recreated the scenario down to the finest detail, allowing you to experience the desperation and the triumphant eureka moment that supposedly saved these Cossacks' skin. But did it really happen? A cannon and cannonballs made from ice? Before they build the ice cannon, they're going to test ice cannonballs with a real cannon.
We're starting with pure ice cannonballs and 8 ounces of black powder, the minimum amount we can use in the cannon.
Don't worry, comrade. They are only shooting ice. How bad could that hurt? We'll use it to chill our vodka.
Hey, come on, let's go dance into battle.
A pure ice cannonball and a ½ pound of black powder with a potential muzzle energy of 20,000 joules.
Eyes and ears?
Surely it doesn't stand a snowball's chance in hell of surviving.
Firing! 3,
Let alone doing any damage to our dancing dummy.
1.
That was awesome.
I am totally shocked. Not only did the pure ice cannonball come out completely intact, but it was traveling 1,000 feet per second, or 680 miles an hour.
So we've got our cannonball. Now he needs a cannon.
Everybody okay? Now, what I have here is a giant cardboard tube. This is the mold that we're gonna fill up with water and let it freeze so we can make our cannon. So I'm gonna build a couple of different sizes, and we're gonna see which one is the strongest to withstand the exploding black powder.
Before making the cannon barrel, they're going to make and test the breech. It's the explosive chamber at the base of the barrel that has to contain and channel the energy of the blast.
All right, so now that the tubes are filled up with water, we just need to let them freeze, and then we'll have our breeches.
And 1 week later, the cannon breeches are ready for a refrigerated trip to the bomb range.
God, it would suck if this thing fell.
We have a 4-inch wall, a 6-inch wall, and an 8-inch wall. We'll put our half-pound of black powder in there and see which one of these, if any, is able to survive the kinds of forces that are generated in a cannon.
First up is the 20-inch breech with 8-inch walls.
Don't let go. Oh my God! I don't know how these guys would have been able to actually maneuver an ice cannon.
All right, this is 20-inch diameter breech in 3, 2, 1.
Well, we just figured out a way to make hail instantly.
That means the Myth is on very thin ice. That was the biggest breach they have, so the only way forward is to lower the charge from 8 to 1.75 ounces.
All right, ice breech locked and loaded.
Once more onto the breach, comrades.
2, 1.
Now that was more impressive. But can a brand new breech contain 2 ounces?
2 ounces. In 3, 2, 1.
Oh. All right, looks like that was too much. I guess 1 3/4 ounces, that's the perfect amount.
Yeah, 2's just a bit too much. So, we've got the ball, we've got the amount of black powder, we've got the size of the breech. You know what that means?
Mega ice cannon making montage, that's what.
Look out, people! We have an ice cannon! Ice cannon! Ice cannon!
It's time to go to war.
So this sets up the criteria for our myth. Number 1, the ice cannon has to have sufficient range, meaning that it has to fire about 150 yards. Number 2, it has to cause significant damage.
This is a family show. This isn't quite from a family store. I might have to do a little bit of censoring.
And number 3, it has to be reusable. One time only doesn't work.
That's better.
If the ice cannon meets all 3 of these criteria, then we can call this myth plausible.
With its full majesty revealed,
Oh, it's beautiful.
It's an ice cannon.
there's no telling what this cannon can or can't do.
All right, we're wired and hot.
If you believe the myth, it's been 300 years since anyone's been crazy enough to try this completely insane cannon.
All right, this is ice cannon final experiment.
In 3, 2, 1.
And the cannon is still intact!
With a muzzle velocity of 200 miles an hour, the cannonball easily covered the 150 yards to the target zone.
Look at this. This is the ice cannonball. This is awesome. We took our first shot and we reached 2 of the parameters. 1, we made the distance, and our cannon is still in good condition. We can take another shot.
We just didn't get the damage that we were looking for, but for something that hasn't been done in 300 years, it's pretty good.
Yep, the team successfully fired a cannon made from nothing but water. But according to their strict criteria, they have to keep their celebrations on ice until they actually hit an enemy.
Well, I know the cannonball made it all the way to the guys, but I'm hoping this time it actually does some damage.
So with the same amount of black powder and a higher trajectory,
we are hot.
Will the ice-cold cannon this time be an ice-cold killer?
This is the ice cannon. In 3, 2, 1.
Wow!
The answer is no. Although the ball more than covered the distance, sailing over the heads of the targets, this myth blew up up the moment the cannon did.
I like this. I'm going to start crushing my ice this way.
For this myth to be plausible, we have to have damage and range and reusability all in one, and that just never happened.
For our next myth, we're going to icy Alaska to test a material invented back in World War II. Pykrete was a mixture of ice and wood pulp that was said to be so tough you could build a ship from it.
And supposedly it made a mix that was harder than concrete when it froze. And they were going to build an aircraft carrier out of it, but they never got around to it because the war ended.
So as far as we know, no one's ever tried to build a boat out of this stuff.
That's correct.
Until us.
Yeah.
They're starting at the beginning by making the stuff.
The traditional recipe, if there is such a thing, of Pykrete is that it should be 14% by weight of sawdust or wood pulp, and then 86%, of course, by weight of water.
It's such a simple recipe, there's not even a need for a montage. Jamie mixes the wood pulp and water, and that's it.
Aircraft carriers, huh? Who knew?
The Pykrete goes into the deep freeze to set. Once it's ready, they want to test how strong it is. First, they're going to see if this ice mix is bulletproof.
In 3, 2, 1.
There you go.
That's bulletproof. You weren't lying.
It's tough stuff.
For comparison, here's what a bullet does to pure ice.
We turned it into a snow cone.
And when they do a weight test,
This is killing me.
they find Pykrete is nearly 8 times stronger than regular ice.
Well, there you go.
I love this stuff.
But Jamie sees some room for improvement.
The reason the Pykrete is strong is because of the overlapping fibers of these wood chips. Now, the reason that it actually breaks under shock is that the fibers are not terribly long, and so they can break apart relatively quickly. So what other kind of cellulose products do we have that maybe would be superior?
And there's your answer. Newspaper. Lots of newspaper. He saturates it with water and then freezes it. And in a bench test, this super Pykrete turns out to be even stronger than regular Pykrete.
Dude, I'm gonna go out on a limb and say I like this material.
Okay.
I mean, I'm literally out on a limb.
Yeah, I got it.
They have the material. Now they're off to Alaska to attempt to fashion a speedboat from it.
In case you ever wanted to know how to build a boat out of frozen newspaper, this is how it works. First, you got to get a bunch of newspaper. Then you build a mold and you put the wet newspaper in the mold. And then you build an inner mold to hold the whole thing together. You take the whole affair, you put it in a freezer, and when it's frozen, you pull it out, and then you remove all the mold stuff. I'm so excited. You put an outboard motor on it. You take the whole thing down to the water, and out you sail away into the icy Alaskan Ocean. This is it. It's no return once we open the doors of this freezer. Are you ready?
Let's do it.
Okay.
Ba, ba, ba.
It's a tense process as the boys unpack their precious cargo for its first and possibly final voyage.
That's beautiful. That's the first time we've seen the outside of the mold.
I know.
At the water's edge, there's time for a few adjustments.
That's it. I don't want to catch your stash. You're good.
Okay.
Leaving Master Savage and Commander Hyneman ready to cast off. This frozen boat, dubbed Yesterday's News, has taken thousands of hours to make. And there's a chance with that large outboard motor attached, it'll be headed straight to Davy Jones' locker.
Okay, you and I are pushing. Ready?
Yeah.
Here we go. Ah! Look at that! Come on, baby. Do you realize what this is? The maiden voyage of Yesterday's News, ice and newspaper. Let's go.
Incredibly, their boat is staying afloat. But for our intrepid voyagers, that's not quite enough.
Dude, it's holding up. Let's take it up on a plane.
They want to really push the boat out at speed.
3 miles per hour. 10 miles per hour. 18 miles per hour. Yeah! Wow!
Keep an eye on the motor.
23 miles per hour. Holy crap!
Remarkably, even at a clip of 23 miles per hour, the frozen newspaper boat is holding fast.
I love this boat. Here, check it out. You knew I was gonna do this, right? I'm king of the world. Whoa. It's a little slippery.
But Adam's celebrations may be a little premature.
Dude, we've got a leak.
Why don't you fix it?
Yeah!
Although Adam's snap freezes the first leak with a blast of CO2,
we've got to keep it afloat.
He can't stem the tide.
The water's coming in quicker than that pump can push it out. I think we should head back into shore.
Okay, can I drive?
Yeah, go for it.
It's my last chance to drive a boat made out of frickin' ice.
After half an hour on the high seas, the guys head back to shore, with the boat starting to disintegrate.
We came to Alaska to make a boat out of ice and newspaper, and as far as I'm concerned, we knocked it out of the park.
They came, they froze, they conquered. But where does this leave the myth?
It looks so damn good, I swear people are gonna think we faked it, even though we didn't. I say that makes it plausible.
Yeah, but let's not forget that this myth is about the original Pykrete and about an aircraft carrier. And given that our super Pykrete darn near melted through in 20 minutes, if you're talking about an aircraft carrier that can go anywhere in the world, including tropical waters, it's going to be sloughing off huge chunks of this stuff as it goes along. That means it's just not at all practical.
How about plausible but ludicrous?
I'll buy that.
Good.
In our final myth, Carrie, Grant, and Tori are going to flush out the truth behind one of aviation's greatest mysteries.
What's the story?
It's the one where the pilot jettisons the contents of an airplane toilet, which promptly freezes at altitude and turns into a deadly projectile.
Ah, you're talking about the myth of blue ice.
Exactly.
According to the blue ice myth, a pilot supposedly jettisons the contents of a toilet's tank. And apparently at high altitudes, the sub-zero temperatures freeze the liquid into a foul, icy blue missile. First, Carrie wants to check if it's possible for a pilot to dump the contents of the latrine.
So you're an airplane technician. What do you think of our old blue ice myth?
Well, Carrie, as you can see from this cockpit, there are thousands of buttons and switches, of which none are labeled dump the toilet.
Which is bad news for the myth. But if the pilot can't jettison the John mid-flight, is there any way the liquid blue waste can escape?
Failure of components.
Turns out if there's something jammed in the toilet itself,
any hard object gets lodged up against this seal, it's going to leak.
Or if the seals of the access door on the fuselage fail, that could, in theory, create a blue ice buildup.
It's not likely. Is it possible? Absolutely. Multiple components that fail, leading to a problem.
But can they make the blue ice happen? Rather than test on a real aircraft, they're going to create their own aluminum aerodynamic shape to simulate the fuselage.
And what we have right here is our valve. This is what we're gonna have hooked up to a water tank, and we're gonna be doing two tests. One where we dump the water completely, and then one where there's a slow leak to find out, can you grow a chunk of ice on the side of a plane?
Forget taking this up to 30,000 feet. Instead, they're heading to a NASA wind tunnel.
Cool. Wow.
And if you thought you were MythBusters' biggest fan, check this fan out.
This is the heart of NASA's icing tunnel. It's powered by a 5,000 horsepower direct drive electric motor. The wind comes rushing through here, refrigerated to -20 degrees Fahrenheit.
And the way we're gonna test this is we're gonna stick our section of fuselage into their wind tunnel.
Does this mean I'm the R2-D2?
Oh boy. And recreate the same wind speeds and temperatures that you would find at altitude. Then we're gonna create a leak inside the valve. Let it sit there and see if those conditions will cause that blue liquid to form into a chunk of ice.
Maximum warp.
Ugh.
Sorry, I just made that really
We're trying to make
nine.
science cool, dude.
Here we go.
With the wind up to 290 miles an hour and the temperature dropped to minus 20 degrees Celsius,
Our model is holding together perfectly.
they're ready for the first test. A catastrophic failure with the hatch ripped off.
So this is full tanked up in 3, 2, 1, go! Wow! Oh my God!
Look at the stream!
Look at how fast it's coming out. That is awesome.
Impressive. But as soon as the liquid exits the aircraft, it's ripped away by the wind. And despite the bitterly cold air, it's unable to form the mythical slice of ice.
Okay, so we're ready to do our slow leak test.
Once again, the NASA technicians simulate the same high-altitude conditions, then sabotage the plumbing for the drip test. And once the leak is leaking,
Oh, let it go!
Look how quick the ice is building up!
they get instant results.
Dude, this is looking great, and it's blue!
That is fantastic. It hasn't even been 2 minutes yet.
Oh my gosh, that is incredible!
The liquid moving over the surface of the aircraft is protected from the extreme wind speeds by what's called a boundary layer.
What that means is that not all the air traveling over the airplane goes at the same rate. In certain areas, it actually travels a lot slower.
Which creates a protective cushion where ice crystals can form.
But let's see if we can get it to fall off. Let's pretend like it's at its final descent, temperatures are rising. Maybe we can get it to break off and find out exactly what happens when it does.
Perfect.
All right, start warming it up.
And as it turns out, when the wind tunnel conditions match those of an altitude of 12,000 feet,
Minus 7 degrees.
we have liftoff.
That thing blew up in one giant chunk. Wow, dude, that was perfect. That is unbelievable. That is solid ice. And it happened so quickly.
And it came off in one giant chunk.
This myth is starting to look very, very believable.
Yeah, but you know what the next step is? What happens to the ice after it falls off?
I can't believe it.
So could this ice survive a fall to the ground with enough mass to damage something or someone? To find out, Carrie's made a block of ice the same size. She's going to drop it from 12,000 feet and attempt to follow it down.
All I gotta do is look at the ice. One job.
Yeah, I got them. They're approaching the drop zone. Okay, the ice is away.
Ah, so are they. Look, it's standing in one chunk.
Dude, that's crazy.
But will it stay that way as they enter the final few thousand feet of descent?
Whoa! Do you see the size of that impact?
And did you see it stayed in one chunk?
I saw the ice go down, and I swear I saw it land.
You made it!
Wow. Nice!
That is still a chunk of ice.
Check it out. It dug itself into the ground.
Wow, that is a serious impact.
This is the size of the block of ice that we threw out of our plane, which is very similar to the size of the chunk of ice that we formed in our wind tunnel at NASA that fell off. That block of ice reached terminal velocity very quickly, and it left a sizable impact crater. And what's more, it stayed pretty much intact all the way down to impact. Totally confirmed.
I agree 100%.
Don't try anything you're about to see at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem.
Hot set.
On this episode, shocking developments
Is that a big enough lightning bolt for you?
with 3 myths about electrocution. And later,
This is awesome!
the team gets rough and ready
We got ourselves a big one!
as they ask fact or friction.
Go!
But first is a phone lightning combo potentially fatal.
Were you ever told to stay off the phone in a lightning storm?
Yes, actually, we were told to stay off the phone, out of the shower, don't go under a tree, don't go out in the middle of a field with a large metal pole.
Yeah, that would be bad. Well, all the ones that occur inside a house that we've heard, from staying off the phone to staying out of the shower, we're going to test on this myth. Should you be on the phone in a lightning storm?
Here's the theory. Lightning strikes your house, or the phone or power cables leading to it, and it looks for the quickest way to the earth. Usually that's through a ground wire. But failing that, conductive wiring or metal plumbing is the fastest route. And if you happen to be hooked up to that, but can it actually happen? To find out, the MythBusters need to build a house and zap it with some serious voltage. You know the drill. Montage music, close up, wide action shot. And hey presto, the plumbing's done.
Oh, yeah. That works.
Yeah.
And with the wiring hooked up, we're live.
Our little shotgun shack is all ready to go. We've got the computer set up, we've got 2 kinds of phones, we've got a television, we've got wall switches, plugs, junction boxes, everything to code, plus a shower that will be fully grounded. And we're ready to shoot lightning bolts at this thing. I mean, I've been ready to shoot lightning bolts at it from the beginning, but now we're officially ready.
But is the testing facility at Pacific Gas and Electricity ready for the MythBusters?
What are your plans, my master?
We're going to take over the world.
Oh, yes. Yes.
Actually, no. They're just going to wreck some stuff like they usually do. Adam's Playhouse and its ballistics gel resident are being brought directly into the target zone of a device capable of unleashing huge jolts of electricity.
This electrode will give us about 200,000 volts. Now that's enough to make it jump across the 2 feet here, through these wires, down either into the electrical box here or through the phone lines.
Our test subject here, Chip, is set up with a phone strapped to his ear. We've also taped in some gunpowder in a little paper baggie here. And finally, we have our MythBusters patented heart paddle current meter setup, where we've got 2 copper paddles set up right where the heart would be. And if we read more than 6 milliamps of current across these lines, we know we've got a dead guy.
Here's how this will work. Electricity can jump through the air. Every 10,000 volts adds about 1 centimeter to the distance.
Closing 200 over 5.
With the electrode in this position, when the charge reaches between 200,000 and 300,000 volts, it will zap across to the house. Real lightning is around 100 million volts. But as the charge builds, they're still anticipating a very large shock. That was 300,000 volts straight into the house's wiring. It generates an electromagnetic pulse strong enough to throw our remote camera out of focus.
No smoking, no sparks.
No smoke, no sparks from the phone.
Incredibly, Chip's phone call is uninterrupted.
Well, everything seems just like we left it. No problem, no reaction whatsoever. I don't think he got any current.
It appears the jolt exited straight out of the ground wire, standard to most homes. But remember, this shock is just a fraction of real lightning's power. So Adam will grease the tracks a little by cutting some of the grounds to the electrical wiring system to try to guide the charge towards the telephone cord.
580, 96, 100 kV.
House is hot. He's going up in voltage.
150,000. 200,000.
200,000.
220, 230.
That actually worked.
That was beautiful.
The lightning arced from the mouthpiece into Chip's head, setting off Jamie's charge. The jolt finding its way with disturbing accuracy.
That was awesome.
Are we clear?
Do you want us to put out the fire?
I'll just blow it out. So that's it right there as far as I'm concerned. You know, this is a standard phone. It arced through the mouthpiece of the phone. That's a lot of current to go through gel. So,
well, we can check and see what kind of current it is.
Yeah.
Remember, 6 milliamps across Chip's hard paddles would indicate a fatal shock. But there's a problem. The meter's blown.
We had it set on the 40 milliamp setting, which is more than enough to kill you. If it fried the fuse of this meter, that was a lot more than 40 milliamps going through it, and that's a dead guy.
Works for me.
Lightning fatality stats back up the result. About 100 Americans die of lightning strike every year, and around 2% of those were talking on the phone. Chip's shocking phone call is about to be followed by a particularly spine-tingling shower.
There we go. We have grounded plumbing, which is running near electrical wire. We're hoping for a short between the electrical wire and the plumbing. And then our guy here, I've put a ground wire directly into him. This is basically equivalent to if you're standing in the shower and you're standing on the drain, which is also grounded.
They're ready to go. Ramp it up.
140 kV.
The storm clouds gather.
It's a lot.
We're up to 243, almost 250 kV.
Not since Alfred Hitchcock's Psycho
I hear it.
has a shower scene held such riveting suspense.
Did you see that?
Yes, I did.
Only the MythBusters could manage to start a fire in the shower.
There you go. Here.
So Chip is saved from the fire. But was he already fried? The meter is inconclusive again. The electromagnetic pulse that messed with our camera could be frying it too. Even so, there seems little doubt you don't want to be in the shower during a storm. Or on a landline phone.
Arcs the size of boa constrictors that are kind of like wiggling right next to you. You kind of get the hint that there's going to be a problem there somewhere, don't you?
Exactly. I'm looking at phone confirmed, shower plausible.
I'd say that's a safe bet.
For our next myth, we're investigating a more unusual, but just as shocking scenario. Being electrocuted while using a railway track as a toilet.
Oh, this is the one guy found himself late at night in a train yard, peed on the third rail, the electrified rail, got electrocuted and died?
That's the one.
Some subway systems are powered by an electrified rail on the track. A steel paddle slides along the top of that third rail, arcing as it draws current. But could peeing on the third rail really cause a fatal electrocution? To test this myth, they'll need to make a stunt dummy with the same electrical properties as a human body. They'll have to come up with a system to make it pee and electrify a track. After making a mold out of the same material used for soda bottles, Adam plans to fill the dummy with ballistics gel.
He's looking pretty healthy. I've always wanted my own full-sized, visible human.
And they now need to get their hands on the #1 ingredient in this test.
Well, here on MythBusters, it seems we'll do just about anything for science. Oh, it's warm.
To work out how much current will zap a third rail victim, they first need to know the electrical resistance of urine.
So it's about 10,000 ohms, which is just what we expected.
And they know a subway train runs on about 650 volts. A famous electrical formula called Ohm's law says the current equals voltage divided by resistance. So 650 volts passing through urine at 10,000 ohms resistance means there'll be a current of 65 milliamps, enough to give you a heart attack. So in theory at least, urine can carry a shock big enough to kill you. But they're a long way from fully testing this myth yet. The next hurdle? Crafting a bionic bladder.
Personally, I don't let gravity do my trick. You know, there's some pressure involved. So the question is, how to add pressure to the system?
When in doubt, break out the party box, where Adam realizes what's needed is a good old whoopee cushion.
Yeah, that's holding pressure.
But of course, that's only half the equipment.
Yeah, I've gone as close as I can to the real thing.
You got to fill it up?
Yeah. Are you ready?
Ready.
Commencing. Wee-wee.
Gee whiz.
Looks like a pretty convincing stream to me.
Yeah.
Dr. Frankenstream, at his finest creation, let's call him Baron von Bladder, arrive at the rail yard test site. The plan is to wire him up so that if the myth is true, current will run from the third rail up his urine stream and trigger an electric release switch, knocking him over backwards. There's no third rail here, so they'll build their own, attaching a section of track to a 650-volt transformer.
It's a dry day. The ground is dry. Our subject is wearing normal rubber-soled shoes. He's having a wee on the rail. There's no wires around him. We'll electrify the rail, and we'll see what happens to him.
The guys will stand on a rubber mat to insulate them. No such protection for Baron von Bladder, who is busting to go. If his stream triggers the electric release and he topples back, that'll mean he's had a fatal shock.
Let's make the set hot.
Hot set.
3, 2, 1.
No stage fright for von Bladder, and his aim is perfect. But the release isn't triggered.
That's exactly what I expected. He's got rubber-soled shoes. He's on dry ground. There's no way a mere 600 volts is going to arc through his shoes.
Maybe it was a rainy night. The Baron's shoes were wet. That would help complete the circuit with the ground.
Bladder recharging.
Hot set.
We're electrified. Here we go. Nothing. Not a thing.
Damn.
He needs to see a doctor. Set is cool. Okay.
What about barefoot?
Okay, there's 2.
Baron von Bladder must have had quite the evening.
Stumbling around the train yard late at night, looking for a place to pee, barefoot. All right, are we good?
Hot set.
All right, here we go. Nope. Nope, there's no connection going.
Checking the high-speed camera, they see the problem. By the time the urine reaches the rail, it's broken into separate drops. It needs to be solid to carry a current.
The only thing we have left is to try a larger stream of urine. You know, maybe that'll be more likely to create a continuous connection there with the ground.
For Von Blatter, that means a substantial upgrade.
That's what we started out with, and that's where we're going.
And since the Baron's barefoot, drunk, stumbling around a rail yard late at night, why not give him something to steady himself? They move the rail closer.
I always like to hold on tight to whatever I'm sitting on. The bladder is full. The rail is set.
Powering up.
Powering up.
If this surreal setup doesn't complete the circuit, trigger the release, and blow the Baron backwards, the myth will be history.
All right. And 3, 2, 1. Hey! It worked.
Yeah, at 6 inches away from the
It just
rail.
goes to show, do not grab the third rail with both hands and on it from 3 inches away.
So, what's the verdict?
Watching it break up in every stream that we've photographed, you know, just doesn't look like you could make a solid connection.
I'd say that's a myth busted.
Not that I'd be peeing on the third rail anytime soon. Hey! Ah!
For our next myth, Adam and Jamie have heard that foreign spy agencies may be creating a water-based stun gun. But could it be true?
A water-based stun gun?
Exactly. And it's our job to determine whether it's feasible or not.
Step 1, determine how a regular stun gun operates.
Dude, that is harsh.
I hit him in the face.
It turns out that a regular electric stun gun has wires that deliver a massive 50,000 volts through 2 of these barbed spikes. On contact with the bad guy, the volts instantly drop down to 5,000, causing neuromuscular incapacitation.
But can an electrified water stream do a better job? Well, just in time, the deliveries arrive by mail.
So I've got an arm full of all the latest water shooting toys. We're gonna shoot them on high-speed camera and see which ones give us the flow we like.
Having learned their lesson from the third rail story, they're looking for an unbroken stream to carry the electricity.
1, 2, 3.
You know, it looks like it's breaking up after just a couple feet or so.
And after trying a whole arsenal, there's only one gun left.
It doesn't get any simpler than that. It's just a big tube.
Yeah.
All right.
Let's see what it does.
All right, I'm ready. That is by far the best one we've tried yet.
At last, the high speed gives it the thumbs up. A 15-foot, totally continuous laminar flow.
Now the question is, can we get electricity into this stream? Can we get it to a person? And when we do, is it a reasonable stun gun?
For double the power, Jamie takes one water pistol and connects it to another.
To this, we're going to attach a stun gun to supply the electricity.
Pull the trigger of this electric device right here. Electricity will travel through these 2 wires out to electrodes that are in the water stream. And when those water streams hit your suspect, ho-ho, they are yours, gift wrapped.
Remember, they want to stun, not kill, their target. They set up a testing area with a ballistics gel dummy and an oscilloscope reader.
We'll know if the signal is being transferred to the target via the water by what we see on the electrical screen.
Time to test their AquaZap from 5 feet away.
Go for it.
But unfortunately, it registers a lethal charge.
It's not where you want to be if you want to stun someone.
It's where you want to be if you want to
potentially kill them.
Oh, okay.
Yeah.
And each subsequent test produces a totally different result, from no stun to death.
At this point, what I'm seeing is a test where we're not getting a lot of good data because we have so many variables.
To minimize the variables, they've ditched the ballistics gel dummy
Beauty.
For a leg of lamb. And to try to better control the stream, they're going to guide it through plastic tubes.
Testing the AquaZap is actually quite difficult because it's hard to control where the streams of water are going. So we're going to actually run water through tubes, and the plastic tubes will act as insulation. We should get more reliable results if we do that.
Next, they stick electrodes from the electric stun gun into the plastic tubes and poke the tubes into the lamb.
This is very Frankenstein.
Firing.
And at point-blank range, it works.
Awesome.
Firing at 2 feet.
But as soon as they start moving back,
4 feet.
4 feet.
The effectiveness plummets.
Every time we move a foot out, it's dropping.
Firing 8 feet.
What we're seeing here has everything to do with a property of resistance, of a medium's resistance to electricity. Wire's got a very low resistance. It loves electricity. Water, it's got a much higher resistance, and it increases significantly however much more water you've got to move through, which means every time we move 1 foot further away from our target, the water's applying more resistance and less electricity is getting to the target.
I think it's starting to break down because look at the current here.
It's not looking very good for the AquaZap here. And you've got a super limited range this thing works from, and that doesn't make it a very effective weapon.
Okay, so the AquaZap is DOA. I'm kind of disappointed, though. I had my heart set on, like, firing lightning bolts.
Funny you should say that. Because this is MythBusters, sometimes you get exactly what your heart desires.
Now there's a lightning bolt generator of our dreams.
So do you mind if we hook that big beastie up to my little squirt gun here and see what happens?
We'll give it our best shot.
Awesome.
Using a colossal Tesla coil to subdue a fugitive might be overkill, but that's never stopped us before.
Is that a big enough lightning bolt for you?
Yeah.
Let's zap some bad guys.
Okay.
Jamie will be up top in a cocoon basket. Using the AquaZap, he'll fire a stream straight at the ballistics gel perpetrator. Can the 1,000,000-volt jolt juice up the stream and blast the bad guy?
This is my new favorite toy.
Jamie takes aim.
At speed.
And fires.
We hit him! Whoa, yeah! You got him!
That was a nice shot. I could see right down the lightning bolt right to his head.
But as the smell of charred ballistics gel fills the air, Adam acknowledges the elephant in the room.
Here's what I've concluded. You've got a perp, he's causing trouble, you want to subdue him. So, you get a crane. You crane in your 18-foot high-tested coil, you bring a ladder over, you climb inside it, get a water pistol, load it up, squirt it at the perpetrator, and subdue him. In other words, it seems totally impractical.
So far, we've been zapped and fried.
Done! He's out! Whoa!
Now it's time for some myths that are stranger than friction.
Go!
For our first friction myth,
all right,
Adam and Jamie are painstakingly interleaving 2 phone books.
We've just passed 500 pages total.
We're cruising.
Each with 800 pages.
Does this remind you of when you used to count money for the mob?
I was a hitman. I wasn't a money counter.
Once they're done, they're going to test the myth that friction between the pages will make the books totally inseparable.
What I've got here is a lesson in friction. While this might look like 2 800-page phone books, Jamie and I have interleaved them, and apparently almost nothing will rent these 2 things asunder. And we're going to see if that's true.
It's really quite amazing. I mean, when you tug on these, it's like they're glued together, but they're not. It can only be the friction of each page where it contacts the next one, and times 1,000 or so, it adds up to a lot.
Friction can be defined as the force resisting the relative motion of 2 surfaces. For example, the pages of a phone book. Static friction is the force keeping 2 stationary objects from moving. And kinetic friction occurs when 2 objects that are already moving rub up against each other. It's very hard to believe that friction alone can hold two books together with such force. If they want to stand a chance at pulling them apart, they need strong handles attached to the book's spines. But these don't add strength, just something to grip onto for their first test.
All right, you want to do some tug of war?
Okay.
Oh, check out my guns. You ready?
Here we go.
Remarkably, the books take the strain.
Oh, I believe I'm winning.
Equally matched in weight, it's actually Adam's superior foot friction, AKA traction, that is the ultimate decider.
Good job. The phone book's still together, though.
While Jamie's ego is torn, the phone books ain't.
This puppy didn't creak, didn't move, didn't budge. We're gonna need some more help. Let's get everyone in the building on this.
Okay.
Are you ready to fight the Spartans?
With 9 muscled warriors and Adam split into 2 teams of 5.
1, 2, 3, like that.
We're about to see exactly what these phone books are made of.
Ball! Lunge! Lunge! Come on, they're beating us, you pansies! Move!
Okay.
So far, it's phone books 1, everybody else 0. 5 people on 5 people tug of war, generating almost 2,100 pounds of force, the weight of a small car, and the phone books are steadfastly refusing to be separated.
And even with all 10 tuggers in one mighty team, incredibly,
2, 3,
the books
lunge!
refuse to part.
Tug!
All right, what do we get? We got up to 4,000 pounds.
You guys called it up. Called up the beast.
And the beast was beaten by the books.
Dude, this thing is a behemoth. What are we gonna pull it with now?
Rental cars.
I wish I could say they used the phone book to find a rental company and rent these cars,
I love full insurance!
but we all know they use the internet like everyone else these days. Though phone books definitely still have their place. And this is it.
I'm ready. Are you ready?
Yeah, I'm ready. Let's do it.
Cabled between 2 sedans, driven by 2 men hell-bent on tearing their interlaced pages apart.
I'm starting to spin.
Millennials, good luck doing this with your newfangled internet.
Come on, spin some more.
Unbelievably, with the force gauge peaking at 4,800 pounds, the phone books, unlike the car's tires, hold firm.
Still intact. I think the phone book's feeling pretty self-satisfied, but we're not done by a long shot.
And when he says long shot, he means a really long shot from a really long barrel attached to a really big tank. 2 big tanks, to be exact.
This is awesome! It's like some sort of a sideshow with me.
You got a phone book for me?
Right here.
To handle this military-grade test, they'll need a military-grade clamp.
This is an opportunity to not mess around.
Nice.
If these clamps give way, I'll eat my beret.
I'd pay money to see that.
There you go.
But this tank test should be quite the spectacle, too.
I don't know about you, but I think we're ready to start stretching. Behind me is 30 tons of military steel. Are they gonna separate the phone books? At this point, I have no idea. But I do know that something is gonna happen.
When 2 15-ton tanks go up against 2 phone books held together by nothing but friction, something's got to give.
Okay, go ahead and pull slack.
Engaging a combined 615 horsepower, the mighty military machines slowly begin to move in opposite directions. And the force gauge climbs quickly.
There it went.
Separated, it worked.
The yanking tanks finally win the tug of war.
Darn.
You wanted to see some metal breaking?
Yeah, well, I wanted to see these things spin, burn rubber.
Unlike the rental cars, the tank's own friction, created by their tracks on the ground, trumped the phone books.
8,000 pounds of force is what it took.
So it turns out that interlaced phone books are not, in fact, indestructible. You just have to have a couple of tanks hanging around to do it.
In our next story, Carrie, Grant, and Tori are fired up to test a fishy tank.
All right, so this next myth is an old fishing myth, and it's not about the big one that got away. This one is about flaming reels.
Okay, flaming reels, you're gonna have to give me more than that.
All right, now as any fisherman knows, once the fish is on the line, all it wants to do is get away.
All right, meaning it takes off in the opposite direction.
Exactly, and as it's taking off, it's pulling a lot of line off that reel.
Okay, I see where you're going with this. If the line's coming off fast enough, it generates friction, which creates heat.
And if you generate enough heat, it could burst into flame, hence the name flaming reel.
And that's the myth. Can a fish cause a reel to catch on fire?
This myth is all about the heat generated by friction as the reel spins. Friction creates heat because it causes the molecules on surfaces rubbing together to move faster and therefore have more energy. But before they get to catching fish, they'll figure out what equipment will be best at catching fire.
All right, let's begin with the 80-pound monofilament test.
Okay. All right, hold on. We're missing one thing. just in case this myth is true, we just gotta be prepared.
All right, let's do it.
With the safety set, a motor pulls the 400 yards of line at 20 miles an hour.
All right, we're at maximum speed.
Before Tori engages the drag, a kind of braking system.
All right, going to full drag.
Which will take the friction up to the max.
Stop. Okay, we're at the end of our line.
All right, what do you got, Byron?
Oh, look at that, thing's glowing.
Looks like we are maxing out at 105 degrees.
After testing 3 other lines, there's a clear winner, braided polyethylene, peaking at 158 degrees.
I think we have a winner.
That's pretty hot.
They experiment with a variety of reels until settling on one with a star drag. Because after rapidly reaching 180 degrees, this happens.
Getting red hot.
We're starting to smoke. It's smoking.
Oh my God.
Keep going. We got smoke.
Wow. 187.
Oh my God. Hey, get the fire extinguisher ready.
223.
That is incredible.
230.
So we've completed our reel comparison, and this is the winner. The limiting factor, though, in our tests was the amount of speed that we could get pulling the line off and the amount of line we had. Now what we've got to do is find some way to get more line off this spool a lot faster.
And to do that, take one marlin, mount it on a go-kart, and head out to Alameda Runway.
We're here.
I'll drop the anchor.
Carrie's job is to drive the go-kart as fast as a sailfish. At 68 miles per hour, they're the fastest fish on Earth.
Now, why have I been chosen for this task? Well, it turns out that the weight of the car plus my weight is about the same weight as a big old sailfish.
She drives like a maniac. So Carrie is hooked. She's gonna take off down the runway going 68 miles an hour. At that point, I'm gonna start adding drag to the reel. I don't know if this thing's gonna catch on fire, but this fish is going 3 times as fast as we did in the shop. This thing's definitely gonna smoke.
Go for it, Carrie!
Will Carrie's desperate dash for freedom be enough to get flames flying off the reel? Take 2.
That is a fast fish. We got ourselves a big one. Whoa!
66 degrees.
Look at how fast it's going.
78. 86 degrees.
Oh my gosh.
90 degrees.
We're already smoking.
100 degrees. Oh my God.
That is a big fish. Look at all the oil pouring out of this thing right now.
The spool's are spluttering, and the temperatures hit 200 degrees.
Listen to that reel spin!
But before it can rise anymore, Carrie's reached the end of the 1,000-yard line.
Wow.
You hear it sizzling?
Oh, gee.
That thing was like, whee! And then the smoke started pouring out, and then the oil was like, and then it started burning. It was like, and we got up to 205 degrees. Still, there was no flames. Right now, it is not looking good for this myth.
They've cooked the washers on that reel, so they load up another. This time with over a mile of line.
Go fish! All right, apply the drag.
As Carrie cruises at 70 miles an hour, the temperature is soaring.
480 degrees. It's white hot. 500 degrees. We got nothing but smoke pouring out. 530 degrees.
Serious friction is making the temperature skyrocket.
Man, that's 530 degrees.
But although they say there's no smoke without fire, in this case, they're wrong. Carrie reaches the end of the line, and no flames.
Well, we got a lot of smoke, but still no fire.
No fire?
No fire at all.
But like you, they want to see flames. So they're upping the ante. This time with a road racing sidecar capable of 200 miles per hour. And while the test is going, they'll spray on highly flammable ether as a lubricant.
Is the shark ready? Yeah. All right, here we go. Sharks away in 3, 2, 1, go!
All right, putting the drag on.
We're up to 120, 245, 300.
Get it on the drag.
We're up to 470, 500, 600.
Oh, my
700. Oh, my God. We're up to 700 degrees. Whoa! Whoa! Woohoo!
But when the temperature passes 700,
Whoa! Oh, this is ridiculous.
the line melts but doesn't ignite.
There is no way this myth is true, but we need to see this thing catch on fire.
Without doubt, they got the hottest reel possible. But that heat within the reel was still not enough to ignite their fuel on the line. So as a last resort, Tori adds one final ingredient, a 1,200-degree flame. And
Ah! Finally! You know how long I've been waiting to see a flaming reel?
Now this is MythBusters Fishing.
thanks to a little cheating, they got the reel burning. But this myth is also up in flames.
This one is busted on every level.
While Carrie, Grant, and Tori were trying to increase friction, in our final friction myth, Adam and Jamie will be trying to reduce it as they test if the tablecloth whip can be performed on a banquet table using a motorcycle, like in a famous viral video. They'll start with a more intimate table setting to understand the science first.
Dude, are you ready?
I'm all ready.
Well, there's a vote of confidence.
Tablecloth pull in 3, 2, 1.
Oh! That wasn't bad for a first try.
That was not bad for a first try.
Adam's clearly got a fraction too much friction between the tablecloth and the object on the table. So he's going to refine his technique. To monitor how much the wine moves, he makes a pointer.
You ready?
I'm ready.
Okay, here we go. In 3, 2, 1.
Same thing.
Maybe it's the way I'm pulling.
Try after try, fail after fail. Until eventually, Adam gets the technique right.
Hey! All right, now what did I do right?
This is a classic battle between inertia, the tendency of objects at rest to stay at rest, and friction, the force that creates drag on the base of the bottle. If the inertia is greater than the friction, Adam's able to pull the trick and the tablecloth off.
7/16.
To reduce friction even more, Adam tries a range of fabrics.
This one's no good. I mean, took me wrong. It's lovely, but it's no good for this trick.
It turns out the lightweight
3,
satin
2, 1
works best.
Wow.
Yeah.
That works.
I know.
And they're ready for the banquet hall, where it'll be Jamie on his supercharged sports bike who'll be attempting this ultimate party trick.
If we can't pull this off, it won't be because the bike's not fast enough.
Using the lightweight satin tablecloth, the table is laid for a banquet that could go down in history, or more likely, the recycling bin.
It's all set up. You ready to ruin Christmas dinner?
I can't wait.
Uncle Jamie always does that. Get started.
I've got a very bad feeling about this.
Monster tablecloth pull, go! Well, some stuff stayed on the table.
Abracadabra, this ain't. Despite Jamie gunning the superbike to 50 miles an hour, it wasn't enough to overcome the friction of 24 table settings.
Oops.
This is why we can't have nice things.
I guess so.
What a horror show.
I left some of them on the table.
That's exactly what I said. The glass is half full.
3 things are clear. 1, next time they need some slack in the line, so that the tablecloth isn't pulled until Jamie is at maximum speed. 2, they need to go way faster. And 3, they need to get away from this mess as soon as possible before someone asks them to clean it up. Alameda Naval Base has a quarter-mile runway.
Show off!
Where Jamie can easily hit the speed they need.
97, ladies and gentlemen. 200 yards will be the length of the rope we attached between Jamie's motorcycle and our tablecloth.
They've reduced the weight of the table setting, and they've coiled 200 yards of slack so that the yank doesn't happen until Jamie's at top speed.
You ready to do this?
Yep.
Let's do it. All right, here we go. Possibly the world's biggest tablecloth pull in 3, 2, 1, go! Well, that is certainly as good as it gets. Plate's still rolling.
They almost pulled that one off. But even a perfect run at 100 miles an hour still wasn't enough to leave the table intact.
Everything slid, especially on the front half. We lost a few place settings. Most everything is still standing, but honestly, you know what I'm thinking?
It's busted.
Yeah, totally busted.
The friction is too much. But on MythBusters, knowing when to quit isn't our strong point. They're going back to the banquet hall to attempt to fake the whole thing.
What's different about this setup than its predecessor? Actually, quite a lot. I started out by treating the entire tablecloth with a dry lubricant made for sailboat sails, and that should actually reduce its coefficient of friction. But most importantly, I then laid down on top of the tablecloth a sheet of plastic, 24 feet long, and mounted at the non-motorcycle end of the table. And then we set the table as normal. What this means is that between all the place settings on the tablecloth is a thin membrane on which everything sits. So the tablecloth should, in theory, slip out easy as you please without disturbing anything on the table.
There's a lot resting on this thin layer of plastic, 24 table settings to be exact, and the MythBusters' reputations as masters of special effects.
Boy, I hope this works.
It'll work.
This is tablecloth pull, the cheat. 3, 2, 1, go!
This is it. Will they finally be able to overcome friction and make the tablecloth disappear?
And that's how it's done. Congratulations, we did it.
It looks fantastic.
Yeah, we disturbed 1/4, and that was it.
I'll settle for that.
So will I.
The only way to pull this off is with friction-free fakery, which means
it's busted.
I totally agree. It's busted. Let's get out of here.
Don't try this at home. Whoa!
Well, there's your problem.
in this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode,
Surf's up, dude.
the MythBusters blast off to the outer reaches of rocket science.
I'm gonna use poop.
Then they train their sights
Pretty sure I curved that one.
on myths about guns and ballistics.
That's pretty much it. That's just wrong.
First up, the countdown is on to a steamy blast-off.
We have a plumbing myth. Picture an old house, and in that house is an old hot water heater. The hot water heater is neglected so badly that it blows up like a rocket shooting up through the roof of the house.
Gets me all steamed up just thinking about it.
The humble water heater is an often overlooked and poorly maintained appliance. According to the myth, a neglected old boiler can overheat and build up so much pressure that it becomes a rocket capable of launching right through the roof and high into the sky. To find out how good water heaters go bad, Jamie and Adam head out to the wide open spaces of Alameda Naval Base.
So the very first thing we're gonna do is make this bunker into a safe haven for all the people on the crew to be able to monitor the blast. And the second thing we're gonna do is make a blast for all the people to monitor.
In other words, they're gonna blow stuff up for science, but without explosives. Just water plus heat and pressure. First, they need to make this new 30-gallon water heater mimic an old and poorly maintained one by disabling its fail-safe devices.
The electronic cutoff switches and thermostats, gone. The temperature and pressure valve, gone.
But this myth requires actual liftoff. So will the heater go up or just blow up?
Now, the difference between a rocket and a bomb releases all of its energy in every direction at once, and a rocket releases all of its energy over a little bit longer period of time in one single direction. And that's what we're looking for here.
The water heater is turned on and the team retreats to the safety of the bunker, from where they'll monitor temperature and pressure.
Okay, now we're at 160 PSI. It's officially a no-go zone.
With the safety features, the heater would automatically cut off at 140 degrees Fahrenheit and 150 PSI. Without them,
The suspense is killing me.
well, we're about to find out. Liftoff.
Wow!
That was at about 350 PSI.
The water heater launches so high into the air, you could almost run a bath before it comes back down.
Wow, no, it just came down. There it is. It came down like 40 seconds later.
This was a really serious explosion. I mean, even though this is just a water heater, you would be in danger of shrapnel hitting you. You could get severe burns from the steam. And not only that, the shock wave was really significant. I mean, the whole area was reverberating.
Dangers aside, it's a thing of rare beauty.
Oh, that's one of my favorite booms we've ever done.
As 30 gallons of highly pressurized, superheated water turns to 30,000 gallons of steam in an instant.
Wow.
The boosters were separated.
Yeah, exactly.
But the pressure's still on. Before they can really blow the lid off this myth, it literally has to go through the roof.
Do we have a house?
Yeah, we got to build one. You ready?
Damn.
For the grand finale,
Bada bing, bada boom.
the guys are going with a family-sized 50-gallon water heater. Safety features removed. The house is modest. Just one bathroom with water heater.
Hi, everybody. Welcome to the MythBusters Clubhouse.
But the all-important roof is made to Californian building standards. So it'll be no pushover. Color scheme, optional. Right, let's get this sucker started. They turn on the heater, hunker down, and wait.
Okay, everybody, we're at 300 PSI. That's twice the tank rating. Keep your eyes peeled, because it'll go any minute now.
As the pressure inside the tank mounts, so does Jamie and Adam's heart rate.
315 PSI.
Oh, this is killing me.
320.
This kind of stress on a regular basis can't be good for you.
No, it's shortening our lifespan.
We're going to make it to 350.
And... so long, roof. The water heater flies so high, you could check yourself into a hotel before it returns to Earth.
Look at the house. What house? I don't see a house. I don't know what you're talking about.
NASA, eat your heart out.
Oh.
I gotta say, it's more interesting than an actual explosive explosion because the steam is just erupting everywhere and completely disintegrating. It's different. It's more elegant.
No black powder, no rocket fuel, just superheated water and pressure. So the moral of the myth is, don't take your water heater for granted, or there may not be a happy ending. Rockets and danger go hand in hand, but this next myth is asking for trouble.
A California surfer moves to the Midwest and gets a little frustrated.
Oh, let me guess. No waves, dude.
Exactly. But instead of getting bummed out, he decides to make a rocket-powered surfboard.
The story goes that a souped-up surfboard gave its rider a 20-mile-per-hour ride for 30 nail-biting seconds. So will this rad myth catch a break or simply wipe out?
You guys ready to rock it?
Yeah, MythBuster style.
This is our rocket surfboard. Just like in the myth, one big rocket.
Surf's up, dude.
This could get choppy, so Buster will be our bodacious board rider.
Ouchie.
That's right, it's built for comfort.
Behind him, he's rocking a powerful Cicerone K-Rocket, readily available in any reputable hobby store. A guide rail will keep the board stable for the first 20 feet. After that, the dummy's surfing solo.
All right, we're good. This is Rocket Surfer with one big rocket. Here we go. In 3, 2, 1.
That looked a little dangerous.
That is a lot of thrust. Yeah, that was a crazy flip.
Houston, we have 3 main problems. There's way too much initial thrust for any rider to handle. The board is unstable. And the ride was nowhere near the myth's 30 seconds.
Don't die on me.
Time for Plan B.
Now, it's obvious the single rocket is just too powerful and is not long enough to get the ride that we need. So we're gonna have to come up with a multiple rocket system. This is gonna be tricky. But I'll tell you what, if it's safe, I'm gonna ask the producers if I can go for a ride.
Here's a disturbing glimpse into Tori's mind. But he's nothing if not game. If the Italian stallion is going to ride the rocket board,
what could possibly go wrong?
They first need to find out the maximum thrust he can handle at launch without falling over.
Tori acceleration at 60% capacity in 3, 2, 1.
Holy!
And there's the sweet spot.
So this right here is the information from the data logger. You can see here the peak is at 0.8 Gs. So what this means is that none of our rocket tests should exceed 0.8 Gs. That way, we know that he'll be able to hang on.
To limit the Gs, the plan is to use several banks of model rockets and a series of ignitions. And with the board ready for testing, it's off to Treasure Island.
Why does this thing weigh so much?
Because you're a fat guy.
Tori plus board weighs 180 pounds, and each model rocket gives 2 pounds of thrust. So a bank of 20 should get them to the required 20 miles per hour.
All right, the rockets are wired.
But will it pack a thrust below that critical 0.8 Gs?
All right, this is acceleration test for Rocket Surfer. All right, here we go in 3, 2, 1, firing. Awesome! Oh my gosh, that was beautiful.
Sure was. A controlled acceleration with a peak velocity close to 20 miles per hour and at 0.6 Gs, just inside their G-force envelope. Now for stage 2, a second bank of rockets with a timed fuse to hopefully prolong the ride.
All right, here we go. This is 2-stage rocket on the surfboard. In 3, 2, 1, fire it.
That's the sound of happy rocket scientists. Stage 1 fired and produced a gentle rideable start. Then stage 2 kicked in to extend the ride, just as they'd hoped.
Now we just need to add more stages to get that 30-second ride. How much fun is it gonna be when I ride it?
Back at the lake, surf's up, and there's a belated Belleci reality check.
I'm a little nervous. What if this thing blows up?
Since Buster's maiden voyage, they've added more surface area, a keel for greater stability,
Keel weight is installed.
and 200 rockets. Time to go off in banks of 30. Now for the final ingredient, a surfing superhero.
All right, I'm ready for danger. What could possibly go wrong?
All right, buddy, are you ready to make history?
Yeah, I think so.
We'll see you out there. We'll be crossing our fingers for you.
All right, see you guys on the other side of the lake. Now, I'm a little concerned. There's a lot of safety issues involved. I mean, the whole bank could explode. The whole board could set on fire and burn me. Okay.
Tori's done some crazy things on MythBusters, but this could take the biscuit. Oh well, too late to pull out now.
Ride the rocket!
In 3, 2, 1, ignition. We have liftoff.
You okay?
That was one incredible ride. The acceleration was insane.
Tori showed he truly has the right stuff, and that you can surf without waves if you have 200 model rockets handy.
That was awesome! That was insane! Dude, you did it! It literally happened so quick. It was like I was trying to get my balance, and I hit the switch, and before I knew it, I was in the middle of the lake. It was crazy.
Crazy, but this is MythBusters. And Tori didn't reach 20 miles per hour. nor did he last 30 seconds. So while it's a wild and heroic ride, it's myth-busting. Adam and Jamie have already proved that steam can power a rocket. Or at least make a water heater behave like one. And that's got them wondering, what?
Yep.
About what else you could turn into rocket fuel.
What do you got?
An awesome fan favorite myth about non-standard rocket fuels.
I'm gonna go out on a limb here and guess that it's gummy bears?
It is, Sherlock. You're absolutely right.
They're going to try and launch a hybrid rocket, which works like this. Liquid oxygen is sprayed through a hole in solid polymer fuel grain, which ignites, forcing hot gas out of the nozzle, causing liftoff. Simple, but how do you make fuel grain from gummy bears?
These guys are mostly gelatin, which is mostly water. The last time I checked, water doesn't burn very well.
So they'll boil off the H2O from a batch of bears and see what's left.
The trick is to get the candy between 300 and 310 degrees Fahrenheit. It's a superheated syrup. If it got on you, third-degree burns. 305, excellent. Ah! I'm good, I'm totally good.
Explosion number 1, before there's even a rocket in sight.
Wow. Okay, I'm just gonna cool this down because I've got a compressed gas cylinder over there.
Take 2.
All right, welcome back to How to Ruin Kitchen Equipment. Now I'm about to heat up a bunch more candy using this big non-glass container.
This time, things go disappointingly smoothly. And with all the water released...
Okay, tell me what to do.
Just hold on to that while I pour.
All that's left is to pour it into a rocket fuel mold. Here's one Jamie made earlier.
Jamie, I think this might be the worst mess I've ever made in your shop.
I don't know.
You'd have to think about it.
I'd have to think about that. So, there's an engine.
So, armed with a hard candy gummy bear rocket engine, Adam and Jamie hit the desert for a date with destiny.
This is it.
The middle of nowhere.
Welcome to MythBusters Mojave HQ, where it's straight down to business.
So the gummy bear fuel grain is going into its housing. There are a lot of fiddly bits that all have to work perfectly in concert. This is one right here.
Some final adjustments, a mandatory strip of duct tape, and the countdown to gummy bear glory can begin.
System is armed. Launching in 3, 2, 1. Ignition. Oh. Oh, hey! Come on, baby!
I saw light coming out of it, so
yeah,
it's burning.
I see flashing out of it. Come on! Go! Oh. A duck.
Dead duck, more like. The gummy bear rocket is a total dud.
What is wrong?
But total failure does not compute, and Jamie smells a hardware rat.
I'm suspicious as to whether it's the fuel's fault or is it the general rocket system that is at fault here.
There's only one fun way to find out. Fire off a test rocket armed with conventional rocket fuel. This should launch to at least 20,000 feet.
Anything less than that, and we're gonna have some problems to solve. Here we go, launching in 3, 2, 1.
It's a liftoff.
Oh!
Swiftly followed by a letdown.
That doesn't look like it went higher than about 600 or 700 feet.
It should have gone 30 times higher. Jamie was right. The rocket failed, not necessarily the gummy bear fuel. So it's back to base for a second bite at the cherry. But this time, they're tossing out the flighty hybrid rocket.
Instead, we're going to use a solid rocket motor like this.
A solid motor is a carefully prepared mixture of fuel, oxidizer, and binder.
Now, it's nice and simple because, in theory, all you do is light it and off it goes.
But only licensed specialists can make them. So Adam is supplying the raw materials, gummy bears. This time, turned into a fine, dry powder.
Dude, look at that. That's exactly what our Rocketeers want. Time to make a whole bunch more.
While Adam ramps up production, Jamie's making a separate bid for NASA glory.
Oh, man, that's nasty. I'm gonna use poop.
In space travel, every gram of payload costs dear. So astronauts already drink their own urine. Could they recycle their poop into rocket fuel? Jamie's using sun-dried dog poop.
Already giving me nightmares.
Like astronaut poop, it's a hydrocarbon, which burns well in the presence of oxygen. So this experiment isn't as mad as it sounds.
Yep, that's pretty well ground up.
With poop and gummy bear powders packed off to the specialists, it's soon time for the second showdown in the desert.
Round two.
Never in the history of aerospace research have a pair of solid rocket motors like these been put to the test. But first, because this is serious science, a control rocket,
Big rocket coming through.
with conventional solid rocket motor will face the firing squad.
There we go. She's up. MythBusters solid rocket motor controlled. In 3, 2, 1.
Wow.
I knew we'd see a rocket fire eventually. That was cool.
Yeah.
The control rocket reaches an altitude of 4,491 feet. Gummy bears? That's your benchmark. In appropriately dramatic slow motion, the rocket takes its place for a shot at history.
Let's gummy the sky open.
Gummy bear rocket in 3, 2, 1.
There it goes. We have ignition.
Oh, went way up there.
It did. Gummy bears worked.
Yep, they did.
Give me some right there. Boom.
So when you decode the altimeter, it says that our gummy bear rocket got up to 3,691 feet. That's pretty respectable.
It's an awesome result. But at 82% efficiency compared to standard rocket fuel, gummy bears aren't likely to make it to the NASA launch pad. Which just leaves the final rocket fuel frontier, dog poop.
All right, this is it. Poop rocket, the final launch. In 3, 2, 1. Oh, there it goes. Whoa! That's beautiful!
Never before has dog poop shot out of a rear end so spectacularly.
Jamie, that was really respectable.
Yeah.
That was fantastic.
Dog Poop 1 reached an impressive 2,900 feet.
Who knew?
Elon Musk may not put his foot on this tech right away, but Pooh may have a brighter future in space. Back on terra firma,
Firing. We got a gun that'll shoot whatever you want.
it's time to take aim at 3 gunslinging myths. First up,
The gun that shoots its owner.
it's a comic book classic.
It's kind of handy.
I'm thinking bent barrel.
You're gonna have to give me a little more to go on than that.
Okay. Seen it in a million cartoons. One character grabs the gun of another character and bends it, hoping to neutralize the weapon, but it still fires.
So what's the plan?
Plan, I think, is pretty elaborate, so see if you can follow along. I think what we should do is get a gun with the barrel, remove the barrel, and wait for it. We bend it.
Genius.
To test out this crazy cartoon concept, they shoot straight to the Yolo County bomb range.
Awesome.
But before the barrel bending begins, they need to find out
in 3,
how far the unmodified rifle
2,
will fire a bullet
1
into a block of ballistics gel.
There you go.
That was neat and pretty. Let's go check it out.
Okay.
So, what's their ballistics benchmark?
This is funny. It actually went all the way through it, hit our bullet-resistant glass, and bounced back in the ballistics gel about 1.5 inches. It went doink, doink.
The bullet traveled at 1,216 feet per second. Time for some barrel bending.
So to bend our barrels, we figure we're going to heat it up first to make it more malleable. That means getting it like red or cherry red hot. And to do that, we've got a sword forge, which for some reason Adam just happened to have.
Let's fire it up.
Okay.
It's an extremely hot oven in the thousands of degrees for manipulating metal for making swords. In a few minutes, we should have some delicious gun barrel to eat. And it's perfect for our purposes. It's getting there. It's powered by 5 gas jets of propane. Once that gets cherry red, we'll pull it out and bend it to the angle that we need.
Oh, yeah.
Oh, it's moving. Look at that. Right?
And with the hot barrel bent to 45 degrees,
Excellent. Let's let it cool.
the comical-looking gun is soon ready for its first test.
It just kind of feels funny, don't it?
It feels funny.
Yeah, you probably wouldn't want to take it to a holdup, but will it fire?
There we go.
All right, 45-degree bent barrel in 3, 2, 1, go. It fired.
Oh, look at that.
It went all the way through. Went all the way through, bounced off the bulletproof glass, and look, landed on top of our ballistics gel. That is awesome. Well, the numbers are in. Our first control bullet, fired from the straight barrel, shot out of the barrel at 1,216 feet per second. Our second bullet, fired out of this, the 45-degree angled barrel, 1,131 feet per second. 45 degrees, still lethal.
Let's bend it some more.
This time, they're taking it right up to a right angle.
This gun, bent at a 90-degree angle, this is where the rubber meets the road.
That's just wrong.
This is potentially a gun that shoots around corners.
So what's the prediction?
Oh, Jamie, this is perfect.
Is this barrel about as bent as ballistics will allow? Jamie thinks so.
This 90-degree barrel is the maximum point that I think that the bullet is probably going to come out of.
Loading the gun. Shooting bullets around corners in 3, 2, 1, go. Hey, it hit the ballistics gel and the box jumped.
The bullet didn't just leave the barrel, it did so with surprising speed.
Look at that.
That's still a significant hit.
It is a significant hit. It's slightly less than the middle one, but it went all the way through the ballistics gel. That puppy's lethal.
On that note, we'll be right back after a short message from our sponsors.
Come on down to Jamie's House of Bent Barrels. We got a gun that'll shoot whatever you want. Duck hunting, fishing, heck, it'll shoot things you can't even see. Only $19.95, curved ammo not included.
There's only one way to go from here, and that's over the top.
135 degrees. That's a serious bend.
Range is hot.
John Browning must be spinning in his grave.
135-degree bent barrel in 3, 2, 1. I saw the box jump.
I guess that means it came out.
Whee! Oh, it went all the way through the gel.
Incredibly, the bullet still penetrates the ballistics gel with deadly force.
That's astonishing to me. I thought that by the time we got to 135, it was going to be going halfway through.
To remind you, with the straight barrel, the bullet was coming out at 1,200 feet per second. Now with the barrel bent at 135 degrees, the bullet's coming out at 1,050 feet per second.
Flushed with success, there's only one more turn to take.
This barrel is going all the way, 180 degrees. This gun that we're about to put together will shoot the guy who's holding it or someone standing behind him. Almost there. That's it.
That's pretty much it.
That's beautiful.
It's as bent out of shape as a barrel could possibly be, matching the gun in the comic myth.
It's kind of handy.
But will it be lethal?
This is it for the money. Here we go. The gun that shoots its owner, 180-degree turn, and 3, 2, 1. Nothing jumped.
Is that myth busted?
Jamie, it went all the way through.
Wow. Who knew?
This is now my officially new favorite artifact we have ever made on the show.
That's excellent.
I was optimistic, but now I'm speechless. This is amazing.
Okay, so what's with the hardware?
Well, we have a new movie myth that has MythBusters written all over it. And since this movie's come out, we have been inundated with requests to do it.
You're talking about the movie Wanted, right?
Exactly. And in that movie, a secret society of assassins shares the ability to curve a bullet.
That's right. Just with a little bit of a flick of the gun, you can curve the bullet around an obstacle and hit your target.
Secret assassins, swerving bullets. They're not going to pass up the chance to test this.
Okay.
First, they fashion a trio of grimacing targets.
Bad guys are done.
Then head as far from civilization as they can get.
Because this involves swinging a live gun around, we need a lot of open space.
For our first test, we just need a control. To make sure we can all hit the target.
Let her have it, Carrie. Look at that, 4 in the black.
Straight shooting test passed with flying colors. Let the real fun begin.
You guys ready to start curving bullets?
Let's do it.
The goal is to somehow swing a bullet around the pig and hit the target.
So the question is, what technique do you use? Do you use the old top spin lob, maybe a slider, or the old bowling shot? I don't know. I guess I'm just gonna see what feels comfortable.
First up is Grant,
Kind of like an aerobics workout.
who has spent hours honing the bullet-bending technique from the movie. Wasted hours, as it turns out.
Apparently, I don't have that ability.
Sadly, neither does Carrie.
I don't have superhuman strength, abilities, or shooting capabilities. What are you gonna do? I'm just a regular girl.
In fact, the only target under threat around here is passing bird life.
Have to look at the high speed, but I'm pretty sure I curved that one.
So with no bendy bullets and a 100% failure rate, it's time for a helping hand.
We're only human, and the characters in Wanted have superhuman abilities. So that's why we're resurrecting this.
A pneumatically powered arm-swinging robot of previous myths.
It can swing its arm at superhuman speeds, and what's more, it can fire the gun at precisely the moment we want it to.
All it needs is a little modification. Could this be the magic bullet they need? To test it out,
Going down?
they turn themselves in at the South San Francisco Police Department, where they hit the firing range.
We've set up 5 frames of paper down the gun range, 8 feet apart. That way, when the gun goes off, the bullet will punch a hole in each one of those sheets of paper. Now, if those holes are not lining up,
Hey, it works!
then we're curving bullets.
A high-speed swinging robot gun could be a tad dangerous, so there's no room for fooling around.
I've got a 25-point checklist to make sure that we can load and discharge the weapon safely. Trigger cylinder is out. Check. Pressurizing the shoulder. Check.
Your fly's down.
Check.
Safety pin pulled, let's go.
Get out of here.
Test 1 sees the robot arm set to swing at regular human speed.
3, 2, 1.
All right, here's the laser.
The bullet didn't curve. We can see the laser down at this end.
This confirms that human speed is not going to curve a bullet. Now it's time to ramp it up and see if superhuman strength is going to curve it.
We've calibrated the rig to twice what a normal human can do.
Loading the gun with the live round.
Twice as fast. We'll see how that goes.
All right, live round at superhuman speed.
You ready?
Let's get it on.
In 3, 2, 1.
Center shot. Let's check the alignment.
Okay. You see the laser?
I see the laser. It's a straight shot. There's no deviation whatsoever.
Superhuman strength, and we still have a straight shot.
This myth seems to have shot its bolt. So is it time to call time?
This is more fake film physics.
Whoa, we can't go busting this myth yet. I mean, they did have a cool collection of customized guns.
And special engraved bullets.
Okay, I see where you're going with this. Maybe it's not just the sidearm flick that gives us the curving bullet.
Exactly. Maybe it's a function of altering the bullets and guns themselves that's giving the bullets that curve.
First, Carrie modifies the barrel by removing the rifling, which should affect the ballistics.
That should do it. We have a smooth barrel.
Meanwhile, Tori's busy unbalancing bullets. Set 1 has vents cut into the tip. Set 2 has inconsistent weight. And Set 3 combines both modifications.
It is no longer balanced, and it's no longer aerodynamic.
But will the alterations cause a curve?
I gotta make some arrests.
To find out, it's back to the police firing range.
Calling all cars.
Can I get my bike back?
Sorry.
They break open their modified arsenal and carry out tests with a regular gun, but irregular bullets. All with disappointingly dead straight ballistic results.
That's a straight shot, no curving.
Next, they try Carrie's modified barrel.
Okay, groove bullet, D-rifle gun.
Whoa!
Look at how wild that bullet went without the rifling.
The bullet wobbled.
Look at that.
It's a straight path.
But it didn't bend. And it's the same sad story for all of Tori's modified bullets.
Yeah, it's like going whoosh.
But still, it's not curving.
No.
It's proof, if proof were needed, that the momentum of a speeding bullet
Nah, straight path.
means it will fly straight no matter its modifications.
So it's looking like no matter what we do, physics are working against us. We cannot curve a bullet.
Doesn't matter if the barrel's rifled or not. Doesn't matter if the bullets are altered or not.
So this one's busted.
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 Next, a classic straight from the physics textbooks.
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
Until now, it's been a purely theoretical conundrum confined to science exams. But nobody's ever seen it happen for real, because the two bullets would always land so far apart.
So what's the plan?
Well, we gotta go full scale with bullets, but dude, how difficult is that gonna be? I mean, for starters, I don't know how far a bullet fired level from a gun even goes.
Well, why don't we try a .45 caliber pistol? I mean, that has a large, slow-moving round.
And head out to the range and see where it hits the ground.
Exactly.
Perfect, let's do it.
They hit the gun range. Hands down, the best place to test the range of a gun. First, they rig the .45 caliber rigid and level, exactly 36 inches off the ground.
That's perfect.
Next, they check that the gun is aimed dead level, so the bullet flies with a flat trajectory.
Nice. The reason we've gone level is that gravity starts having an effect the moment it leaves the barrel. And that's what I'm interested in. How fast does it drop? How far does it go? Gun is hot.
To find out, they fire a full clip to see how far the bullets fall over 100, 200, and 300 feet.
Let's go take a look.
Okay.
What we've got so far in terms of data is actually pretty freaking cool. This orange line represents the bullet at 100 feet. Very little amount of drop-off. 200 feet. A little more drop-off. 300 feet, that blue line, a lot more drop-off.
A quick calculation shows a fired .45 caliber bullet should bite the dust around the 350 to 370 foot mark.
I expect to be able to see where they land by the marks they make on this white paper.
Firing in 3, 2, 1.
Oh, that looks like we might have hit it.
Their math is right on the money. 360 feet it is. It's vital data. That's the spot where they'll put the fired and falling bullets head to head.
I think we got what we came for.
But to carry out the test, they need laboratory conditions. The 480-foot-long Fort Mason Center on the bay should do nicely.
Ah, look at that. It's magnificent.
There's no wind to worry about affecting our bullet, and it's perfectly level.
First, they set up the gun at one end of the room. Adam checks it's exactly 36 inches from the ground and firing perfectly level.
1.
That gun's firing level.
Works for me.
Okay, we've got all the sensors we need and all the equipment we need to time the exact amount of time it takes a bullet both to be dropped from 36 inches and to be fired from 36 inches off the ground. But that's not good enough for us, for we have a bigger vision. We want to see that drop bullet hit the ground in the spot the fired bullet will be skipping off. That's what we're about to set up.
To pull that off, they'll drop the bullet 360 feet from the gun, the exact spot where the fired bullet should land.
This is my bullet drop rate, and the key component is this electromagnet right here, because it'll hold on to my bullet, and then on cue, it'll drop the bullet.
Sounds simple, but dropping and firing bullets at exactly the same time is anything but. So, over to Adam.
You see the little red light in the lower left part of the frame of this high-speed shot? That's an LED coupled to the electromagnet holding this bullet up in the air. Now, the moment that LED goes off, I know that the electromagnet is no longer powered and it's dropping the bullet. Now, see the tip of this gun? The moment I see a bullet peek out of that, that's when I want the electromagnet to go off.
Got all that? Now a check to see if the synchronizing system works.
Simultaneous firing and bullet drop test in 3, 2, 1.
Let's see how it looked on high speed. It sits on that electromagnet for a while.
Yeah.
The gun and the timing LED went off together, but the drop bullet took its time to fall.
If you look at this high-speed shot of the bullet on the electromagnet, you'll notice it hangs out for 65 milliseconds. That tells me there's a lot of residual magnetism in the electromagnet itself, even though it's turned off, and it's no good as a mechanism for our drop. We've got to rebuild a mechanism, and we've got to rebuild it fast.
Cue brainstorm.
The most difficult thing about this whole experiment is getting the fired bullet and the dropped bullet airborne at the same time.
It gave us the problem that we currently have, which is that it's late.
The gun has to do its thing, the release mechanism has to do its thing, and we can't tolerate even a few milliseconds of variation in this mix to make the result that we want to see happen. It's hard.
But not impossible. And 4 hours later, they've got a solution.
Everything's hot, let's do it.
A solenoid that's triggered by the trigger, releasing the bullet.
Bullet leaves the gun. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Fast forward 360 feet downrange.
Right about there. That's where they were landing out in the shooting range.
They roll out the white carpet to capture the result and move their bullet-dropping rig to the calculated drop zone.
So, simultaneous with the signal that sends that bullet from the barrel of that gun, an electronic signal sends this bullet falling from our little drop rig so that hopefully when it reaches this point, it will meet its friend, the fired bullet, and all of it will be captured on that high-speed camera right there.
Everything's set. Here goes.
Bullet dropped versus fired. In 3, 2, 1.
That looked promising.
Wow.
The fired bullets bang on their calculated drop spot.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
Adam analyzes the high speed and crunches the numbers.
Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
It's truly groundbreaking. A classic theoretical physics conundrum played out for real for the first time ever.
2 bullets, 1 dropped, 1 fired. Amazingly, they ended up in the same place at the same time.
Dude, this myth was every bit as much fun to test as I was hoping it would be. And I gotta say, even though the physics textbooks had it right, I love the fact that we did it full size with real unmodified bullets. I bet no one has ever tried that before.
I think you're right. They all hit the ground at the same time.
Yep. Gravity, man. It's not just a good idea, it's the law. Confirmed.
Please don't try what you're about to see at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode, it's grown-ups gone wild with 3 myths that are anything but child's play.
3, 2, 1.
Oh, darn, the seesaw broke. It just kind of like folded in half.
And later, the adrenaline's rising as the team feels the need
That car didn't skip, it flipped!
for speed.
You got me.
To source our first myth, Adam and Jamie are going into the ungoverned wilderness of the internet.
This is a YouTube clip. A man is seen sliding down a water slide, launching himself off a ramp, flying a seemingly impossible length through the air and landing in a little tiny swimming pool.
And so you want us to test this?
Oh, I want to test this.
Is it actually feasible to fly that far and land in a tiny paddle pool? Or are the video makers pulling a fast one? They're going to build a similar slide with one crucial difference. Instead of land surrounding the paddle pool, they'll set up the slide next to a lake. Using the video, Adam's done the math and figured out they need a 200-foot ramp on a slope of 24 degrees. But there's some work to be done first.
Behind me, in sheer size and tonnage, is the biggest build we have ever undertaken.
With the earth finally in place, the guys get to work on their ramp slide hybrid. 52 sheets of plywood are slid down.
It looks great. You first.
They add straw barriers to stop them going off-piste. And cushion it with a roll of carpet that needs to be taped down.
Oh.
Can I get another roll of duct tape?
Well, the duct tape survived. So with lacquered vinyl applied...
Come on, all the way, buddy. There we go, okay.
It's time for a cautionary dry run.
I'm not only having fun, I'm finding if there's any spots that are sticking up that could hurt us.
Our slide is 165 feet long. As we go down it, we'll be going at a 24-degree angle. As we come off the end of it, we're going to be going at a 30-degree angle. How far we go and how fast we travel, that's what we're here to find out.
Jamie sorted out the lube.
Pull.
And Adam suited up. Tempting as it is to go from the top, Adam's playing it safe, and for the first try, is going to set off from halfway.
I'm dying to try this out. Here we go, test number 1.
Adam Danger Savage empties his bucket and adopts the downhill luge position of the video.
Oh, yes! I'm okay. Up very far.
Ironically, by not going from high enough up the slide, Adam nearly came to serious harm.
You barely made it off the end of the ramp.
I don't know what happened.
And for take 2, he'll need a little more slide. So he heads to 3/4 of the way up. The landing may have been a little hard on his derriere, but at least Adam got air.
Coach, I'm ready to go in for another run. Will you send me in?
This time, Adam's going to the top. For the myth to be confirmed, they need him to fly around 115 feet like the guy in the video. And they also need to hit the same spot repeatedly.
Okay, I'm ready to go from the top.
It should be all downhill from here.
Yeah, well, break a leg.
Here we go.
3, 2, 1. Oh, it doesn't take much. Here we go. Whoa! Yeah! Wow!
Well, that was one mighty splash. But Adam only flew 70 feet. A far cry from the 115 feet of the myth.
That's totally intense. That was, above and beyond everything else, the single most intense thing I've ever done on the show.
But Jamie's not getting left out of the fun.
You don't think I'm going to pass something like this up, do you? I mean, look at it. And besides, who knows, I might go further.
From the top, 3, 2, 1.
Oh! He's okay.
After a pretty ungainly landing, Jamie only beats Adam's distance by 2 feet. That means the distance achieved on the slide in the video is busted. But that's only half the myth.
But now that leads to the natural question of accuracy. If we did this on dry land, could we place the pool somewhere where we'd hit it every time and survive?
In one run and a second, Adam surprisingly strikes almost the same spot.
So those runs were great. They were both within a couple feet of each other.
Really?
Yeah.
Time for a makeshift paddle pool target.
Okay, so from everything we've done so far, we've calculated that we're hitting a spot that's pretty much in the center of that circle behind me. But here's how I want you to think about this. Picture that that is dry land, and the only salvation you have at the end of that dry land is that circle, which is full of life-saving water somewhere in the middle of the dry land, and you are going to trust your life to hitting that target? I would not.
Dude, I wish you could see it from here. From here, the ring looks like the size of a quarter.
Well, then you shouldn't have any trouble hitting it.
Okay.
It all comes down to this one. One souped-up super slider and one floating ring of rubber. Will Adam be accurate enough to ring in this myth?
And 3, 2, 1. Yeah!
That was a perfect splash landing.
Dude, I didn't even break it!
Adam's final run propelled him 70 feet and then directly into the center of the pseudo-kiddie pool. But where does that leave the myth?
Well, as far as the distance goes, it's busted because we'd have to have a slide at least twice as long as this to get that 115 feet. But accuracy?
Plausibility of the accuracy is the thing I find most astounding in this. When we started testing this, I would have never called that we'd be reliably hitting that dot time and again, that you could somehow set this up on dry land and actually hit the target.
Well, for the myth to be true, both halves have to be true, and they're not, so it's busted.
Our next myth has danger written all over it.
The claim is that if you get up enough speed, you can actually swing all the way around a swing set, make a complete revolution without falling out.
Sounds like a good way to break your neck.
Grown-ups attempting a dangerous stunt using equipment designed for kids. I can see where this is going.
Warning, this swing was designed for use by children only, not for adult use.
But a little padding should make it safe, right? With a few more pads added and a high-speed camera to capture the stunt, Carrie's ready for a first attempt at the 360 loop.
Okay, test number 1, me under my own strength. Watch out. Okay, I'm getting to the point where the chain's starting to get loose when I get to the top. So I'm thinking I'm at my maximum.
Carrie's way off a 360, but still gets some impressive height.
Whoa!
You went total
Whoa!
You went
I'm
over
above
horizontal.
Your swing technique is excellent.
Ready.
Test number 2, Tori underneath his own strength.
All right, ready?
Can Safety Officer Tori launch the child swing any further around? To infinity and the ground.
I'm okay.
Are you okay, dude?
Oh, I'm so glad we had the mats.
As further proof you should never try this, here's another look at Tori's epic fail. Time for Plan B. A 65-pound crash test dummy. Add some serious muscle.
You made it! Dude, we need a little help.
Tori's biker buddies are going to help try to swing the dummy all the way around.
Cool. All right, you guys ready? 1, 2, here we go.
They've got the mini swinger over the bar. This myth is still alive and kicking.
That's all we needed. Just a little muscle.
But it turns out that moments after she goes over the bar, the dummy falls out of the sky. So it's not a proper 360. Time to get a little creative.
We know this myth is busted. You can't, under your own power, do a 360. But as MythBusters, we kind of want to see what it takes to actually do it.
They're going down to small scale and adding some mini boosters to a doll called Simulate Susie.
We came up with sort of a Wile E. Coyote solution to this 360 problem. We're just gonna strap a few rockets till it'll simulate Susie and just watch her go around the swing set.
In 3, 2, 1, firing.
Where's her hand, dude?
Busted off.
Blew her hand off?
She's tough.
The horizontal rocket sends Susie off into a cataclysmic spin and blows off her hand. They decide to reposition the rocket at 40 degrees.
We're armed and launching in 3, 2, 1, fire.
Yes!
Yeah.
Yes!
Beautiful.
Perfect!
That was great.
40 degrees was spot on. Susie goes 360 and beyond. So the next stage is to replicate this result on the full-size swing by strapping on some mammoth missiles.
Something a little scary about this image.
Oh, come on, it's perfect family entertainment.
Definitely don't do this at home.
The dummy is wired to the swing and fitted with 2 rockets, one each side.
Going in 3, 2, 1.
Okay, stay put.
That did not go according to plan. So what went wrong? The high speed shows that one side fired off just before the other. It's a fraction of a second, but it's enough to throw Susie into a crazy twist. Time to simplify. They now attach the single biggest rocket dead center. But because they're worried about Susie's weight, they opt for a launch angle of 60 degrees instead of 40.
3, 2, 1.
Another failure to launch. But it's not all bad news.
That even though the rocket fired its full ignition, she didn't spin, she just stayed in one direction, which is ideal. That means all we need to do is probably drop the angle a bit and she'll go forward instead of being just pushed down.
They drop the angle to 40 degrees. Now everything matches the successful scale test. While the fire marshals stand by, Jamie does a final head count.
3, 4.
With the light fading, it's now or never for this myth.
Okay, we're good.
Jamie gives her one final push.
And 3, 2, 1.
And she's over. At last, using the results of the scale model tests, their girl finally goes the distance.
That's a full wrap on the chain.
And they have video proof that amidst the smoke, she really did go up and over the bar. And her chains, well, the high speed shows that they were straight the whole way round. A perfect demonstration of a swing set 360, even if it was cheated with rocket power.
So in the final analysis team, what is the final verdict? The myth that you can do a full 360 on a swing set, busted, plausible, or confirmed?
Totally busted.
Not possible, busted.
Busted, but the rockets were spectacular.
To understand our final myth, you'll need to concentrate. And not just because Adam's bunged on his British accent.
I'm a skydiver, right? And I'm falling through the air, and my parachute has utterly failed. Looking desperately down at the ground for something to break my fall, I spy a children's playground and a seesaw with a little girl at the other end. Not worrying about her, I aim for this end of the seesaw, go straight upright. At the last second, I hit the seesaw and catapult that poor little girl up to the top of a 7-story building where amazingly she lands safely.
Wow.
So, if a skydiver with a failed parachute did happen to land on the end of a seesaw, basic physics tells us that the lonely little girl on the other end is going somewhere. But could she really go 7 stories high and live? There's only one way to find out.
All we need is a regulation seesaw.
And a correctly weighted little girl.
And a skydiver.
Terrific.
Adam knocks the seesaw up in record time.
It is, in fact, a seesaw.
I want one of these in my office.
They've also got a crane and a cute little girl crash dummy.
So shall we name her Ariel?
From this height, they can't get a skydiver to fall at terminal velocity of 122 miles per hour. So they'll compensate by adding a lot more weight in water-filled barrels.
I've calculated that filling the barrels with 1,150 pounds of water and then dropping them from 75 feet should exactly match the skydiver's free fall impact force of 85,000 foot-pounds.
Looks good to me.
All right, let's go up. So I'm gonna pull the safety, but you know what? I don't want to be anywhere on this lot when we drop this thing.
I was thinking we should be up over there.
I was thinking the same thing. All right, here we go. Skydiver Seesaw in 3, 2, 1.
Oh, darn, the seesaw broke. It just kind of like folded in half.
The bench is buckled, but the full extent of this disaster is best assessed from ground level.
I don't think we've ever done this specific kind of damage.
It not only crushed it right at the pivot point, but it also crushed it right at the end here. So, you know, that's a heck of a lot of force.
A lot more than we considered. We're gonna have to rethink this thing.
When Adam says rethink, he means it. A week later, all 5 MythBusters get together at Mare Island Shipyard. They've now got a mega-sized crane, a 170-pound skydiver made from a wetsuit filled with guts-like material, a mega bungee cord to fire the skydiver at terminal velocity of 122 miles per hour, an innocent little girl crash dummy.
You're gonna be fine.
And of course, the pièce de résistance, a handcrafted, super-strength seesaw.
3, 2, 1. Ta-da!
Wow! Oh my God, this is better than Christmas.
I've never seen a seesaw like this before. I was expecting a giant piece of steel. This is beautiful. It's elegant. It's gorgeous.
With the girl in position, Grant applies stick-on patches that measure the force of the impact.
If the red one triggers, she's dead. If the green one triggers, she's injured and alive, but she's not walking away.
When Grant presses go, the plan is that the bungee cord will fire the skydiver right at the seesaw, opposite the little girl. Because accuracy is crucial, the skydiver will be guided by wires.
Here we go. In 3, 2, 1.
Did you expect that? It didn't go up. It shot across the dry dock.
Wow. That was cool. The skydiver hit the seesaw stayed together, and the little girl got launched over 55 feet in the air. That's above the dry dock. See, the skydiver exploded.
One word for this, splat.
Looks like he landed butt first.
His legs missed the seesaw, but his upper torso hit it. It's probably about 60–70% of his mass contacted it, and even that amount was enough to catapult her 5 stories up in the air and 70 feet laterally.
Grant checks the shock watches, and the news is grim.
Oh, red shock watch is tripped.
Not surprisingly, the dummy is toast. They want to try again with better aim, but our skydiver is in no shape for another run. Instead, they'll use a weighted inner tube.
Now, it is the same exact weight as the average man, but this time we're hoping that we'll impart all of its energy onto the seesaw and fling the girl the 7 stories that we talked about in the myth.
Here we go! 3, 2, 1!
The skydiver hit 122 miles per hour. And despite the colossal sideways arc, little Ariel flew way higher than anyone dared hope.
She flies about level with our spreader bar, and that's 130 feet.
That's 13 stories, and that was with an angle like this. If we'd got her to go straight up, she would have cleared 200 easy. If you had an impossibly strong seesaw, if you had a parachutist that didn't just go splat when he hit it, you'd be capable of launching a little girl up at least 13 stories in the air.
So, how do we call it? Well, sad to say, it's busted. The team built the best possible rig and almost doubled the 7-story flight. But the sensors proved that, unfortunately, that flight was a one-way ticket. It'll be tough to keep pace with those playground antics. So, time to put the pedal to the metal
50 miles an hour!
and power up 3 myths about speed.
The distance I'll be shooting at Jamie from is 400 yards.
First, Adam and Jamie are going to test the movie myth that driving in reverse could give you an edge in a car chase.
Been trained to drive in a lot of different ways over the years, but backwards isn't one of them, and it involves a lot of different skills, not only driving ability and spatial awareness, but also really proprioception.
Yeah, let's get to driving.
Okay.
Going backwards in a car chase might sound like movie make-believe, but first, let's check how fast a reversing car can go.
We're going to test out these cars, see how fast they go in forward, and compare that to how fast they go in reverse.
All right, commence quarter-mile test in 3, 2, 1, go. Here it comes. 80 miles per hour.
It's a good start for their converted cab. But how fast will the taxi go backwards?
Now, will our car be able to go as fast as they seem to go in the movies? That is just what we're about to find out. All right, Mr. Hyneman, in 3, 2, 1, go! 52, 53, 54 miles per hour.
Pretty quick. A car traveling in reverse at that speed could definitely provide a good movie chase. But how easy is it to steer in reverse?
We've got a course that's full of the kind of challenges a Hollywood hero has to face, and we're going to see if we can reverse through it at high speeds without crashing.
All right, first run in 3, 2, 1, go.
Adam's off. And from the outset, he's ignoring the mirrors.
Whoa!
Oh, there goes a cone.
And going with the over-the-shoulder technique. But his cone count is cataclysmic, and his time is terrible.
How did I do?
1 minute, 7 seconds.
It's very hard to gauge how hard you need to hit a turn in reverse because all of your metrics for reaction in terms of how the car moves are way off kilter. It's a far more sensitive device in reverse. But with some expert training, will we be able to bring this myth back from the brink?
Enter expert driver Brian Frazier, and the technique he's going to teach is surprisingly simple.
So I'm going to change my seating position now a little bit. I'm going to prop myself up, loosen my seatbelt, turn yourself as far as you can around, get your body almost in the center of the car. Okay. I'm going to steer the car now with one hand, but this hand will never leave the steering wheel.
You're not going to let the steering wheel shift in your hand to lock.
You're palming the wheel the entire time.
I see. Okay, cool.
And believe it or not, that's apparently all there is to it.
3, 2, 1, go.
By shifting his body to the center of the car.
Wow.
And keeping one hand on the wheel at all times.
Wow, I can't believe how fast you're able to do this.
Brian speeds through the course.
That is amazing.
So I'm about to give that a shot. This is gonna be cool.
Like Brian, Adam slides to the center to give a viewpoint that's easier to process.
Oh, look at that. Okay, so 3, 2, 1.
And like Brian, he then nails the course.
Oh, that's so cool.
In just 20 minutes, he's gone from being pretty average to being pretty great. And it seems to be all down to the central head position, which seems to be letting Adam's brain process the direction to turn much more accurately.
Time for the final test. Can Adam plausibly evade a cop in a car chase going backwards?
I'm here in an abandoned neighborhood in Marina, California, where my crew has set up a course, and I'm just supposed to drive as fast as I can in reverse.
This final farewell is a half-mile of twists and turns, but with some movie mayhem thrown in.
We're going to put a little pressure on Adam because I'm going to be in a cop car on his ass the whole way, with the sole exception that when he sees me and takes off, I'm going to be outside my car. So he's going to have just a little bit of a head start.
Adam's goal, like the classic Hollywood hero, is to make it to the finish line before those pesky police.
That is a cop. That's bad.
But with reverse gear his only option, will he escape to freedom?
Here we go. Bye, cop.
The chase is on.
Here we go. Getting the heck out of here.
And by the time Jamie's got going, Adam's already out of sight.
Make a right-hand turn here. Don't let go of that wheel.
By shifting to the central position, he's able to navigate with skill.
Whoa! Flaming car! Dude! Oh, man! Post-apocalypse!
At least when he wants to.
I want those boxes! Come on! Yeah!
But while his steering is supreme,
I don't know where he is. I hope he's not close.
his speed, while fast, is no match for Jamie.
Oh, fruit stand! I'm not gonna miss the fruit stand.
Adam may be down, but he's not out, as he reverses back uphill.
Ah! I'm going still!
A strategy that the Hyneman then copies. With both drivers now speeding in reverse, it's a case of who's going to blink first.
Oh, yet another in a long line of things that we should just set up for the public and charge money for. That was awesome.
Step out of the car with your hands up.
That was so much fun. Oh my God. That was the best thing ever.
So how you want to call it?
I have to say, I started this story thinking it was going to be handily busted, and I am now thinking that it's actually plausible. It's not unreasonable how much speed and maneuverability you can get going in reverse.
Yeah, I mean, both of us, I think, if we had our choice, would go, you know, front forward.
Yeah.
Because that's going to be your better option, but surprising how good it can be.
Let's call it plausible.
All right.
Next, a myth that requires speed and skipping.
Are you familiar with the Cannonball films?
Yeah, from the 80s, right?
Okay, so it's the third installment that our myth comes from. The beginning of the movie, there's a red Lamborghini that is trying to evade the cops. So what the sports car driver does is he drives off the road and heads straight towards the lake.
He totally floors it, skips across the water, makes it to the other side, and gets away from the cops.
Exactly.
So the myth is, could a 1.2-ton car skim a pond like a skipping stone?
So what's the plan?
I have watched the scene over and over in slow motion. And what I have found that watching frame by frame and measuring points of reference, the car wasn't going very fast, maybe 50 miles an hour. It went off a little launch and skipped about 4 times over a 100-foot body of water.
To stand in for a Lamborghini, we've got this.
What in the heck did she get that for?
So our prop budget couldn't stretch to $250,000. But it's the same size, surface area, and weight. No one's volunteering to drive this on such a dangerous mission, so Grant's going to wire it for remote control.
I got a plan. I got a plan.
Let's skip to the fun part. A small lake in Oregon with a road leading up to it. They've built a small kicker ramp to get the car airborne, just as they had in the movie.
There's something that doesn't look quite right with this car. It doesn't look fast enough. That's a fast car.
We are ready to find out if this car is gonna skip. Is it gonna work? Probably not.
So for this test, we're doing everything like they did in the movie. We're going 50 miles an hour, we're taking it off a little jump, and we're gonna hopefully skip it across water.
It's sink or swim. As Jessie heads to her vantage point, a clearly excited Grant starts the engines.
The car is armed. This is it, you guys.
And Tori gives the countdown.
Here we go. In 3, 2, 1, hit it.
Grant's actuators put the pedal to the metal, and the mustard marvel takes off. As the car gains speed, Grant expertly steers straight down a guideline until
50 miles an hour.
with a hop, a flip, and a thump, the car crosses the pond, but not quite as hoped.
That car didn't skip, it flipped! Oh,
Oh my God.
I don't think
That was insane. Look at what it did, though. It actually made it to the other side of the pond.
that's not how it's supposed to do it. Wow.
Oh, wow. Oh, my God, we destroyed this car.
Now, we matched pretty much every aspect of the movie. The ramp, the speed, specifications of the car, and we got a completely different result. What this means is that the movie stunt was faked, that it wasn't a real skip across a lake.
But they're not stopping there. What does it take to get a car to skip across a lake? Using a scale test, they figure out it's better to ditch the ramp
1. That was cool.
and also boost the speed.
28. Oh, holy crap.
At the equivalent of 100 miles per hour, the model car skips and would skip again, except it runs out of trough.
But this is just small scale. I mean, this is a toy we're using right now. When we go to full scale, using a car weighing 2,600 pounds, who knows what's gonna happen?
Time to try the pond skip again. This time they'll get rid of the ramp. And they'll have a new car that will be souped up with nitrous, doubling its horsepower.
Now, this little wire right here, this is the Go Baby Go wire.
And this huge rush of power coursing through the veins of this little car, and it's just going, and it's gonna make it exponentially harder to control. So I could potentially have a rocket on my hands.
Here's how it could work in theory. If the car is traveling fast enough and keeps its nose up each time it hits the surface, forcing water downward, the opposing force of the water pushing up on the car should propel it forward.
My heart rate just went up when you started that engine. I'm ready to do this.
Me too. And with only one car, there's just one shot to make it across the lake.
And we're gonna put it in drive.
The vehicle is in drive.
Yay!
Okay.
Dude, has it hit you yet? We are about to skip a car across a pond. This is crazy, man.
This is totally crazy.
We're like Thelma and Louise.
We are?
I just say dumb things when I'm excited.
Okay.
It's make or break time.
In 3, 2, 1, hit it.
Okay, brakes off.
But probably break.
And here we go.
Grant builds up the speed, then presses the Go Baby Go button.
Here goes the nitrous.
The car surges forward, and when it reaches the lake, something beautiful happens.
No! We skipped a car across the lake!
That was a full-scale car skip. The high-speed shows the supercar skipped twice over the 100-foot lake and then continued to drive on the far bank until Grant remembered to apply the brakes.
We did it! We skipped! No rockets, no special tires, no ramp, and no underwater platform.
and it skipped across the lake.
Just like the small scale said it would.
In fact, it's so easy, I think we really need to stop and say, do not try this at home.
Yes, but let's keep in mind, the movie is still busted.
Of course, going 50 miles an hour with a ramp and you're going for a swim.
Next, the boys are going to try and move fast enough to dodge a bullet.
The theory behind this myth is the idea that there is a theoretical distance at which you could both see a bullet being fired and yet have enough time to get out of the way of the bullet that's been fired at you before it gets to you and hits you.
They want to find out if a sniper is far enough away and you can see him take the shot. Can you react quick enough to save your skin? First, they need an abandoned airfield. Check. Then they need a sniper. Check. Let's check his aim is true.
That's how it's done.
Check.
How do you like them apples?
He'll do. Their aim is to find out how long a bullet is in the air between the barrel and its target.
The purpose of this test is to shoot the rifle at a fixed distance and record how much time it takes for the bullet to hit the target. That's the amount of time that we'll have to dodge a bullet.
They test at 200 yards,
231 milliseconds?
500 yards, and at 1,200 yards, which is almost a mile away.
Beautiful. We got a reading, 1.791 seconds to target.
Well, now we need to know how quickly we can jump out of the way, huh?
Human reaction tests it is. Let's do it.
Back at the shop, the boys are going to need some Matrix-style moves.
This is our human being. His task, to get himself out of the path of a bullet described by the X on his chest and the bullseye behind him. His signal to move that the shot has been fired will be given by this digital camera flash remotely triggered by me from back there.
All right, are you ready, Jamie?
Human reaction time speed test at some random point in the very near future. Nice.
Jamie's fast. His reflexes are honed to an almost superhero speed.
Nice work there, cowboy. You want to man the remote flash while I try a couple?
Okay.
Adam's style is best described as different. But to see who is quickest, they need to see it in slow-mo.
Here's mine. So I turned into one of the Three Stooges, and I don't know.
But Hyneman's hips don't lie. With all the swagger of a bullfighter.
Check his bad self out. He is a bullet-dodging Hoosier.
Despite Jamie showing an artful economy of motion, it turns out that Jamie and Adam clocked very similar times. Jamie's a touch quicker, though, at 490 milliseconds. Now they'll use data from the sniper test to determine the range at which you could potentially avoid a bullet.
Now, if I draw a line from 490 milliseconds out to our plot and check out the corresponding distance, it's 400 yards. That is the theoretical distance at which you could possibly dodge a bullet, but only if you could see the muzzle flash from that distance. That's what we're about to find out.
The question now is, how far away can you still spot the muzzle flash? Back on the range, the boys ask the sniper to fire blanks, while they try to spot the flash. First up, from 100 yards.
I saw it.
I saw it.
At 100 yards, the flash is as clear as a bell. And that's also true of 150 yards.
Saw it.
I saw it.
But 200 yards, or 600 feet, is a different story.
Okay, Dave. 200 yards, fire at will.
I didn't see that. Let's have him do that again.
Dave, let's have one more go.
Did you see it?
I'd say that's at the borderline.
Well, if you got the eagle eyes, let's push it another 25 yards.
And at 225 yards, or 675 feet, even eagle-eyed Jamie fails to focus on the flash.
Nope, I don't have it.
200 yards is our threshold.
Yeah.
With our blank rounds matched to a sniper's round, our ability to see the rifle firing is 200 yards. If you look at that on our graph, yeah, it's not quite enough time for us to get out of the way.
Remember, based on the bullet travel time, coupled with the human reaction time, 400 yards was the minimum distance needed to dodge. But at just half that distance, you can't even see the muzzle flash.
I don't have it.
So the myth is busted. But we all want to see them dodge a bullet, right? So what about a larger muzzle flash? That would help them see the gunfire from further away.
In Hollywood, for instance, a blank for that rifle includes a lot more fire coming out of the tip because that's more visual for the movies. So that's what we're going to do. We're going to start from this distance with a full Hollywood flaming blank and see how far we can see that rifle firing with one of these.
The Hollywood round turns out to be visible even at 1,200 yards.
I saw that.
Totally saw it. Wait. And I heard it. That's plenty of time to get out of the way.
So in theory, they should be able to dodge a sniper's bullet, so long as he's using a Hollywood-style muzzle flash.
Now, since we can't use real bullets for this test, but we've gathered the information that tells us the exact bullet flight time for any distance we choose,
perfect.
We are going to imitate the bullet's flight electronically. Here's how.
When this gun fires a blank, a wire I've mounted on the trigger is going to close a circuit,
which starts this timer timing. It will count down for the precise length of time the bullet should be flying through the air, and at the instant it is supposed to hit its target, it will tell this paintball gun to fire a round directly into Jamie's chest. Now, will he be able to get out in time?
I think I might.
No, not yet. That's what we're about to find out. The distance I'll be shooting at Jamie from, I love that sentence, is 400 yards.
I'm set and ready.
Okay, fire Will.
Copy that.
You got me.
But Jamie can't dodge the bullet from 400 yards. And neither can Adam.
That was interesting. At 400 yards, we've got 500 milliseconds to react and get out of the way, which ought to be enough time, but there's a difference between the shop test and the real world test. In the shop, we had this super bright flash right in our face. In the real world, we've got a tiny dot 1,200 feet away. It's a lot harder to see. So now, we're gonna move that dot to 500 yards, give Jamie even more time to react, and see if he can deliver the goods.
Never has the need for speed been greater. With 500 yards and 600 milliseconds to react to the Hollywood blank, it's time to go big or go home.
It's time to call into play those cat-like Hoosier reflexes.
Fire Will. I dodged it.
At last, at 500 yards or 1,500 feet, the Hyneman sways at speed and the paintball sails clean past.
This test showed that I would have been able to dodge a bullet, but here's the thing. We were using Hollywood blanks, and if we were using real bullets, I wouldn't have been able to see a thing, and I would have been dead.
The verdict is, it's busted. There is no way you can dodge a sniper's bullet.
Please, don't try what you're about to see at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode,
You are crazy!
we drop some jaw-dropping myths
I'm terrified. I'm totally excited.
about gravity,
That was such a rush.
And later, inflation is rising. With 3 myths about balloons.
This is my favorite scale experiment we've ever done. Full stop.
Falling or floating, we've got you covered.
Now that is what I call a party.
First up, or rather down, it's the elevator of death.
Now, the myth goes that you're in an elevator, the cables are cut or something, you're plummeting rapidly towards the bottom of the elevator shaft, and right at the very last second, you jump as hard as you can, and that saves your life.
Oh, yeah. I've been looking forward to this for a long time.
Yes, the MythBusters are going to drop an elevator down a shaft. Just before it hits bottom, the test subject will jump in the air to see if he can counter the effect of the falling elevator and come safely to rest. First up, they need a tall building with an elevator they can drop and destroy. Seems like a tall order, but incredibly, they strike gold.
Is that it?
I guess that's it. It's an 8-story building.
A derelict hotel now scheduled for demolition, with elevator service as well, of sorts.
There's the motor. What's left of it.
Getting the elevator working will be no small task. The cables haven't moved in years, and the motor is a wreck.
In theory, if we could tie power onto that, we would have a working elevator.
It's a long haul to the top of the shaft. 8 floors, 9 counting the basement.
92 feet to the top of the pulleys.
92 feet to the dead bird.
To get to the bottom of this legendary myth, they have to figure out a way to raise and drop the elevator, and how to get Buster to jump up at just the right moment. But how high and how fast? Time for a human test.
All right.
In their short moment of acceleration, the average top speed generated was just over 8 feet per second. Now, they need the stunt dummy to replicate that.
I need to figure out how to make Buster jump. I think I'm going to have to use some kind of spring because I don't want to go for the gunpowder.
A car spring inside overlapping tubes with a quick release catch.
There we go.
There, okay.
With Buster riding shotgun.
Giant industrial pogo stick.
Now that looks like a good jump to me.
It's time for Buster to fly or flop.
Well, that wasn't very much at all.
So it's back to the springboard, but with a bigger spring and a couple of gallons of duck fat.
Tastes like French fries.
Test 2. Will this give Buster a bigger kick in the pants?
Ready? Well, that was a good jump.
Nearly 12.5 feet per second. More than enough to give this myth a fighting chance. But will it be enough to break Buster's fall? Or just break Buster? Now for the sticky problem of those elevator wheels. If they can't get them working, this myth is stuck between floors. But Jamie has a gift for thinking outside the box.
I had an idea that I might be able to modify an electric vehicle that I built. It's a prototype that I have back at the shop.
Meet Jamie's Life and Death Machine, or LAD for short. With applications for law enforcement, fighting fires, and hopefully operating ancient elevators. Multi-purposing is the MythBusters' middle name.
Okay, ready? Hey, that's it.
Remember, the elevator hasn't moved in years.
Jamie, that looks great.
Yeah, baby! Couldn't be happier.
I think Jamie's rig is a classic MythBusters rig. You know, we have to lift an elevator, and Jamie says, well, I've got a robot in the shop that we could modify to lift this elevator.
Obviously, elevators are designed not to fall. Fortunately, the MythBusters wrote the book on disabling safety systems. So first, dump the emergency brake.
Anticlimactically enough, I believe I've disabled the entire mechanism by removing this simple pin.
There's also a counterweight that balances the elevator car. It's got to go too.
We are cutting the cable. Stand by.
the drop mechanism's attached, a movie special effects quick release.
When we get upstairs, we'll be able to pull a pin, and this whole car will drop. You know, working with these dirty cables, I can't tell you how hard it is not to touch Jamie's white shirt. I just want to touch it, make it dirty.
They're ready to board. Final call for passenger Buster. But how to trigger Buster's jump at just the right moment before he hits the ground?
Okay, Buster, this won't hurt a bit.
Adam's tying off a trip line at the top of the shaft. That will pull the release on the launcher when the elevator's 6 feet from the bottom.
Looks about perfect to me. If something goes wrong, somebody could get killed here.
No kidding. Getting insurance for this stunt was harder than finding an elevator to destroy.
We're about to drop an elevator. I'm beside myself.
It's all gonna be over in a few seconds. And with a big boom, what else could we ask for?
Jamie and the team are in the basement. Adam's 9 floors up, quick release in hand.
I'm terrified, I'm totally excited. Ready to drop. In 3, 2.
Bon voyage, Buster.
Oh my God! That blew my face back.
That was such a rush. It was just like this enormous blast of air.
The overhead camera shows Buster's pogo stick launched right on cue. But did it save him?
His head's gone.
We've got an arm. I believe this is more damage than we've ever done to Buster in one myth before.
By the bottom of the shaft, the elevator and Buster were falling at 53 miles an hour. Buster jumped up at 12 feet per second, or 8 miles an hour. Enough to hit the roof, but he still hit the ground at a fatal 45 miles an hour.
Well, you know, you might be weightless relative to the elevator, but you and the elevator are going down at 53 miles an hour. So unless you can jump up at 53 miles per hour, you're dead.
I think we've done all that we can here. I think this myth is definitively and finally busted.
This next myth from the movies is all about terminal velocity and wind resistance. From the movie Point Break.
That's the one where Patrick Swayze jumps out of the plane with the only parachute. Adios, amigo! Gets into skydiving position. And then Keanu Reeves freaks out 15 seconds later. No shot! Jumps out with no parachute, but gets in a streamlined position and catches up to Patrick in 45 seconds.
You are crazy!
To see if one adult human really can fall faster than another, Grant starts with baby steps.
I want to do a small-scale experiment first to demonstrate that objects with the same mass but different shapes will have different terminal velocities, and that's because the difference in wind resistance.
Terminal velocity is the maximum speed that something can fall through the air. It's when the force of gravity is matched by the force of wind resistance, preventing that object from falling any faster. But can subtle changes to its shape affect how fast an object falls? Grant hastily knocks up a mini wind tunnel and 2 mini skydivers of identical mass, in different falling positions as per the myth.
One in the arms and legs out position for maximum wind resistance, and one in the straight position for minimum wind resistance. I'll put them both in the wind tunnel and see what the difference is.
First, the spread-eagled skydiver. When the wind speed is strong enough to hold him stationary, that's his terminal velocity. Carrie clocks the wind speed using an anemometer.
Okay, what'd you get?
We're looking at a pretty stable average of about 1450 in feet per minute.
Okay.
Next, the streamlined skydiver. If this myth is going to fly, his terminal velocity has to be higher.
I got about 2,000 feet per minute.
Oh, fantastic.
So, proof of concept, tick. Better streamlining equals faster falling. In Toy Town, at least. But can real human beings fall at different speeds? To find out, they hit a supersized skydiving wind tunnel, where the instructors are head over heels in anticipation. Gigantic turbines shift 1.3 million cubic feet of air a minute, so they can replicate a skydiving freefall, perfect for their Stage 2 tests.
We're here to see how changes in wind resistance affect terminal velocity.
So what's the plan?
I say we just get in there and try different body positions and have some that are more wind resistant and some that are less and see how we behave.
We're gonna go to some hot nightclubs in San Francisco.
I expect I'm gonna walk in there to make sure it's working, and I'm probably gonna get tossed around like a rag doll.
With the wind howling, Tori tries out Patrick Swayze's spread eagle position. And he floats, confirming Swayze should have been traveling at 120 miles an hour. The terminal velocity of a standard falling human. Next up, Carrie tests Keanu's vertical position, and she doesn't fly, meaning if this were for real, she'd be falling faster than Tori.
I think this is a great demonstration of how your surface area affects your terminal velocity.
But it doesn't tell us exactly how fast Carrie would fall. Even at 150 miles per hour, she's still grounded. Only when she untucks does she fly. So there's only one way to test this myth, and that's for real. With our handsome hero from 15,000 feet.
Skydiving!
Next up, Skydance skydiving. With the moment of truth fast approaching,
Do we really need to test this myth?
Tori's wild enthusiasm has gone AWOL.
When everybody else is doing it, you're like, ha, that looks fun. But then, you know, when you're about to get up in the plane and do it, a lot of things go through your mind, like death. I just gotta remember to breathe, not my pants, not throw up, not pass out, not scream like a little girl. Oh yeah, and open the parachute. That's an important one.
Here's the plan. When the plane reaches an altitude of 15,000 feet, Tori and his tandem buddy will jump out, assume the spread eagle position, and plummet to Earth. 15 seconds later, a specialist skydiver heads off in hot pursuit with streamlined pose. But will he fall fast enough to catch up with Tori, as in the movie?
I'll be timing the whole thing. Once you jump, I start the timer, wait 15 seconds, then I'm going to signal your catch-up diver and let him go on after you.
All right, let's do it.
With Tori finally on board, it's chalks away.
I'm taking your tools.
But as the plane soars to its target altitude, our hero gets that sinking feeling.
Is it too late to change my mind?
Too late now. You're going out the door.
There's no turning back. Terminal velocity is about to take over.
The plane hit 15,000 feet. Tori's reminding himself to breathe and his eyes are bugging out. The tandem skydiver pushes him to the edge right outside the door. He jumps.
Tori and his buddy assume the spread eagle position. With twice the mass of one person, they need a small control chute so they don't go faster than Swayze's fall of 120 miles per hour.
10! I count 15 seconds in so that I can signal the catch-up skydiver to jump out after him. 15! He just soared down as fast as a bullet, and then everything just kind of went white.
After 15 seconds, Tori's already plunged 3,000 feet. But the specialist diver's bullet position means he hits an eye-watering top speed of 250 miles per hour. Can he reel them in? Incredibly, after only 20 seconds, and just as Tori's about to pop the chute, the chaser not only catches up, but actually overtakes them.
Oh my God!
Just like the can-do Keanu.
That was insane!
Nice! Dude! That was insane! So, did the guy catch up to you or what?
Yeah, we jumped out. 15 seconds later, he jumped, and right as we pulled our chute, he was like right next to us.
You're kidding!
You're darn tootin' he's not. the chaser traveled nearly 7,500 feet in only 20 seconds and caught up with Tori, just like the movie.
So it turns out, given enough altitude, you actually can jump and catch up to someone who has a 15-second head start.
How are you gonna top that one? I don't know.
Gravity is all about how masses mutually attract. The bigger the mass, the greater the gravitational pull. So you wouldn't want to be standing beneath, say, a falling car. But how about a falling coin? This next myth is an urban classic. At around 1,280 feet high, the Empire State was once the tallest building in the world. And it's home to one of the tallest tales in myth history.
The myth is that if you throw a penny off of a building this height, it'll embed itself in the concrete at the base of the building, or it'll hit somebody in the head and kill them.
The simple way to test this would be to toss a coin off the top and see. But if the myth were confirmed, Adam and Jamie would be busted. So instead, they have to apply some science in lab conditions.
We need to figure out how fast a penny would be going if it fell 1,280 feet, what kind of damage it would do. I think we need to go back to the shop and test it.
Calculations show that the terminal velocity of a penny should be between 35 and 65 miles an hour.
I used to be able to juggle them.
But complex equations aren't the MythBusters style. So Adam sets up a mini wind tunnel to test it for himself. At the bottom, wind speed is clocked at 65 miles per hour. Holes in the tube allow the air to dissipate, so the speed at the top drops to 35 miles per hour. If the penny stays in the tube, then the equations are correct. Bingo! Adam's one happy MythBuster. If only Jamie were as excited.
This matches the math, the complex equations that we have showing the velocity. I think we should go for a worst-case scenario, like 65 miles an hour.
Okay, works for me.
This is excited, Jamie?
Yeah, this is
We got a
game.
world first. It's going out on television that we did the experiment that showed exactly how fast a penny goes. No math, no ideas, no timing off a building. We got it right here in the lab.
It's great. Good job.
Enthusiasm isn't Jamie's strong suit, but he needs to get a penny firing at 65 miles per hour. And luckily, MacGyvering is right up his alley.
I don't like to go through a whole elaborate process and days of machining something only to find that it was the wrong approach.
So he quickly modifies an industrial staple gun into a penny firing pistol and modifies a penny to make it fit.
Whoops. We should get out of here. That's mercury vapor there. Well, that worked.
On the bright side, the pistol definitely fired. But how fast did that penny fly? Cue high-speed camera.
We've modified the staple gun to accept the penny. We're firing it and tracking it, recording how fast it goes.
So here's firing a penny into a concrete block. The penny traveled 3 feet in 16/500ths of a second, which amazingly is right on the money at around 65 miles per hour.
Terminal velocity gun right here.
Meanwhile, Adam is making a stand-in for the myth's unlucky passerby, using real bone wrapped in ballistics gel.
Okay, stop.
Jamie's improved the penny pistol to fire a full coin.
Damn, that is some serious impact there.
And they're good to go. This myth has been doing the rounds since the Empire State was built. Now it's finally about to be tested. First up, can a falling penny bury itself in pavement? In an instant, the decades-old myth is busted on both asphalt and concrete. But what about flesh and bone? The myth says a penny falling at terminal velocity would pierce the skull. This one's for the money.
Lights. Perfect hit.
The penny pierced the thin layer of ballistics gel, but the skull stays intact. unlike Adam's common sense. He's aching to see what happens when this penny hits skin firsthand, or first butt.
Go ahead, shoot me in the ass.
So here it is, Adam's ass on the line for science.
Oh! That hurts. Oh, man.
It's painful proof that at terminal velocity, a falling penny would kick butt.
You said I could. I always enjoyed seeing Adam in pain. I'm not sure what it is.
But lethal, it ain't.
So you made that great gun. We made the pennies go 64 miles an hour. What did we end up with?
Well, the myth's not looking good.
Okay, time to ramp it up to see if a penny can be made to go fast enough to do some serious damage.
Anytime we get to play around with explosives and gunpowder and, you know, cool weapons and things like that, here at MythBusters, we're happy campers.
So Adam sets about modifying a high-powered rifle.
Test firing.
The coin will be fired from a special aluminum barrel, attached to the rifle like a silencer. The rifle itself will be loaded with a blank round. When it's fired, the expanding gases from the cartridge will explode along the barrel, propelling the coin from the slot with bullet-like speed.
Firing in 3, 2, 1. The high-speed camera result apparently is 3,000 feet per second.
Well, that's like a bullet. That's the speed of a bullet.
But there's still no penetration. And there's your problem. Force equals mass times acceleration. Even at supersonic speed, a penny weighing just 2.5 grams simply doesn't have enough mass to break through concrete, asphalt, or bone. Unlike a real bullet, which in this case is 6.5 millimeters of solid lead.
1.
Now that's penetration. It's a face-melting finale, but the penny myth isn't worth a dime.
I hate when that happens. Eliminating all the things that are in the penny's way from just reaching the ground, 64 miles an hour just wasn't enough to cause any kind of damage to a person. And then when we made it go almost 3 times the speed of sound, it still wasn't enough to break the bones.
Yeah, I mean, the worst thing I can come up with is if you were looking straight up in the sky and you got hit in the eye, it probably wouldn't be very good for you.
I think we busted the heck out of this one.
Myth busted.
Yeah.
Time to switch track. From going down to up and away with some balloon-based myths. And beware.
These things are always catching on fire.
Once you pop, you cannot stop. For our first myth, Adam and Jamie are going to try and solve a decades-old balloon-based mystery.
So what's the myth?
The myth today has to do with the cause of the Hindenburg disaster.
In 1937, the giant German Zeppelin Hindenburg was coming into land when it suddenly burst into flames over New Jersey. 36 people died. History's largest airship was reduced to ashes in just 34 seconds.
Doesn't everybody know that that was caused by the hydrogen, which is the reason they don't fill blimps with hydrogen anymore?
Not according to our myth. Our myth states that the cause of the Hindenburg disaster was its skin, specifically the dope and paint on its skin.
The Hindenburg was filled with hydrogen, which is lighter than air, but its cotton skin was coated with a kind of paint called dope, which made the fabric taut and waterproof. The dope's ingredients included aluminum powder and iron oxide. Put them together, and they produce an extraordinarily explosive substance called thermite. Could it have been this paint, and not the hydrogen, that caused the fatal fire? Before building replicas of the ill-fated airship, they're going to investigate the chemical reactions at work. Adam builds a test box using the same cotton fabric and paint as used on the Hindenburg.
The dope-covered fabric that I've got covering this box for this test represents the top half of the Hindenburg. It is a layer of butyrate dope and iron oxide covered with 3 layers of butyrate dope and aluminum powder. Ladies and germs, here we go.
Hydrogen is pumped into the box, and Adam introduces a naked flame.
Whoa! Okay. Is everybody okay?
Yes, but we really think you should have more stringent safety procedures in place when you go bigger scale.
How big do you think we can go?
I don't know, like 10, 12 feet?
Well, if we go 16 feet, that's 1/50th scale. That's a nice round number. You think we can do that?
They'll build two 16-foot Hindenburg scale models and coat them with the aluminum iron oxide paint. One will be full of air, the other hydrogen. If the hydrogen Hindenburg burns faster, this myth is busted.
Look at that. That is very, very cool.
By following the original Hindenburg blueprints, the MythBusters are building blimps smoothly. Until Jamie decides to break out the welder.
These things are always catching on fire. That is the textbook definition of irony, kids.
The last thing they have to do is apply the dope, and the models are complete.
Now, we're gonna blow up some Zeppelins.
Their blimps are pimpin'. At 16 feet long, each model is 1/50th the scale of the actual Hindenburg.
We got these figures from a train set. These are 1/50th scale. Check these guys out. That's how big an actual person would have been with the Hindenburg. This thing was massive. This fire must have been just the most unbelievable thing that anyone that day had ever seen.
The blimp skin matches the Hindenburg's exactly, right down to the dope formula painted on its surface.
The first test is just the blimp without any gas, no hydrogen, and we're just going to burn the skin and see what that does.
To avoid another, is everybody okay moment, the room will be a strict no-go zone during the test. To set fire to the blimp remotely, Jamie rigs a blowtorch on a stand.
This is a test number 1. Period, correct skin, no gas. Ignite when you're ready. That looks good. You're right on target. It's going. That was quick.
The Hindenburg burned in 34 seconds. For the myth to be plausible, this Hindenburg has to be consumed in a similar time.
But yeah, we're already at 1 minute, 10 seconds.
So we could have burned 2 Hindenburgs by now, and we're only like not even a quarter of the way through this.
Suddenly, the flames take off like, well, wildfire.
Oh, wow. Wow.
Oh, yeah.
That is so beautiful.
Sparks cascade as the aluminum and iron oxide on the skin create thermite.
Bang. 2 minutes, 6 seconds.
It's a lot quicker than I thought it was going to go.
That's almost 4 times longer than the real Hindenburg took to burn. On to burn number 2. This dope-coated Zeppelin will be filled with hydrogen.
We're gonna feed it from the hydrogen tanks through this blue gas hose up the main strut and into a trough of water. And the trough of water is going to diffuse the hydrogen across the entire Hindenburg.
If this hydrogen Zeppelin burns faster than the first blimp, the paint theory will be punctured once and for all.
You're lit.
As the flames take hold, the hydrogen is fed into the mini Hindenburg.
Whoa!
More hydrogen. More.
And the blimp is instantly filled with flame.
What's our time?
Boom. Wow. 59 seconds flat. That just feels exactly like what we see in the newsreel. God, it's great.
He's right. Their test and the 1937 footage look eerily similar.
This is my favorite scale experiment we've ever done. Full stop.
The period skin plus the hydrogen burned twice as fast as the period skin without the hydrogen. Doesn't get much more definitive than that kind of result.
It's busted.
Yeah, but you know, the skin actually did have a fair amount to do with this. We saw that it does burn aggressively, and it was clearly a part of what was going on here. We even saw little bitty thermite reactions, which tells us that, like any good myth, there is a grain of truth to the fact that the skin had something to do with thermite.
But in the end, it was the hydrogen plus the skin.
Yeah.
We're calling this one busted.
Busted.
For our next story, Carrie, Grant, and Tori are investigating a very balloony myth that could also be baloney.
Two clowns are driving to a party. The clown in the passenger side has a big bunch of balloons.
What happens? They go out of control and crash the car?
Exactly. Now, the driver clown is wearing a seatbelt, so when they careen into a wall, he's fine. But the passenger is not.
But, and the balloons save him?
Exactly.
It's a myth that makes for one heck of a headline. But can a bunch of party balloons really act as an improvised airbag and cushion a potentially fatal blow? To simulate a crash full of clowns, they're going to drop a car from a crane.
All right, bring in the clown.
Now, we've calculated that if we raise the car 41 feet from the bumper to the ground, we can achieve a 35-mile-per-hour crash.
The dummy clowns are rigged with accelerometers. If their G-load passes 100, it means it's a fatal crash.
Now, the theory here is these balloons are going to act as an airbag. Now, the goal of any airbag is to slow the passenger's forward motion as evenly as possible in just a fraction of a second. I'm not sure these balloons are going to function that way, but it's sure going to be fun to find out. Okay, in 3, 2, 1. -1. Oh.
Now that is what I call a party. I don't think they survived it, though.
The high speed shows the passenger who wasn't wearing the seatbelt pushed past the balloon barrier and connected with the windshield. Not surprisingly, the stats show the balloons didn't save the clown's life. It experienced 350 Gs to the head and a 620 G load to the chest, over 6 times the survivable limit. But the myth isn't popped yet.
So it turns out an average bunch of party balloons is not enough to save your life in a car crash. But it's not such an outlandish idea. An airbag is an inflatable, and so is a balloon. Maybe there's a balloon out there or a configuration of balloons that we could make that would save your life in a car wreck.
To find out which balloons might be better lifesavers, Grant's going to build a balloon crushing rig.
Good. I've added this plunger right here with a 50-pound weight. Now, the idea is that we drop this onto each type of balloon. Using the same weight and the same volume of balloons each time, we can compare and find out which type of balloon absorbs the most energy.
First, a control with no balloons. The result is 100 Gs. Then the same latex party balloons used in the car drop,
2, 1.
which aren't much better than no balloons, at 98 Gs.
I'm making a pterodactyl.
Next, balloon animals.
Oh, that's a good one.
Yeah, it's an octopus.
Balloon animals in 3, 2, 1. That worked pretty good.
That worked better than I thought it would.
With a radical G-load reduction to just 6 Gs.
We got 6 Gs from the balloon animals?
Yeah.
All right, giant party balloons.
We got 2. I think we have winner.
I know, isn't that crazy?
That's awesome.
Reducing the G-load from 100 to just 2, these giant latex balloons are the winner. But could they save a clown's life?
This is like how we used to pack for family trips.
Take her up.
Now remember, if he goes over 100 Gs, the clown is dead, and so is this myth. All right, this is clown car drop with our best latex balloon. Here we go in 3, 2, 1.
Yeah.
Oh.
Oh my God.
I think it might have worked, man.
I think that clown may have survived.
Now, in the high speed, you actually see the cars start to compact. The balloons separate just enough for a clown face to peek through and a clown nose to dust the windshield and then start to go back into the car as if the balloons are bouncing him back.
All right, Byron, how'd we do? Did either guy get under 100 G's?
Now, you'll remember he sustained over 600 G's with just the party balloons. But this time, only 130.
It's a huge reduction, but there's still no way a clown or anyone else could survive that kind of G-load.
So it turns out, even with our best balloon, the oversized latex balloon, we were not able to save the clown's life. So this myth is busted, but we're not gonna stop there. This is MythBusters. It's time to ramp it up. So we're gonna go back to the shop and see if we can come up with some kind of configuration of balloons that could save the clown's life.
They test a bunch of different balloon configurations and combinations.
That looked really good.
The best turns out to be Grant's version of giant bubble wrap.
In 3, 2, 1.
Oh, we got a couple of pops, but hey, maybe more than a couple.
All right, let's see what we got.
You got 1.7.
Hey, that's great. Now what we need to do is make 15 or 20 of them and stuff them into every part of the car and see if it saves the clown.
Probably better if you don't watch.
In their final drop test, the guys stuff the car so it's literally fit to burst.
You guys are packed in there like sardines.
That ought to do it. Now, with this last and final test, we're trying to get below 100 G's on our clown. That is our benchmark for survivability. We have balloons on sheets of plastic. That way the clown can't push through the middle of the balloons, and if one little balloon breaks, it's not gonna create a big cavity where the clown can actually fall into the windshield.
If packing the clown car with giant bubble wrap doesn't work, nothing will.
All right, here we go. This is bubble wrap in 3, 2, 1. Oh. It did not look good.
Okay, so the passenger's head peaked at 220 G's and his body at 230 G's.
Wow, so the clowns actually experienced a bigger G-load than in the previous test.
So party balloons are not a substitute for airbags or seatbelts.
Stop clowning around.
For our final myth, Adam and Jamie are going to challenge a well-worn idiom.
Have you ever heard the expression, going down like a lead balloon?
You mean like, that'll never happen?
Kinda, but it more commonly means a joke that falls flat or an epic fail. In myth-busting terms, though, it's simple.
The myth is that it is totally impossible to make a balloon like this one out of lead.
And so we're gonna build one.
Lead's defining characteristic is it's heavy. That means it surely can't be made to float like a balloon. Or can it? Turns out impossible isn't in the MythBusters vocabulary.
This balloon is made of fabric that's extremely light and very strong. We're gonna be building a balloon that's very heavy and very weak. So, not so easy. Hello?
To stand a chance of making this work, they need a wafer-thin layer of lead.
Sprechen Sie English?
Turns out a supplier in Germany makes lead foil.
What this may look like is a box full of rolls of foil that weighs about 30 pounds. In fact, this is our lead balloon.
Oh, look, it's beautiful.
Beautiful, but very, very fragile.
The problem is this. It just kind of falls apart. It's like, almost like wet toilet paper. There's not going to be any room for error.
They build a quick prototype.
Ah, I found a tear.
And it becomes clear that the main challenge, aside from the weight of the lead, is its tendency to tear.
You're going to ruin it, aren't you?
The biggest problem that the lead is giving us is that it's delicate, and we can't go lifting up huge sheets of it to tape these complicated seams. So I'm going to try and design a way to make a cube so that we lay it out panel by panel, flat, and then we can inflate it. It works. All right. There it is. That's the deal.
With the design and construction map worked out, Adam crunches the all-important numbers.
Roughly 11 kilograms.
His design will require 640 square feet of lead, weighing the equivalent of 24 pounds. They'll use helium, the second lightest gas after hydrogen, to hopefully give the lead balloon lift.
Gonna make a lead balloon!
They're at the Alameda Naval Base to attempt to assemble and fly the world's first lead balloon.
We've chosen this because we got plenty of room to fly, we got no wind, we got a nice flat surface to build on, so this is gonna be like a medical procedure. Okay, everybody, this is no walk zone.
Here's the plan I worked out in the shop. It's 12 steps, 12 pieces of lead. Each square gets assembled over on the assembly square and then put together on the home square.
With rubber gloves to protect against what is, after all, a toxic material, the guys begin building the ambitious 12-step plan.
It is hard work.
Almost as bad as picking strawberries.
But we've got something strawberry pickers don't.
What we have here is the largest clear tape dispenser in the world.
Simply insert an atom to tape in all those awkward, hard-to-reach places.
I've never built anything like this before. The final result's going to be about 7 or 8 layers thick in some places. That's as thick as one of your hairs. That's how thin the material we're working with is.
It's painstaking work. 4 hours becomes 8, then 12.
It's all working out quite well right now. It makes me a little nervous.
Adam's origami-style model is coming together.
Slow down, slow down.
Everybody slow.
Okay, stop, stop.
And he's hoping after the final piece is taped into position, it'll inflate seamlessly.
I want this thing looking like a real inflatable balloon, like with a basket and with passengers. Yes, Jamie and I are gonna go for a ride in the lead balloon.
It's going up.
You gonna man the valves?
I'll do that.
All right.
Adam is understandably nervous. His clever design is on the line. And as Jamie opens up the helium, one thing's clear.
It's gonna take a while.
If that tape sticks someplace that it's not supposed to, if something catches, it can rip, it can tear, things can come apart. This is the hard part.
With the ever-present chance that a tear could quickly turn this into a disaster,
I'm nervous.
Jamie starts filling the cube not just with helium, but with air as well.
We're putting air in this because we think we actually have too much buoyancy. We want it to just barely come off the ground, otherwise we're liable to rip something.
It's looking good, it's looking good.
At last, the genius origami structure slowly comes to life.
I don't see any major holes, I don't see any major failure points, but I'm keeping a close eye on it.
Hey, Adam.
Yeah.
Congratulations on the design. It unfolded and twisted out just the way it was supposed to. Whether it flies or not, I don't know, but your plan worked.
I'm really psyched about this one.
But as it gets bigger, rips and tears appear everywhere.
I got a hole. Hold on to it, hold on to it. Hold on. That's it.
Thanks to Adam's patching jobs, their lead balloon is airborne.
I still want more balloonness out of it.
I know.
Finally, it's time for the test. Will the lead balloon actually float with a basket and mini MythBusters attached?
Dude.
That is a lead balloon.
I am really pleased. We might have been able to get away with a smaller balloon, but this is a lead balloon. We did it.
That worked beautifully. It's perfect. 11 kilos of lead hanging right over my head. And if I let this go, it's going up. It's just amazing.
Well, I tell you, that might be ridiculously impractical, but, you know, if someone says it's impossible, we just take it as a challenge. Busted idiom.
Don't try anything you're about to see at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This won't hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode, the team put themselves on the line as everyday accidents are put to the test.
This is gonna be a horror show.
And later, myths about some very weird weapons are lying in wait.
Death and destruction.
Fire.
It's chaos,
We have to hurt this boat.
carnage,
Watch out!
and catastrophe, MythBusters style. First up, could this innocent Sunday ritual ruin your neighbor's day?
Oh, crap.
It's Sunday morning. It's time to mow the lawns. Your lawnmower goes over some rocks, kicks it across the street, kills somebody. The idea is that a rock kicked by a lawnmower can have an equivalent amount of force as a bullet delivered from a .357 pistol.
Lethal lawnmowers. I like it.
Potentially lethal projectiles are a possibility, so they get with the program at a gun range, where they roll out the green carpet and spice it up with stones to create the lawn from hell.
This is gonna be a horror show.
To complete the Nightmare on Myth Street scenario, Jamie fashions some friendly foam targets. Neighbors.
If any rocks come out of the mower with any force, this foam is soft enough that it should easily show it.
Most mowers have stone guards, but this myth points to a poorly maintained machine, so bye-bye.
There we go. Safety feature removed.
That's a sin in the safety manual. Is Adam about to cast the first stone?
I start out and I get into a rhythm. It's the most terrifying rhythm I've ever been in. I actually ended up by turning my entire body away from this firestorm of little tiny pebbles. One even flew up in the air and landed on my hat.
Good Lord!
The lawnmower goes quiet, but over the fence, all hell's broken loose.
Hit, hit, hit.
That went all the way through.
Wow.
It just goes to prove the point, MythBusters make lousy neighbors.
I'm amazed.
But did the stone strike with bullet-like force as per the myth? To find out, they need laboratory conditions and a killer lawnmower calibration rig.
This thing's stuck.
In the interests of relative peace, quiet, and safety, Jamie does an Elon Musk by removing the gas engine.
And we got it.
Hooking the mower up to a power welding machine and turning things electric.
I love it when things actually work the way you hope.
That's amazing. All right.
The plan's simple. Power up the blade to the top speed of a regular lawnmower, drop it on a rock, and observe how fast it flies on high-speed camera.
You ready?
I'm ready.
Well, let's do this.
18, 32, 34, speed.
Here we go. Dropping a lawnmower onto a rock. 3, 2, 1. Cut it.
The blade moves so fast, it strikes the stone 3 times.
Oh, wow, just absolutely decimated that piece. The fastest chunk was going 250 feet per second, and that's actually pretty significant for a chunk of rock about 1 inch long and a ½ inch wide.
250 feet per second is 170 miles per hour.
Okay, so we got a whole pile going in.
Now they're giving their mower more to aim for.
Dropping big pile of rocks. Cover your eyes. 3, 2, 1. Cut it. Everybody okay?
Chunk. Chunk made it out.
Well, I hope we got the shot because that was the sound of the blade coming off of the motor.
Oh, really?
Yeah.
The high speed shows 1 clean hit.
Boom.
400 feet per second. 272 miles per hour.
Well,
I feel like we're in some very dangerous territory.
Which is right where the MythBusters like it. But is this territory as dangerous as a bullet from a .357? Before they left the gun range, Jamie did a spot of data collecting.
the .357 went at 1,400 feet per second. Now, the fastest rock we got off of our lawnmower went 400 feet per second, which is nowhere close.
But it's not busted right there. No, 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 because while this rock is bigger and slower than this bullet, it's heavier. What I'm wondering now is there a rig I can build that can compare the amount of energy the bullet brings to the equation and compare it to the amount of energy the rock brings?
The answer is an ingenious yes, in the shape of an impact pendulum.
Let's take a gun and shoot the face of this hammer. What's gonna happen? It's an indicator of how much energy the bullet brings to the equation. Now, if I fire a stone at the same hammer at this speed it would be kicked by a lawnmower, and the hammer moves the same amount, well, then we could conclude that the amount of energy being brought to the equation by the bullet is the same as the stone.
Well, that looks nifty.
With the Hyneman stamp of approval, it's back to the gun range.
Gun is hot. All right, 357 on your mark.
And 3, 2, 1.
The pendulum peaked at 60 degrees, marking the energy delivered by a .357 bullet.
We've got the data we need to move on to stones out of a lawnmower.
Now, if you thought that means no more guns, then think again.
Wow. Because stones from a lawnmower are hard to aim, and because Adam's pendulum target is very small, we're going to take the lawnmower out of the equation and use a pneumatic launcher instead.
Before long, Jamie has it firing at around 400 feet per second, the same speed as the stone launched by their Elon Musk mower.
406.
Seriously? Awesome.
Time for the final showdown.
Good to go. Firing in 3.
A stone lies hidden in the grass.
2.
The lawnmower approaches.
1.
Stone flies out at 400 feet per second.
Dude, I swear that went past 60 degrees.
All right. See how high it actually went. Wait. Oh my gosh, dude! Dude!
It went above the 357.
That's 66 degrees. That's more energy from the rock. I'm sorry, I'm yelling, but I totally didn't expect this result. That is more energy from the rock than from a bullet from a 357. That is amazing. Shocking. Totally awesome.
I knew lawnmowers were scary. I just didn't know how scary. So with everything that we tested, I think we have definitively proven, and frankly, I'm astonished by this, but that a rock thrown from a lawnmower can possibly have as much or more power than a bullet from a 357. This one's confirmed.
Bifurcation from above.
3.
It's a deadly myth
2.
from out of the blue.
1.
Literally.
Ah!
The myth is that if a pane of glass falls out of an office building and you're unlucky enough for it to find you on the street, it will shing, cleave you right in twain.
Well, I don't know about that, but whatever happens, it ain't gonna be pretty. For us to do our glass guillotine experiment, ideally, we need a human. I asked for some volunteers from the shop crew, but nobody stepped up.
So Jamie's making his own gel-based volunteer body double with some extra human flesh features.
This is a polyethylene material, and it actually rips, just like flesh will rip.
Getting a human-like texture for their torso is critical.
There we go.
Adding bags of blood? What's not to like?
Lower down.
And with the gel mix molten,
it's all looking good.
Ta-da! Hey! Oh, he looks a lot better than I was afraid he'd look.
With fresh flesh all set,
hey,
they're good to go.
This is the Santa Rosa Fire Department's fire training tower. Today,
I hate heights.
we're gonna be dropping large panes of glass onto unwilling ballistics gelatin test subjects.
So we've got a 4-foot by 6-foot piece of 3/8-inch thick glass, like what they would have on top of a high-rise. And I'm gonna hoist it to 75 feet.
Good.
Where Adam and I are gonna drop it.
But it's not just any kind of glass.
The glass in an office building is called tempered glass. It's made to be very hard, and it also doesn't break into shards. It actually breaks into many, many thousands of little tiny chunks, kind of like this.
This could get messy.
Man, this is scary.
Yeah, that's it. Jamie, this is working beautifully.
What we are looking for from the glass here is not whether or not it kills him.
Okay, now, I figure we hoist it over our heads.
Yeah. 3. It's that it would cleave him in 2, 1.
And it's a bull's ass.
Oh! I'm like, oh my God, it's gonna hit him. It's gonna hit him. And then what feels like just before it got to our dude, it went like this and hit the ground perfectly flat and spread in every direction.
Oh my goodness. It looks worse down here than it did up there.
When I was like 10, I would have taken these home and pretended they were diamonds and pretended I had treasure.
I would have sold them to the neighborhood kids and made a profit.
Either way, this myth is going to need a bit of a helping hand.
What do you think? Should we head back to the shop and make a system for guiding the glass?
Yeah, I've got some ideas.
Me too. Ta-da! I know it doesn't look like much, but check this out. This coat hanger will be a welded steel rack which we sit on the lip of the building.
We're clear.
These red pieces of parachute cord are guide wires which we mount to the ground.
Awesome.
The glass has riders on it that keep it aligned with the guide wires.
They say the glass is tempered, but is it bad tempered?
We bring it up with a winch.
Go ahead and winch up the glass.
Oh, here she comes.
Drop it from the top and tink! It hits our test subject square where we him to and slices him right in half. Or not. That's what we're gonna find out.
So is this just a perilous pain, or is it a glass guillotine?
It is really just about to happen. I can't wait to see this.
In 3, 2, 1.
There it comes. Ah! That was perfect.
It's a direct hit. But did it divide, or merely conquer?
He's still in one piece.
It did not cleave him in twain. It merely beat the living crap out of him. But there's still only one dude. There's not 2 half dudes. Gotta try something else.
To make 2 dudes from 1 dummy, they're gonna need something that packs more punch than tempered glass.
For that, you've got to move to plate glass. Now, they don't use plate glass in office buildings specifically for this reason, but for due diligence, we've got a piece of plate glass here.
With a jagged edge or two added just for effect.
Oh, now it's coming.
This myth is heading for its sharp end.
In 3, 2, 1.
Here it comes. Oh, it's good, it's good. Oh! That was beautiful. Oh. Dude, that would be cleaved in twain.
Not quite a bullseye to the brain, but in twain, he truly is.
Dude, that's amazing.
So, myth busted, confirmed, or split decision?
Can glass falling from a high-rise cut you in two?
If it's the glass they make high-rises from, then no, it's not gonna cut you in two. It's gonna kill you, but it's not gonna leave you in two parts. But if it's the wrong kind of glass, then absolutely it can leave you in two big chunks.
So right kind is busted, but wrong kind is plausible.
Plus say plausible.
All right, I'll buy that.
All right, let's get out of here.
We've seen how lethal a lawnmower,
I totally didn't expect this result,
and plate glass can be
cleaved in twain.
But could the humble tissue box also end in tears, or worse?
Killer Tissue Box says that this tissue box could potentially be deadly. That in an auto accident, if it's sitting on the back shelf of your car when you collided with something, it would be propelled forward with enough force to actually kill you when it hit your head.
Let's try. I don't think this is gonna kill you. What do you
No,
think?
I didn't really feel it. Try again. Okay, started to feel it right about there. Shall we do this full scale?
All right, why not?
The ultimate test will be devastatingly simple. Take a car, insert a tissue box and a buster, and drive it into a wall at high speed. But they want to do multiple tests. So first, they need a repeatable crash test rig.
Are you gonna cut this off?
No.
Oh, okay.
And in the spirit of whistle while you work, Jamie has a fun fact about backseat items that go ballistic. In just 1 year in the US,
13,000 people were injured by unrestrained objects in the back of the car during an accident.
ouch, this myth has wheels after all. So a human stand-in is called for, in the shape of ballistics gel in a box.
Hopefully, when this car stops, the ballistics gel's not going to tear itself out of the mold.
Some finishing touches that probably won't survive the first test.
That's good.
And this myth is wheels down and ready to roll.
We're in Alameda, California on an unused naval airstrip. We need a long, straight, open run.
To replicate an accident, they've got 1,000 feet of cable. One end attached to the crash test sled, the other to 3 concrete barriers, which will act as an anchor. So when the cable is pulled taut by the tow car, the crash sled will come to a whiplashing stop.
Slow it down.
All clear? Let's crash on.
Well, we've got our back seat here, and we've got our ballistics gel making a head here. The tissue box is going to go on the back shelf, and on impact, it's going to travel forward and hopefully hit our ballistics gel. With our meter here, which has got 1-inch markings, we should be able to see exactly what its velocity is and calculate how much force it's imparting to someone's head.
First, a quick run through to test that the crash test rig will actually crash. Nope. Instead of snapping things to a sudden stop, the cable snaps off the rig.
Damn it!
Take 2. And take 3.
I don't know what we're gonna do.
I thought I made a good rig, but I was wrong.
The solution, some huge ratchet straps to strengthen the sled.
Jamie?
Yeah?
I think this is a really good solution.
And they're ready to put their reputations on the line. or cable.
Come on, come on, come on. Right there, I want it to stop right there. Yeah! That's what I'm talking about.
Perfect.
Exactly 45 miles an hour, over.
MythBusters now has a mostly working crash test sled. I'm very pleased, yeah.
But before they test the terrifying tissue box, they want to try out some other random rear shelf objects.
Well, this one's definitely the heaviest.
Right.
And so there's an argument to be said there that it could crush your head. This one also is fairly heavy, and then maybe this one could break your neck even if it doesn't crush your skull.
If the myth is correct, this tissue box is at the top of our lethality pyramid.
First up, how much bite does a 2-pound subwoofer have in foot-pounds of kinetic energy?
Here it comes.
It's a direct hit at a beam-busting 45 miles per hour.
It pretty much would have hit you dead on in the head. We'll have to crunch the numbers to find out how hard, but it was a pretty good hit.
The impact measures 135 foot-pounds of energy, enough to seriously addle your brains, but you might survive. Next up, a regular 3-pound fire extinguisher.
That looked like a perfect hit.
With a kinetic energy of 203 foot-pounds, the driver could be extinguished.
There's your proof. If I whacked you on the back of the head hard enough to do that, you'd be hurting.
Next, they go way over the top with a 10-pound bowling ball. This should be quite a strike. Bowling ball? More like a cannonball. 676 foot-pounds worth of cranium-crushing impact. So that's 3 hits and 3 trips to the ER. Or worse. But back to the origin of this myth, the half-pound tissue box. This is it. It's time to
find out if this is actually deadly.
And at 45 miles an hour, its kinetic energy is a measly 33 foot-pounds. Just headache material, if that.
There's just no way. I mean, we tested a whole bunch of stuff. The bowling ball went right through this whole rig. Tissue box.
It might be like, ow.
This myth's already a sniff away from being busted. But finally, for due diligence, they're going to do it again with a real test vehicle, complete with buster and a tissue box. All towed by Jamie right at the speed limit.
Okay, this is the 70-mile-an-hour test. This is maximum speed, over.
This time, the target is the concrete barriers. So it's a one-shot deal.
The car looks great.
And at 70 miles an hour, cue manic laughter. It was a bullseye for the car, but the tissues flew up and hit the ceiling, not the driver. And the box survived intact. The cardboard's not crumpled. There's not even a single torn tissue.
Looks pretty good.
You know, that's a good indication that this is really deadly, though. That's the one thing in the car that's tough enough to survive an impact.
So on that note of heavy sarcasm, what's the verdict?
Jamie, I think killer tissue box is definitively busted. Even if you had a decorative plastic or metal cover on this thing, it just doesn't have the mass to inflict lethal damage.
Modern life is full of accidents just waiting to happen.
Cleaved in twain.
But the ancient world was jam-packed with some very weird weapons.
Watch out!
First up, might this be a medieval missile from the Middle East?
That didn't go at all like I expected.
Dude, it turns out that the torpedo might have been invented in Syria in the 13th century.
Really?
Well, this, in fact, was a rocket-powered device that skimmed across the top of the water, delivering an incendiary
to its target.
Did it work?
We have no actual record of them actually using it. All the accounts generally agree on the overall shape of this torpedo, that it is pear-shaped, and that it's powered by a black powder rocket of about 20 pounds of powder.
Well, why don't we go down in the shop and each take a stab at it and see what we get?
To test this myth, first they build 2 small, epoch-appropriate copper prototypes to see which design works best. All they know for sure is this surface torpedo was apparently pear-shaped. Spoiler alert, with 2 fins extending out. Methodology, medieval and modern.
I'm using every sheet metal production tool I have ever purchased, from synthetic hammers, planishing hammers, motorized planishing hammers, anvils, beater bags, everything.
And I've got a cannonball.
Jamie's stone tool technique turns out a flat-bottom torpedo, while Adam's modern methods manufacture a V-shaped hull. With their 2 different designs at the ready,
we'll see what happens.
It's time for a head-to-head.
Well, that thing's looking pretty snappy.
I'm pretty psyched about it. Can't wait to try it. How's yours?
It's not quite as pretty as yours is, but it ought to work.
To try out their torpedoes, they shoot off to Treasure Island, where they set up a test range with a target at 100 feet. First on the launch pad, Adam's deep V design, plus black powder model rocket.
It's just sinking into me what we're doing. Crazy. In 3.
Time to roll back the centuries.
1. There it goes.
Look at that. That was lovely.
But not very warlike, unless your enemy is 30 feet away and around a corner.
Any suggestions?
You could strap 2 rockets onto that rocket mount, because I think you're just not getting up on top of the water. It may be that you just don't have enough power.
Of course, when in doubt, add more power.
In 3, 2, 1. That was awesome!
Well, the twin jets do get things moving, but this weapon definitely dresses to the right, so there's no V for victory.
Yeah, that hull shape doesn't seem like it's working very well.
The fact that it's spraying so much water around says that it's wasting a lot of energy.
Yeah.
So it's Jamie's turn in the Syrian spotlight. Flat bottom hull, 1 model rocket.
Here we go.
Ooh. Clearly, it harbors dreams of being an underwater torpedo, but Jamie's unfazed.
I figure all I have to do is bend these tail fins with a slight downward pull to them, and that ought to hold the front end up.
Take 2, with 2 rockets.
This one's for the gold. There you go. Come on, baby.
It's not perfect, but it's clear. The flat bottom kicks butt.
I think we have our design.
It goes pretty quick, doesn't it? Okay, let's get out of here.
Time to go full scale. And Jamie's had a dazzling idea for turning sheet metal into Syrian torpedoes.
I'd heard about this technique called hydroforming, where you use water pressure to form sheet metal shells. We take our piece of sheet metal and clamp it between 2 massive plates of steel. We've cut out an almond-shaped hole in the top plate and attached our pressure washer pump to a small hole in the bottom plate. Now here's the fun part. All we do is start the pump, and the water pressure pushes the sheet metal out the almond-shaped hole, inflating it just like a balloon. Ha! It's perfect. Beats beating on it with a hammer.
The production line swings into gear, and the shells are turned into torpedoes, complete with rocket casings, flotation foam, and control fins.
I think our torpedo army is ready for deployment.
Time for a road trip?
It is.
Shall we get started?
Yeah, why not?
Let it drip.
An enemy boat is moored 800 feet from shore, well out of range of any ancient archer. The torpedoes are painted Damascus Dayglow. and the modern equivalent of the myth's 20 pounds of black powder slides into place.
This is an M motor. It puts out 270 pounds of thrust for approximately 14 seconds, and it will be our ye olde rocket engine.
Remember, the myth says that the torpedo delivered an incendiary device, destroying its target by fire. But first, they're testing without payload for accuracy.
Okay, in 3, 2, 1.
As Jamie would say, whoops.
Well, I don't know. Maybe that was a little too powerful. What do you think? Everything seemed to go haywire. It spiraled up into the sky and did this massive belly flop.
It was fun, though. Let's do it again.
Maybe that first test was just a misfire.
Fire.
Or maybe not.
It was like a porpoise. Yeah. It kept going up and then down underwater and up.
To try and get this myth on target, they tether the torpedo to an underwater guide wire tied to the boat.
Fire.
Oh, shoot. That didn't go at all like I expected.
Next, they bring the target closer and raise the guide wire above the water.
I really hope this works.
Come on! No!
But the torpedo heads for the hills.
Maybe we should just go home.
No! We have to hurt this boat. Darn it!
Fire.
It's a deeply disappointing day.
This is starting to get me upset.
Fire.
Of failure. After failure.
Bugging the hell out of me.
After failure.
Captain Kirk never said this to Scotty, but I think we've got too much power. We're going to go with a rocket motor that puts out about half the thrust.
With patience and daylight running out, they arm the torpedo with its gasoline payload.
10.5 pounds of death and destruction
for one final Hail Mary.
In 3, 2, 1, fire!
There it goes! Come on, baby, come on! Hit it! Ah! Just boom!
That sent fire up over the bow of the boat. That was awesome.
Holy crapola! Skipped beautifully on the surface and slammed into the side of the boat.
Delayed gratification. Hard to beat.
Well, how do you want to call this one? Was the Syrians' mythical surface, rocket-powered, incendiary-delivering torpedo been an effective weapon of war?
Indeed it was, based on this test. We have to call it plausible, don't we?
It's plausible. Let's get out of here.
All right, you guys, this next myth is gonna be insane.
What is it?
That's it, the hatcha. It's an ancient Korean weapon. Oh.
But if there's a picture of it, that means it's not a myth, it exists.
Well, we know it exists. What we're gonna test is the legend of the hatcha, whether or not it could do what they said it could do. Apparently, they could fire 200 arrows all at once, going 500 yards, and all of the arrows explode on impact.
It's a massive Oriental myth with 3 key components. 1, distance. Can a fire arrow actually travel 500 yards? 2, detonation. Can it be rigged to explode on impact? And 3, destruction. Can you really set off 200 at once?
So what I'm gonna do right now is I'm gonna build one of these arrows from the materials that the ancient Koreans would have used. I have some bamboo, I have some feathers for my fletching, and finally, a piece of steel to make my arrowheads out of.
Displaying secret fletching and blacksmithing skills, Tori assembles his ancient arrow.
Now it's time to see how it flies. Pretty dang good.
Easy. 1 down, only 199 to go. And with the arrow prototype sorted, it's off to see if they can make them fly. A safe distance from civilization, Grant and Tori set about making black powder rockets.
Don't hit it too hard, man. I'd hate to see you blow your hand off. Hey.
They knock up a bunch with varying amounts of black powder and head out to the battleground.
This is perfect. I mean, can't you just imagine an invading army coming out of that forest?
They pace out 500 yards and set up a target.
This is gonna be perfect. We're right at the tree line.
To see if their arrows can match the myth for distance.
After it lands, you run out there and stand over where it landed. Got the rangefinder, and I'll take a range on you.
Quick, they're charging!
Oh, yes! That was nuts!
It's a flying start, but not far enough.
The arrow only made it to 290 yards. We're not stopping until we reach 500.
For round 2, they double it up to a twin-engine arrow.
Come on, baby. Come on, watch out.
Come on, come on! Whoa!
Oh! That's 500 yards, buddy.
That went the distance!
Success, 500 yards. Tick. So it's back to the shop for part 2 of the myth, detonation. To test if a flaming arrow could butcher its target, a side of pork plays the enemy.
Ah, you filthy little pig.
They insert an arrow with gunpowder payload that's wired for detonation.
In 3, 2, 1.
Oh, wow, that's good. Wow, look at that, burning of flesh.
All right, but as far as making it a mortal wound that explodes inside you?
Yeah, the arrow itself is probably gonna do more damage than the explosion.
Yeah.
The arrow's not meant to scorch the enemy, it's meant to blow it up. So they repackage the payload for round 2.
3, 2, 1. Oh. Whoa! Ow!
That's a little more what you were looking for.
2 tests, 2 very different results.
Whoa! Now, before we had a thin paper tube, the tube blew out and all the energy was being released. In this test, we sealed both ends of the container. Ba-boom! Big wound.
Distance and detonation done. Now it's time for destruction. Can the hatcha really fire 200 arrows at once? It's early morning on the day of battle, and Tori's been secretly working through the night.
For the hatcha!
There you go.
Yeah.
It's free.
Constructed from original Korean materials of bamboo and wood, it's the launch platform for the flaming rockets.
Let's measure out 500 yards and set up your army.
Drafted. Drafted.
It's a good thing you got a light infantry.
Oh, how long you been saving that one?
Faced with a foaming enemy 500 yards away, it's time to charge the rockets, all 200 of them.
You ready to load the hatcha?
I'm getting excited. This is actually the coolest ancient weapon we've ever made. I think it's gonna take down the army. I'm guessing at least 50% go down.
A bold battle cry that's got the enemy infantry trembling in its boots.
All right, buddy, let's do this. Get it.
Let's light the fuse on this flaming myth.
It's going. Another 30 seconds. You can see multiple fuses going.
It's the launch of a lifetime. A fiery spectacle not witnessed in 500 years. And every arrow but one took flight.
That was fantastic. Just seeing all the rockets come out of the watch at once, beautiful thing. Seeing that would be terrifying, absolutely terrifying.
The army is still standing, but on closer inspection, so is the myth.
They've all grouped right over here.
We only had 50 soldiers. Imagine if we had like 3,000, 30,000, 300,000.
She's right. A full-size army, and this would have been carnage.
That was a success. I mean, we got all the arrows to fire off except for one. We would have killed this army.
Next up, can you turn a log into a lethal weapon?
This myth is from medieval times, actually, and it involves a Hungarian town called Pykrete that was being threatened by their neighbors. So the entire town got together. In one night, they apparently made a cannon out of a tree. The entire body of the cannon exploded, killing half the townspeople.
It's two myths for the price of one. Could our Hungarian bombardiers have made a cannon from a tree? And could it have blown Pykrete sky high in a catastrophic misfire? For authenticity, first they need a tree type that was common in medieval Europe. Dutch elm fits the bill.
Jamie, you're doing such a good job.
Get out of my way.
And in line with the myth, they're going to forge their cannon the old-fashioned way, with ye old-style tools.
Getting a little workout this morning.
While Jamie strips down to strip bark by hand, Adam knocks up a 14th century bow saw.
Now there's some medieval workmanship.
Their research suggests the body of the cannon needs reinforcement. So with the help of some blacksmith buddies, they wrap it in red-hot bands of iron.
That's the ticket.
Oh, it's good.
And rivet them in place.
Yeah.
Oh, it's beautiful.
As the metal cools, the bands contract and tighten.
Yeah, that's it. That's it.
All right.
I got it.
Now for the pointy bit of this build. A drill to turn a log into a gun barrel.
Hopefully I'll make something that resembles a spoon drill, which is one of the first drills that they used.
Unfortunately, it soon becomes clear where this drill got its name.
We're about ½ an inch in.
Because it's about as effective as, well, a spoon.
I need somebody with a whip and a drum.
With 5 feet to get through, boring this hole is just too boring.
Based on what I'm seeing here now, I'm thinking it'd probably take a couple of days to get through it.
So Adam takes a knife to the spoon drill.
I'm not doing anything that the Pykrete wouldn't have done if they had had a chainsaw.
While Adam abandons medieval methods in the interests of modern myth-busting, Jamie clings on to the Middle Ages.
I'm making a cannonball out of granite.
You may be thinking pigs might fly. But as Adam barrels his way through with 21st century power, a perfect stone sphere slowly emerges. The 14th century wooden weapon is finally finished.
That is a tree cannon.
And that's a handmade cannonball to go with it.
It's so far beyond anybody's experience that we're all kind of blown away.
Just goes to show what's possible when you're hundreds of years old. So, locked and loaded, the MythBusters head off armed, dangerous, and set on destruction. Their firing range, a disused naval airstrip in Alameda on San Francisco Bay.
We don't want to drop this, do we?
Good news, there's plenty of gunpowder.
You ready to load some powder there, Jamie?
Yeah, let's do it.
All right.
They're starting with 2 3-ounce cartridges.
Ah, we are in the load.
And a tennis ball for a test run.
Fire in the hole! 3, 2, 1. Boo!
Wow. Is that a flaming tennis ball? That was a good bang.
Yeah.
The tree cannon aced its first serve.
Well, the tennis ball went a little more than a football field in length, which for a tennis ball is a lot.
Fired up by that result, they doubled the load of gunpowder.
Loading the cartridge.
And stepped things up to Jamie's hand-carved cannonball.
Satisfying a little thunk.
Fire in the hole.
It's 100% medieval, a tree, stone cannonball, and gunpowder.
I don't have a clue where that went.
I didn't see a darn thing. Did you see anything? Wow.
Well, it definitely fired. And the barrel is empty. They've proved you can make a cannon out of a tree.
It's a long way.
Really?
Yeah.
But Jamie's cannonball is long gone.
I'm a little bummed out not to find the ball, you know. I put a lot of work into that thing.
Cheer up, Jamie. There's a big boom coming. Remember, the myth says that the tree cannon exploded, destroying the town. Time to overdo things.
Well, we put 6 ounces of powder in last time. What are we going to put in this time?
5 pounds.
Whoa.
Yeah.
On a danger scale of 1 to 10, this is an 11. Make that a 12. They're sealing the end with an aluminum plug to simulate a blocked barrel.
If this doesn't blow up this cannon, I don't know what will.
This is basically going to be a bomb, and there's going to be splinters going everywhere.
The team backs up to the fence. And we're back in Pykrete over 6 centuries ago. Could the town really have been wiped out by its tree cannon? I'd say that's a definite yes.
Is everybody all right? I mean, like, the heaviest parts go farther than the fence.
That was a bit too close for comfort, because clearly tree cannons can explode with frightening force.
There's a little black on the ground around where the cannon was, and that's all that's left.
1 busted cannon, 2 confirmed myths.
My God.
They've proved a cannon made out of a tree will fire, and it could misfire with catastrophic consequences. So maybe the best advice for the good people of Pykrete should have been, run!
Don't try this at home.
Well, there's your problem.
In this special series of MythBusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. On this episode, it's one giant leap for humankind with 3 myths about the body.
Hey, we got one!
And later,
Oh, boy!
it's the call of the wild
That result was pretty shocking.
as we release the beasts.
Hell yeah, I'm nervous.
Humans and animals come together, MythBusters style. For our first myth, Adam and Jamie are delving into a very twisted mystery.
The myth is that a human, when blindfolded, cannot travel in a straight line.
Really?
This experiment will require some field work.
We've got a field in which we can walk 3,000 feet in any direction that we choose. We've got a blindfold. This one here is from my personal collection. And headphones to remove any other stimulus. And we're just going to try and walk in a straight line and see what happens.
We've got 3 ways of telling how good we are at walking in a straight line while blindfolded. First is by using the Global Positioning System, or GPS. Secondly, we've got these lovely little orange flags that we can place. You ready to go?
What? I think I may veer to the left or to the right,
but I think I'll end up pretty close to my goal of that cluster of trees over there. Or is it there?
Adam's confident.
Okay, blindfolded walking. 2, 1, go.
It is a very weird thing to be walking without any visual or auditory stimulus.
What's really weird is how surprisingly difficult it seems to be.
I mean, tickling at the back of your mind, you're thinking something might be wrong, but try as you might, you feel like you're walking straight.
Whoa! Whoa!
You started out pretty nice, but after about 300 feet or so, you started to turn to the left, and you just kept doing that until you ended up right back at the fence.
I swear I thought I was walking a perfectly straight line. Nothing told me that I was possibly walking in a 200-foot diameter circle. I am totally amazed by that result.
The astonishing disparity between Adam's perception and his actual route is there for all to see.
That is hilarious.
It's an outcome that begs several questions. First of all, will Jamie do any better?
Jamie's blind man walking in 3, 2, 1, go!
And any doubt that subtle topographical features caused Adam to go left are dispelled. As Jamie leans so far to the right, he's turned back on himself in a corkscrew pattern.
I ended up right back at the road, just like you did.
Walking in a straight line is apparently not doable without your eyesight. But what about other forms of travel?
What's next?
Swimming blindfolded.
Each of us will take a turn putting on a pair of blacked-out swimming goggles. Then we'll see if we can swim a straight line from here to the reflector across the lake.
GPS me.
Will the water smooth out their wonky route?
Oh, it's cold.
Or only make it worse?
He's swimming around and around in a corkscrew.
For me, the really enjoyable part isn't how far off course Adam is straying,
I must be close.
but that he thinks he's nailing it.
I feel like I'm doing pretty good. In my mental landscape, target's still right there.
No, Adam, it isn't.
Take a look at Adam's GPS trail. He made 3 complete circles, almost the same size. And what that tells me is that he's got some bias to swim in that direction. And unless he has vision to straighten that out, that's just what he's going to do.
And Jamie's no better at going in a straight line, putting on a truly dizzying display.
Well, Jamie didn't fare any better than I did in attempting to swim in a straight line. In fact, he fared far worse.
What else can they probably not do in a straight line while blindfolded?
Driving.
I love it.
Maybe a machine will eliminate the foibles of human biomechanics and finally get them on the straight and narrow.
I don't think it's going to be very hard to drive in a straight line.
Go.
I think all I need to do is align the wheels and not move my hands.
I'm holding my hand steady, but I can't shake the feeling that I'm drifting to the right.
Interesting.
Adam's supposed to be heading towards the distant city of San Francisco.
Okay, you're gonna have to stop. Well, you can open your eyes.
I was drifting to the left?
Yep. Want to try again?
Absolutely.
2 further tests only confirm the fact that driving in a straight line is not as simple as holding the steering wheel steady.
I feel a terrain change. I think I'm in trouble.
If this is how he drives a golf cart, I'd hate to see his tee shot.
Whoa! It drove us into the middle of a field.
No straight lines here.
Nope, and the GPS data shows that perfectly. And Jamie's equally inept.
Even in that machine, the kinesthetic feedback we're getting from the world forced both Jamie and I to make corrections. And these corrections were based on a map of our landscape we had in our head, which wasn't correct, and thus our corrections were incorrect and sent us careening all over the runway. Even driving, we could not make a straight line.
There's no rhyme or reason as to why we can't do it. But the boys have proven that without our eyesight, humans can't go straight. Next, we're going to figure out if there's any factual basis to the phrase, getting cold feet.
Oh, meaning that fear prohibits you from doing something you thought you could do.
Exactly. Like I was gonna jump out of a plane, but I got cold feet.
Well, it sounds like the question for us is, do your feet actually physically get colder as a response to being afraid of something? Okay.
Step 1.
KB, you are 96.3.
Find out what everyone's regular foot temperature is.
So we just took the temperature of our feet, and we're all averaging around 96 degrees. That's gonna be our baseline. Now, it's time to scare each other.
Knowing about Tori's fear of heights, Carrie and Grant have organized a stunt plane that they hope will send his fear into the stratosphere and freeze his feet to boot.
Oh my God.
Okay, now he's just showing off.
Well, if he's trying to scare me, it's working. He's spinning towards the earth upside down. And I have to tell you, I've looked at the numbers, done the calculations, and I've come to the conclusion that I don't want to do this anymore. Dude, he's coming straight at us! What the? Oh my God, this guy is nuts. And I'm trusting my life in his hands.
But it's too late to hot-foot it out of here now. Tori is fitted with a heart rate monitor and temperature sensors.
What do you think? Think you could do some foot modeling?
Maybe for fungus cream.
Memorize where it is.
As Sean, the pilot, goes through the safety briefing, Tori definitely has the look of a guy with cold feet.
If we have to jump, I'm going to say bail out, bail out, bail out. Be prepared. You're going to hit the tail, boom, and you just push yourself away.
You okay?
No.
Here we go.
I believe he's starting with the inverted flat spin.
Oh, you're doing good? Yeah. Here we go. You ready? All right. 2, 3, 4. Oh, my gosh. Doing good? Yep. You're doing good? Oh, my God. How'd that feel? Oh, my God. Woo. What's your heart rate? 140.
I have a feeling if he's got cold feet, right now.
Oh, my God. That was terrifying.
They're not going easy on him, are they?
Nope. And for the next 15 minutes, Sean puts Tori through the ringer, doing everything he can to scare his pants off and freeze his feet.
The earth just keeps moving all over the place. This is where we got to make the decision or we die. And we made the right decision. Ooh, crap. There we go. That's 3. All right. All right, Sean, I think we got enough data. And I think I'm done.
Okay, well, if we look at the temperature of your feet all the way up to the plane ride, it's at 96.2, which is exactly the same as your baseline.
Seriously?
Yeah.
It's not looking good for the myth. I mean, I know I might have looked like I was having fun, but I was actually terrified.
Yeah, but check this out. Before each of the big stunts, there was a slight drop in temperature in your feet.
Yeah, but it's only a degree or 2.
They need more data. Next up, Grant will be wired up with the same sensors to face his worst nightmare, tarantulas.
Here you go. That way the spiders don't get in your eyes.
The theory on why the cold feet myth might stand up is that during the human fight-or-flight response, blood runs to the vital organs, leaving the extremities, such as the feet, out in the cold.
Okay, Grant, I want you to meet Avicularia avicularia, more commonly known as the pink-toed tarantula.
Grant can call a halt to proceedings whenever he wants, but for now, he's keeping his mouth firmly closed to stop intruders.
Heart rate just jumped to 139.
He has to keep his eyes open, and the test will last a maximum of 2 minutes.
You ready? Here we go.
Which starts now.
Whoa! Keep your eyes open. Look at that dark one. Woo! 1 more minute.
1 more minute, Grant. Oh my God! Oh my God, look at the one in his hair! Last spider.
That one went straight across his face.
Grant is clearly scared, but is it affecting his foot temperature?
30 seconds left. 30 seconds left.
It is, quite literally, the stuff nightmares are made of. But finally, he hears the magic words.
Okay, let's take the box off.
All right, here we go.
Okay, there's no spiders around his neck, so we can slide this off.
Wait, hold on. Okay, good.
And
nice work, buddy.
You made it! Yay!
You okay?
Yeah. I don't really think I can adequately describe that scurrying.
Okay, check this out. First control, heart rate 87, temperature of his feet 96.3.
Okay, that's normal.
Okay, we stick the spiders in front of him, heart rate 139, and the temperature of his feet dropped to 81.9, and remained that temperature for the rest of the time the spiders were on him.
Wow, he actually got cold feet.
An impressive drop of 15 degrees means the myth is heading in the right direction. Now, it's vegetarian Carrie's turn to step up and face the banquet from hell.
We have chicken fingers, which is a delicacy in the American South of China. Abalone. This is concha la grande. We have kidney and liver, both uncooked and cooked, flavored with abalone slime. That way you have a choice.
She's wired up and only has to eat 2 courses. And to make it a little spicier, the guys are throwing in some live bugs.
So, the bugs, strangely enough, were the best choice for me. They seemed the most sanitary, considering most of this stuff was prepared in the shop anyway. These came out of a beehive, so I'm gonna pretend they taste like honey.
The waxworm is the larvae of a moth that lives as a parasite in beehives.
What's your heart rate at?
116.
Oh my God, she's at 82.9 degrees. Looks like you're scared.
This is awful.
Carrie's foot temperature has already dropped by 13 degrees, and she hasn't even eaten anything yet.
She did it!
It wiggled in my throat.
Heart rate, 149.
Temperature, 79 degrees.
I can feel it in my throat.
Is it still moving?
For her final course,
Ooh, you better eat it. It's getting away.
Carrie selects the Chinese brown cricket.
Hey, don't play with your food.
You're like a cat. You're just playing with your food till you eat it, huh?
Shut up, both of you. Not sure the cricket was the best choice. I'll tell you why. It's stuck. Oh. You ever get a popcorn shell stuck in the back of your throat? I think there's a leg. I think there's a leg back there.
And as you can tell, you got cold feet.
Yeah, check out here, your control. You start out with a heart rate of 110, and your foot temperature is 96 degrees.
And when you walk into the room, your heart rate goes up to 130, and the temperature of your feet went down to 84.
Well, I think that graph is pretty clear. The decline in temperature in my foot just goes...
Yeah. Particularly here, when you eat your first bug, your heart rate goes to 149.
And when you started choking on the cricket, look what your heart rate is.
Oh my God.
And your temperature is 78.6 degrees.
So, for Carrie and Grant, the myth is clearly confirmed. Their foot temperature dropped by an astonishing 15 degrees or more. But Tori's results weren't nearly as conclusive. So where does that leave us?
So you had a small drop in temperature. It wasn't quite as significant as Grant or mine, but still a drop. So we're gonna have to call this one plausible.
Wow, that's cool. All right, plausible.
For our final human myth, Adam and Jamie are trying to get to the bottom of an oft-overlooked byproduct of metabolic function.
We got flattest to death. This is a myth about a large man living on a diet of beans and cabbage in a small, close room who apparently suffocated by inhaling the deadly cloud of gas that hung above him.
It's a myth from the bowels of the internet. But is this story toilet trash, or does it have a ring of truth? Can flatulence really be fatal?
You know, in order to get started with this, we have to physically determine the actual size of a flatus and what its constituent components are.
Well, that means we have to come up with some sort of device to actually catch a flatus, right?
There's no denying Adam's an expert builder of oddball inventions. But will his bath-based flatus catcher really cut the cheese? I mean, mustard.
This would be the capture funnel of my flatus catcher.
If it does its job, they can then take the trapped air to a lab to be analyzed.
I don't know why you didn't just use a balloon, stuck it in your butt.
With Adam's trap tuned up and a bubble bath on standby, everything is ready for the main event.
My dignity and good television. They'll never meet.
It's a sad truth. The lower Adam stoops, the higher our ratings. So hurry up and get in there.
Oh, God, it's so cold. Oh, dude, that's wrong. For some reason, the cold water's making me pucker up.
But as his body gets used to the cold, finally we have some action.
Hey, we got one! We got a nice 13.5 milliliter flatus.
I think this is the first time anyone's ever tried this on television.
The second, third, and fourth times soon follow. Then they're locked before the team draws straws to see who has to take them to the lab.
I have 4 specimens of flatus to bring into the UCSF mass spectrometry facility. They're going to test them and see exactly what's in them.
Not quite the lunchtime delivery these guys were hoping for.
Well, what we're going to do is take this sample, and we'll open up the stopcock at the top. We'll put this syringe in, pull a volume of air out of there, and then we're going to inject it on here, and they will be analyzed to tell what they are.
When it all sounds so simple, you just know there'll be trouble.
Oh, God!
A quick spray of not so much eau de cologne as eau de colon.
That can't be good for you.
So what are the main constituents of the sample we just took?
So what we're mainly seeing is 28 and 32, which would be nitrogen and oxygen, which of course is the main constituents of our air. There's a little bit of 40, which would be argon, which also is a normal constituent of air. We're seeing some methane and some carbon dioxide.
Adam's air salute also contains hydrogen sulfide and methyl mercaptan, the smelly gases of flatus.
I hope this is the weirdest thing you have to do today.
While Carrie's been on her errand, the boys have been busy building a suitably small bedroom. Now they need a test subject. Yes, the long-suffering Buster.
There we go.
And with the room sealed up, everything's ready for the gas. They're first going to test with carbon dioxide.
The reason we're going to start with CO2 is because of all the constituent gases that make up your flatus. It's the one we think it really has the highest potential to be the most deadly and come out in amounts large enough to actually be plausible.
Regular air does contain carbon dioxide, but there's so little of it, just 0.03%, that it's harmless. But at higher levels, it turns hazardous.
At concentrations of about 2%, we have cerebral dilation, we have increased blood pressure, nausea, confusion. At about 10%, we have death within minutes.
And to see if they can get to the deadly 10%, they're going to turn the dial right up to Flatus Maximus.
The largest flatus recorded in the research we have is 170 milliliters per hour. And given that the largest amount of CO2 in flatus in the study we have is 80%, that's 140 milliliters of flatus. This might be the meanest thing we've ever done to him.
Slow but deadly.
3, 2, 1. All right. That is 1 hour's worth of CO2 in flatus production.
Well, we're showing absolutely no change on the meter.
The meter's staying at 0.03%, nowhere near the 10% needed for fatality.
So I'm going to add another hour's worth of CO2 in flatus. That'll be 2 hours total, 280 milliliters of CO2.
Okay, go for it.
Okay.
No difference.
Let's add 2 more hours. That's half the night.
With no change in the reading so far, they decide to add a whole night's worth of gas emissions.
And that is 8 hours worth of flatus, of CO2 from flatus entered into Buster's little bedroom. What does the meter say?
Well, we're actually up to 0.06%.
The level's doubled, but it's still way too low to be deadly.
If you want to get to 10%, 2,600 hours. It's 110 days to reach the lethal limit of CO2 in a sealed room if all you're doing is passing gas. Look, breathing is going to cost much more CO2 production than flatus.
He's right. A previous test showed breathing could potentially produce enough CO2 to kill you. But flatus CO2 alone? No way.
It's virtually impossible to die from suffocation, from CO2 poisoning, by flatus.
But could any other flatus ingredients be the culprit? What about methane? Deadly at 2%. How long would that take?
441 days.
So, methane's out the window. What about hydrogen sulfide?
That's 193,220 episodes of flatus, or 22 years of solid gas passing. That's a commitment.
They did the math for all gastric gases and found that death by flatus would take anything from 4 months to 22 years. This malodorous myth is busted. But now for some tall tales of creatures great and small, as the team takes on 3 myths.
I know, where is he?
From the animal kingdom. For our first myth, Adam and Jamie are going to see if the world's largest land animal is freaked out by one of the smallest.
Like in the cartoons.
Exactly, except we're going to test it in reality.
I don't want to use a circus elephant. They're trained. I think we need a real elephant, something out of the wild.
So we need to go somewhere where elephants wander in the wild. Africa! Let's go to Africa.
The untamed wilderness of Africa is no place for the foolhardy. But Adam and Jamie are going anyway.
Now, we've brought a bucket full of mice.
Yes.
And I understand you have some elephants.
We do indeed, yes. We've also got the lions, the leopards, the big 5.
Let's not get carried away. With their first look at the elephants, the mouse myth seems more and more like mumbo-jumbo.
Behind me are our test subject elephants. Now, these guys are semi-habituated, which is the only reason I'm allowed to be this close. If we were actually in the wild, this would be extremely dangerous.
Back in the safety of the truck, the boys need to work out just how to get their minuscule mice next to these massive mammals.
All right, so the elephants are over there. We've got their arch nemesis right here. How are we gonna get this mouse to those elephants?
Slingshot.
Okay, seriously. We need to improvise some kind of mouse delivery system, something that won't freak out the elephants.
Well, where there are elephants, there's elephant dung. So maybe we get a ball of dung and we'll dig a hole and put the mouse in. Then we'll just yank
Pull
it over.
string.
Yeah.
That's great. That's a total MacGyver solution. That's exactly what we should do. Let's go find some elephant dung.
Okay.
It's a race to the, bottom.
You go that way, I'll go this way. Don't get eaten by a lion.
Okay.
May the best manure win.
Hey, Adam. Got some.
A job well done. Now, Adam's going to work on the ingenious mouse delivery system.
In the course of doing MythBusters, we've done some pretty elaborate builds. This is not one of those builds. Allow me to demonstrate. You take your piece of elephant dung, and you take your mouse. This is a stand-in mouse. The real one will be later. Put him in the hole, cover him with the cardboard. Lay it out, and think elephants are gonna come on by. And wait in the distance with your monofilament. When the elephant gets near, boop, you expose the mouse and all hell breaks loose.
At least that's the theory. It's a trap that's as sneaky as it is squeaky.
We've chosen this area because it's open enough that we can see what's going on. And we know there's some food over in that direction. And we're hoping that the elephants will come through here on their way to the food. And at the right moment, we'll roll over the ball of dung, release the mouse, and see what happens. Hey, Adam, are you done yet?
I'm all set, ready to go.
Time for some predictable predictions.
For me, I see this the same way I would see a person looking at a fly on the ground. It's going to be so small that you may not even notice it. I don't see any reason why an elephant would be afraid of a mouse.
Honestly, I don't think much is going to happen. I don't have high hopes for this myth.
With the sensible money on the no reaction theory, it's go time. The elephants innocently approach the dung of doom in what must be the most easy to anticipate outcome in MythBusters history. But then, as crazy as it seems, the elephant backs away. The MythBusters, like me, are flabbergasted.
What just happened is a classic MythBusters scenario. We were all like, yeah, right, this little guy's gonna scare those big guys. And it did. I mean, our jaws just dropped because it was clear as day. The mouse came out, the elephant stopped in its tracks, like, whoa, and then it gently tiptoed away as if this thing was deadly. We all thought this was never gonna happen, yet there it was.
It looks like it's true that elephants really are scared of mice.
That result was pretty shocking.
Yeah, it blew me away. I mean, maybe it was the movement of the turd itself and it wasn't the mouse. Why don't we test it without the mouse?
Okay, that sounds good.
Working under the assumption that it must have been the movement of the dung, not the mouse, that freaked the elephant out, the boys reset for take 2. Dung movement only. But this time, the elephant was undeterred. This is getting ridiculous.
He didn't seem to respond to the ball of dung at all, and I think my timing was exactly the same as it was with the mouse in there.
It works for me. Elephants are afraid of mice.
So not only was I totally wrong in the first test about the elephant not reacting at all to the mouse, but after it happened, I was sure that it was the dung moving. I was absolutely positive that it was the dung moving. So we do another test, the dung moves, the elephant doesn't even notice. It has to have been the mouse.
Working on the basis that science is repeatable, the boys are going to retry test 1 to see if they still get this incredible result.
All right, let's see what happens. Okay.
For the final time, the elephants approach. And lo and behold, in this David and Goliath battle, David wins again.
He definitely seemed to take notice of the mouse, like it was a significantly different thing than just the dung. I wasn't dreading this result. I'm always pleased to be completely wrong. I'm more astonished that I'm finishing the day calling something plausible that I knew wasn't plausible when I got up this morning.
When I first heard this myth, I'd say I put it in the same category as something like, you know, when pigs fly. But there it was. It happened. He definitely didn't freak out, but he was very cautious. The mouse had his attention. It's that little grain of truth that we always look for in a myth, and there it was.
From the start, everyone thought this myth had junk in its trunk. Until a tiny mouse sent those pachyderms packing.
How are we gonna call this one?
Well, it wasn't a stampede. It wasn't like the cartoons, the elephant freaked out at the sight of the mouse. But the idea that the elephant was cautious around the mouse, I'd say we have to call that plausible.
I'd agree.
What do you think?
Hello.
For our next myth, Carrie, Grant, and Tori are going to test if bulls really are riled up by the color red.
Okay, so how are we gonna test this? I mean, these bulls can weigh over 1,500 pounds. Not only are they dangerous, they're really unpredictable.
I think it's really simple. I'll just put on a red sweatsuit, I'll stand in the middle of the ring, and we'll let some bulls out and see if they charge me.
Or how about Carrie and Grant check first how dangerous getting in the ring with a bull is from a real rodeo clown?
Oh, yeah, it can be a very dangerous job. I've lacerated my pancreas. I've had a bull stick his horn through my arm. I've had a bull that I didn't even see him coming. He hit me right in the side. He actually broke my femur in 4 places.
Oh, my God. Okay, now I'm a little scared for Tori.
Me too. And I'm only the voiceover guy. Let's go to plan B. Make 3 robotic matadors, each capable of waving a different colored flag.
So what we're gonna do is use these molds to make some foam bodies. We already have Grant's head cast. We need to make Carrie's now, and then eventually I need to make one of mine. And then we're gonna put our faces on these dummies so that the dummies get hurt and we don't.
There you go, buddy.
Thanks.
Okay.
Wait, no, I got another itch. It's lower. You reach that one? I can't reach.
The dummies' bodies are made of soft foam so they won't hurt the charging bulls.
Remember, you gotta get rid of the hands and feet, too.
They're nice little movers in the ballroom.
A little rough on your partners there, aren't you?
But how will they go in the bull ring?
Kind of creepy, huh?
They've got a blue, white, and red dressed matador.
Come on!
And the bulls are all charged up.
These bulls look ready. They look more than ready. So maybe we should get out of the pen and get the tests going.
We've got our 3 dummies lined up, and they're gonna be waving their flags and see which one the bull goes for.
Oh, now he's going for white.
The bull went straight for the white dummy, not the red. Meaning the myth, like Grant's dummy, might need some resuscitation.
Are you done playing with yourself?
There's 2 dummies still standing, Carrie in red and Tori in blue.
Apparently these guys have a Mexican fighting bull, and these things are trained just for that, to attack.
Oh, he's going for the camera!
After bidding adios to the camera, the bull ignores the red Carrie dummy before things get a little gory for Tori.
Oh, he just moved past. Oh, wait, look at that. Isn't that cool? It's like the last one standing is Carrie Red.
The bull chooses red last, not first. So if it's not color, what is making this toro loco? Next, they'll test the theory that it's a moving flag and not a red flag that infuriates bulls. With Grant moving the blue flag with his remote, while the red flag remains stationary, the results are plain for all to see.
Move it. Look at that. Dude, I am totally convinced.
In proving that it's movement, not color, that enrages the bulls, they've hit the bullseye. But why?
So far, our findings do not show that red does anything magical. They seem to go towards movement rather than actually for the color red. Why is that? Are they colorblind?
Well, it's a common misconception that they are colorblind, but in fact, they're not. In the last 10 years, people have looked at animals with hooves and found out that they're what's called dichromates. They can see 2 main color types. Humans are trichromates. We can see the rainbow and all the colors in between.
Color perception is a complex field of study, but basically, the human eye has 3 types of cone cells that help us distinguish color. But cattle only have 2. So although they can see reds and blues, it's likely they see the world with a muted palette of color, like this.
Okay then, so bulls can see red, but there is no scientific evidence to prove that makes them any more enraged than any other color.
Absolutely. There is no scientific evidence to support that.
Which means it's safe for Tori to face the bull dressed entirely in red. We think.
Nervous? Hell yeah, I'm nervous.
This is our ultimate test of the color red to a bull myth. Now what Tori's gonna do is he's going to wear a full red jumpsuit and stand in the middle of the arena completely still. We have 2 professional bullfighters that are gonna be running circles all around trying to attract the bulls. We think that motion is what sets them off and not the color red. So if the bulls attack the cowboys, but they don't go for Tori, we will have definitely proven something about this myth. Personally, I'm really concerned.
This is starting to feel like a bad idea.
Tori, are you ready?
I don't know. Yeah, I guess.
Let's do it.
Okay, release the bull.
It's the moment of truth.
Clever guys running around.
So far, so good. The angry 1,000-pound bull has only charged the moving cowboys.
Somebody come back to this side now. Back over to this side.
But suddenly, with the cowboys out of position, Tori is left exposed. For a heart-stopping moment, man and beast size each other up.
More movement, more movement.
Oh my God!
Good job, dude, good job.
He was looking right at me.
I know.
Toreador Tori survives. And as the bull is ushered away, everyone lets out a sigh of relief.
We just finished the test, and it was a perfect result. One, I didn't get hurt. But two, the bull came out, and it was looking at us, but his attention was always on the bullfighters. A good thing for me, red flag to a bull is busted.
Busted.
And we're glad you're not.
For our final myth, the boys are on the trail of a canine conundrum.
What's the myth? Bloodhounds.
What about them?
We're going to test whether you can trick bloodhounds like they show in the movies.
You and I get to play fugitives?
Something like that.
Oh, cool!
Bloodhounds are the ultimate trackers, but can they really be foiled by simple techniques?
Can you guess what my role is today? I am the chasee.
And here's the chaser.
This is Morgan. He's a 2.5-year-old bloodhound.
Morgan and his handler Matt work in the San Mateo County Sheriff's K-9 unit. Today, Adam's going to try to throw Morgan off the scent using 6 different methods often seen in the movies. But will any of these stop Morgan finding his very guilty-looking fugitive? Test 1, the zigzag.
I am going to be zigzagging. I'm going to be doubling back on my trail, and I'm going to finish off with a lovely climbing of the tree.
Adam has 5 minutes to get as far away as he can.
Okay, that was a zigzag.
Using the most confusing mix of double backs he can muster.
Hello, team. This is Convict 1. I'm hidden.
Time for Morgan to go get. First, Matt shows him the scent article.
Smell.
Eat one of Adam's unwashed T-shirts. The scent a bloodhound detects are the millions of skin cells we're constantly shedding. These minute particles carry a person's unique scent signature. They rub off on anything we come into contact with, and we leave a trail of them wherever we go. A trail Morgan seems to have picked up on mighty quickly, despite Adam's zigzagging path.
Where is he?
And pretty soon, our police pooch is barking up the right tree.
So good boy, where'd he go? So good boy, where is he? Oh boy.
So that's myth number 1 busted. And if this were real, Adam would be headed back to the clink.
I just want to say, if this looks like fun, it's twice as much fun as it looks like. This is like, wow, who hasn't wanted to try this?
Time for test 2, the river cross.
Try and not let the dog see where I'm going.
Okay. Look at the tree, bro.
And he's off. With a 5-minute head start, Adam attempts to lose his pursuers with multiple river crossings. And just like in the movies, he makes his way up one stream for at least 100 feet before getting back onto dry land. But did his tactic wash away the trail? It looks like the answer is no.
Oh, great.
Because Morgan doesn't even pause. He's following and finding his quarry like Adam's wearing a homing device.
Ah, so good boys! Ah, so good boy!
No way! That's impossible!
What a good boys you are!
Dude!
You're just a stinky guy. What can I say?
So how does he do it? Turns out that as long as the water is slow-moving or still, it has the potential to retain a subject smell better than dry land. So the myth that water will foil a bloodhound doesn't hold any water. Test 3, masking your scent with pepper.
This time I used MythBusters brand ground pepper. I had a confidant of mine stash it in this barn where I knew it would be. And I sprinkled it all over the floor of the whole barn, and then I jumped out the window. And the theory, this is right from the movies, is that the dog smells pepper. Can't smell human smell anymore.
Where'd he go? But not only does Morgan find the barn peppered with pepper,
Couldn't be in there.
Let's go. Come on, let's go. Where'd he go?
he also finds the exact path Adam took outside. And pretty soon he's banging on Adam's door again.
You found me.
Despite the peppery problem, Morgan once again gets his man.
Well, I think we proved that it doesn't work.
Well, it didn't hurt Morgan.
Is there anything that can beat this bloodhound? How about when Adam does a complete full body wash and puts on a full new set of clothes?
I have no doubt he can find my wash basin. The question is, can he follow me from there?
Where'd he go?
For a moment, Morgan is overwhelmed by the sheer amount of scent.
I know, where is he?
But he soon gets back on track.
So what are you taking? Boiled again.
Time to try masking the scent with coffee and cologne.
It is a very strong scent, and so I guess the theory is that it will overpower the dog's olfactory abilities.
Oh, no! No!
There's one test to go, so Morgan's not out of the woods yet. Well, actually, I'll take that back.
I suppose the secret's out about what this test is about.
Yeah, this is just downright mean.
Oh, really?
Yeah, oh, yeah.
This is a hard one.
Yeah, for us, this is hard. Some people, not hard. For us, this is hard.
The urban environment theory is that it makes it harder for the dog to find me for two reasons. One is that the area is heavily trafficked by other people. The other is that it's harder for him to smell my scent on pavement.
Adam has laid down a 6-block urban maze of a trail, the ultimate test for a bloodhound.
Good boy. Where? Smell. Get him.
Straight away, it's apparent that Morgan is a little distracted by all the interesting big city smells.
Leave it. Let's go. Where'd he go? Leave it. Let's go. Get to work.
Too much stuff going on here.
Matt, realizing that Morgan has lost his focus and the trail,
Leave it. Let's go. Get to work.
brings him back to the start in an effort to pick up on the scent again.
Smell. Get him. Let's go.
The team have clearly followed a different route to Adam, but after 90 minutes of false leads, they finally find their furtive fugitive.
That's a good boy.
An incredible find. But as Adam points out, there was an element of luck.
Well, I'm amazed that you found me because I didn't go that way. I came that way. I came through a car park, and in fact, I even left a couple of scent pools for you. I got down on the ground and grinded around, gave you a little gimme, and then I came through an alley back there and came this way. I wouldn't chalk this up to sheer luck, but I wouldn't call it 100% find either. I'd say it's somewhere in between, and Morgan's still a young dog, still work in progress, still learning what he's doing, and this is, without a doubt, the most difficult environment for him to track someone in.
Morgan and I haven't yet concentrated on urban environments. It's possible that if you did it with a dog with more urban experience, you might get a different result.
This has been really a wonderful experience for us because it's like magic what this dog can do. It's also really impressive to see a man working with the dog. It strikes me as something that's more like an art. This isn't just like a machine that's picking up scents. This is a combination of the man and his relationship with the animal, taking advantage of what the animal can do, picking up those little tiny hints of what's going on and trying to pull it together into a composition that ends up catching the bad guy. It's really something special.
And at 6 zip, every single one of our bloodhound myths was busted.